Good afternoon, students. How are you all doing? Just let me know if my voice is clear, the video is fine, so we can start. Okay, perfect. So yes, we are going to start combinatorics. It's going to be the next couple of weeks. We are going to be studying combinatorics. It's entirely in English. This course is especially for those students who are not that comfortable with Hindi. We have brought this course for you. I know it's very hard to understand something in another language, so we really cared about you. We really listened to your request, and this course is going to be entirely in English, which means the entire country should be somewhat listening to this, somewhat be able to understand this, right? Because a lot of you, I know you are comfortable with English, you're comfortable with the Olympiad in English, but if you're not, there's already courses in Hindi, in English, whichever language you prefer, but just for your information, this course is going to be entirely in English. Okay? Okay. So the topic combinatorics, it is one of my favorite topics, not because it has a lot of interesting theory. It's more about how you apply that theory. So it's very easy. Understanding the theory part is the easiest in this chapter, but how do you apply that knowledge? How do you actually solve problems? That is the trickiest part. So we are going to start from absolute zero level. We are going to start from very basic level, and we're going to move on to advanced level. Some of the topics I learned at IIT. So yes, this course is going to take you from zero to literally an advanced course. So I hope you guys are excited. Okay, there seems to be some voice issues. Usually there isn't. Just let me know if the voice is an issue. I will check. Okay. It seems normal from my end. Let me still confirm. Okay, so it seems everything is as high as possible from my end. If there is any issue, maybe check your system. Maybe the volume of your device is not the highest it can be. I hope you can figure it out. You guys are smart. You guys are very tech savvy. I know you will be able to handle it. All right. So I see some questions in the chat. Have I given RMO? Yes, I did. I did not have IOQM back in my days. Like I graduated from high school in 2014. That's when I appeared for JEE. So back then we did not have IOQM. I'm so happy that you have an easier level to get you started. You don't directly have to go to RMO now. But yes, I did appear for RMO from Delhi, and I was in the list, but I did not go further because I knew I really wanted to go for engineering. I wanted to focus on JEE, and that's what I was told, that I should focus on JEE. I don't know if it was the best decision. Maybe I would have enjoyed the other path as well, because I do love maths. If you know me, you know I love maths, and I would have loved taking that path as well, but it was just not part of my plan, so I just stopped. I took the test and I was in the top 20 list. Those were the ones who could, I think, qualify for INMO or something like that, but I did not go further. I did not go for the camps or anything. So yes, I did not really prepare, unlike you all. I did not prepare for RMO, I just did it for fun. I did just go through the questions from time to time over the years, because they are very interesting problems. It really is a very good exercise for your brain. So I have been going through RMOs, INMOs over the years. They are some amazing problems. So I'm very happy for you that you are preparing for it. It is going to be really effective no matter what path you are going to take in your life. Trust me. If you are learning maths that way, if you are actually exercising your brain that way, you're going to prepare for every field, because you're actually preparing to learn better, to be able to apply those things better, and that is going to be helpful no matter where you go in life. Okay, a lot of long messages. What's the correct approach to do the questions? You understand the theory, you understand the solved examples. Okay, that is a very common problem, trust me. That's the most common problem in your prep days, right? That you are able to understand the theory, and once you see the solution, you're able to solve the questions, but it's somewhat impossible to approach a new problem, a problem that you've never seen, a difficult problem that you have never seen before. And for that, there is only one solution: practice. The more you practice, the more variety of questions you practice, the more you're going to learn, the more you're going to understand how to see, oh, this seems to be a problem of that topic, even though it's asking for something else entirely, but I have seen something like this before. I have seen how I can solve this kind of problem by using that particular approach, because I practice. So trust me, there is no one-shot trick. There is no, if someone claims that, you know, this is the way to actually be able to solve any question, no, there is not. It's only by practice. It's only by being mindful while practicing. I'm going to talk more about that from time to time, but let's start. I don't know. I think everything is fine. I use this setting for all my videos. It's really low. So combinatorics is a topic that is somewhat common in JEE as well as IOQM. So you are preparing for JEE as well. In fact, you're preparing one level up. So you're not just preparing to the JEE level, but you're actually preparing to a level above that. So yes, it's going to be very similar. Yes. So in JEE we call it permutations and combinations. Here, because it has some topics other than PNC as well, so we call this combinatorics. This entire field is called combinatorics. Okay, so let's start. Okay, so some students are saying that the sound is fine. Some students are having a problem. Maybe it's device dependent, which device you're using to watch this video, but I'm sure if you use some earphones or headphones, you can solve that problem. All right, so let's start. See, combinatorics is something very basic. It's literally, especially when it comes to PNC, it's literally answering this very simple question: how many? How many ways can we do this? How many cases are possible? How many options do we have? How many ways of looking at something? That is all what PNC is about. So for example, if we, let's say, ask something very simple: how many 3-digit numbers can be formed using 1, 2 and 3 without repetition? So without any other knowledge of PNC, we can just think we need 1, 2 and 3. We have 3 digits, we cannot repeat it, and we need to form 3-digit numbers. So we have to use all 3 of them. Now the order can vary. It can either start from 1 and then second digit can be 2, or it can be 3 and the remaining digit is 2. Similarly, if we start the number with a 2, then we have 1 and 3 left. The second digit can be 1 or 3 and the remaining third digit. Similarly, if we start with a 3, then we have 1 and 2 remaining. So 1, 2 or 2 1. So we have counted all the possible numbers, right? There's only either 1 will be in the hundreds place or 2 or 3. So we are sure that we have counted all the possible numbers. So that means the answer is, how many are possible? 1, 2, 3, 4, 5, 6. Right? Now, this was easy to count. Let's say, now we have a similar problem, but we added another digit. Now we have to form 4-digit numbers using 1, 2, 3 and 4. Let's count. Now, same as before. The thousands digit, the first digit from the left can be 1, 2, 3 or 4. Right? Then next digit can be 2 or 3 or 4. It cannot be 1 because no repetition allowed. So let's count like this. Then further we are left with 3 and 4. So the next digit can either be 3 or it can be 4. Now the fourth digit we know because only one digit is remaining. In this case it's 4. In this case it's 3. So like this we can count for each of these cases. Let's do it quickly. 1 3, now 2 and 4. So 1 3 2 4, 1 3 4 2. 1 4, so what are the two digits remaining? 2 and 3. So 1 4 2 3, 1 4 3 2. So starting now, just observe a pattern. If we started with one particular digit, we could form 6 numbers. So if we start with 2, we're going to get another 6 numbers. We're going to start with 3, then we get another 6 and another 6. So total 6 plus 6 plus 6 plus 6, 24. If you don't believe me, you don't want to take any risk, let's count them all. 2 1 3 4, 2 1 4 3, then 2 3 1 4, 2 3 4 1, 2 4 1 3, 2 4 3 1, and so on. Do you really want me to finish all of this? Okay, I know you guys know the answer. You guys know how to calculate. This is very easy, right? But we are going to start from basics. We are going to understand where those formulas are coming from. So as we thought, 6 numbers with each starting digit, right? So total answer is of course 24. But a thing to observe here is, once we fixed the thousands digit, now we have 3 remaining digits, right? We have, let's say we fixed the first digit as 4. Then we had 1, 2 and 3 remaining, and then essentially we had to form 3-digit numbers after 4. And we saw that 3-digit numbers using 1, 2 and 3 is 6. So that is why, starting with 4, we got the exact same 6 numbers. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So that is why once we fix one digit, we are getting 6 numbers. And for that one digit, that thousands digit, we have 4 options. 4, 3, 2, 1. For each of these cases, we are going to form 6 numbers just like before. So that is why we get 6 plus 6 plus 6 plus 6. But we saw that to be 100% certain, we cannot keep writing all the numbers, right? I mean, this was just 4 digits. What if we want to check for 7 digits? What if there could be repetition? We can't list all the cases. We need to be smart about it. We need to see these patterns and find some sort of a formula to do it much faster, right? So that is where these addition and multiplication principle comes in. Let's see what it is through an example. But in general, for combinatorics, for PNC problems, the theory is best understood through problems. If I just tell you the theory, you might believe me, but it will be harder for you to understand where it's coming from, why it is the way it is, unless we see an example. Okay, so we are going to learn this entire theory through examples. So let's take a look at this problem. A person can travel from city A to city B either via road, by car, by bus, by bike. Three options for the road transport, or by train, either the express train or the mail train. So two options for the train route, and similarly through the flight route, economy or business, two options. So how many ways can a person go from city A to city B? Either he will take the road route, for that he has three options, or he will take the train route, for that he has two options, or he will take the flight route, for that he has again two options. So total possible options is 3, or these two, or these two. So total is 3 plus 2 plus 2, 7, right? Very simple. Out of these 7 options, he can take any one. So he has 7 ways of going from city A to city B. So that means if we ever have an OR situation, we are simply adding. So this is one thing you have to remember, that whenever it's an OR option, like either one case is possible or another, one option is possible or another, in that situation you always add. Either he can take the road route or the train route or the flight route. Alright, so that is when we add. But what if it's not an OR situation all the time, right? For example, now a person can travel from city A to city B via road, train, flight, the same as before. But now city B to city C has other options. City B to city C, so A to B we had 7 options, right? Let's see B to C. B to C we have again 3 road options and 3 train options. No flight options from B to C. So B to C we have either road, 3 options, or train, again 3 options. He will only take one of them. He cannot take both. He cannot take B to C car as well as a train. He will have to pick one. So it's again an OR situation, which means we are going to add them. So 6 options for B to C. Now, in how many ways can a person go from city A to city C via city B? That means this person has to go to B and then C. So we had from A to B, we had 7 options. From B to C, we had 6 options. Now it's not an OR situation. He has to go from A to B and he has to go from B to C. It's not an OR situation. He doesn't have to pick between the two. He has to go to both. He has to go from A to B and from B to C. So in case of A to B, we had 7 options, and then again for each of these options he has 6. Let's say he takes the car route from A to B, then again he has 6 options. Then bus route, if he had taken the bus route, he would again have the 6 options. So in total we would have 7 multiplied by 6. So whenever we have an AND situation, we multiply, because he has to pick one from these 7 options and he has to pick one from these 6 options. So total 7 multiplied by 6, he has 42 options to go through to go from A to B via C. Yes, you know why 42. So the answer is 42 ways. Now, we understand if there is an OR situation, we add. If there is an AND situation, we multiply. As simple as that. We just have to be very careful. See, but combinatorics is the trickiest in its language. Once you understand the problem, once you understand the entire question, what is the situation, what do we have to do, what do we have to calculate, once you understand that, then it becomes much easier. But first, the first step is to understand the question. Once you understand if it's an OR thing or an AND thing, then it becomes very easy. Now let's take a look at another problem. We have this stadium which has 5 gates. You can enter and exit from each of these gates, any of these gates. Now there are 2 gates A and B on side 1, 3 gates on side 2. Now we have to calculate how many ways of entering and exiting are there. If, let's look at the first question, first part of the question, if it can enter and exit from any door. So for entering, it has 1, 2, 3, 4, 5 options, and for exit, he has again 5 options, and because it's an AND situation, he has to pick an entry gate and he has to pick an exit gate. It will be multiplied, which means the answer is 25 ways of entering and exiting. Any person can choose out of these 25 ways which door they are going to. Let's say they enter from B and exit from D, or they enter from B and exit from B. So in total 5 ways of entering, 5 ways of exiting, so total 25 ways. Let's look at the next part. They can enter and exit from different doors. They have to pick 2 different doors for entering and exiting. If they entered from B, they cannot exit from B, but they can exit from any of the other 4. Similarly, if they pick C for entering, then they can exit from A, B, D or E, but not by C. So that means we have 5 ways of entering. We can choose any of these 5, but once we have picked, then we only have 4. Right? No matter what you choose, for every case, let's say we choose A, then we have 4 options for exiting. If we choose B, we again have 4 options. If we choose C, we again have 4 options. If we choose D, so for each of these 5 cases, we have 4 options for exiting. So that is why we are multiplying. So 5 multiplied by 4, 20. Now let's do the next one much faster than this. We can enter from side 1 but exit from side 2. So for entering, we have 2 options because side 1, and for exit we have 3 options. So total 6 ways. We can enter and exit from any side, but they have to be different, right? Now let's take a look at this. Either we have case 1, that enter from entry from side 1 and exit from side 2, or the opposite, entry from side 2, but then we'll have to exit from side 1. Right? Now, either this will be the case or this will be the case. So it's an OR situation between case 1 and case 2, and an AND situation between these. So for case 1, Case 1, we have 2 options for entry and 3 options from side 2 for exit. Similarly, in case 2, we have 3 options for entry and 2 options for exit. So 6 and 6, but it's an OR situation, so we are going to add, which means 6 plus 6, 12. Very good. So that is how we can just form the question. So in the last case, if we had not been given these first 3 parts, we just have to solve the last question. In that case, we are going to understand how do we enter and exit. It has to be from different sides. So just list all the options, right? Now, let's take a look at another example. Cities A, B and C and D are connected through these routes. These numbers indicate how many ways A and B are connected, how many ways A and D are connected. So that means there are 2 ways of getting from city A to city B, 3 ways of getting directly from city B to city D, B to C2 and so on, C to D4, right? Now we have to go from A to D. We can either go directly or through B or through B and C, right? So we have to calculate how many ways can a person go from city A to city D without visiting a city more than once. So if we've been to B, then we are not going to go back to B. We are directly either going to go to D or to C and then to D. So we want to go from A to D. So I want all of you to calculate and tell me the answer. Just try carefully, making sure you're not missing any case. Just calmly, patiently, make sure you're counting every single case, every single option, and then tell me the answer. So yes, 24 is correct. Let's see how. So in general, bache, if you're trying to count, there are so many ways of counting, right? You can go randomly. Yeah, I can go from A to D or ABCD or ABD. We are trying to count, but then it's hard to make sure that we did not miss anything. So that is my personal tip to all of you. How do we make sure that we are counting all the cases and not missing anything? You follow an order. For example, when we were counting all the numbers, we followed an order that we first put 1 as the hundreds digit and then check the next 2 digits. And even in that case, I first put 2 and then 3. If I were randomly writing 312, what else? 132 and 123, then it's hard to make sure that you did not miss anything. But if you follow an order, first fix the hundredths digit and then you check the next digits and you do it in an ascending or a descending order, then you have the guarantee that you did not miss any case. Similarly, when I counted these entire 24 numbers, I was following the same order. I first fixed the thousands digit, then even in the other 3 digits, I followed this order: 2, then 3, then 4, and then 3, 4, 4, 3, 2, 4, 4, 2, and so on. Okay, so even in this case, how can we order? How can we fix the order to make sure that we're not missing anything? We will do that by number of cities between A and D. So we have to start from A. we have to finish our D. That is given. But how many cities can be there between A and D? First, we start with 0, which means directly A to D without any other city. Or first list all the cases, okay? Don't start counting right away. First, make sure you've written down all the cases, then count how many ways per case. Or there can be one city between them. Which city? It cannot be C because there is no way of going directly from A to C, right? So it will be A to B, then to D. Then it can be 2, A to B to C to D, right? There is no other option because from A you can either go to D, in that case we have reached our destination, or it can go from B. From B it can either go directly to D, which we have covered, and to C. So these are the only possible cases. Now we are sure, we are confident because we followed an order. But these might look easy and they are easy questions, but as the questions get harder, it is very likely that you miss some case. And that is what I always tell my students, follow an order. In that case, there is a complete guarantee that you're not going to miss any case. You're going to count all of them perfectly. Once we have this, then it's an easy question, right? From A to D, there are 2 ways. From A to B to D, first it has to go from A to B 2 ways, B to D 3 ways. So total 6. A to B 2 ways, B to C again 2 ways, and then C to D 4 ways. So total 16. And because it can either choose A to D or A to B to D or A to B to C to D. It's not an AND situation, it is an OR situation, which means we add all of these. 2 plus 6 plus 16, 24. So that is how you calculate this entire thing, all the possible cases, by not missing any of them. Okay, there is a doubt, why not take 3? Are you talking about this, Bache? Number of cities between A and D? Because total we have 4 cities. Let's say we wanted 3 cities between A and D, but there are not enough because we can only visit a city exactly once, right? So that is why you have to, of course, very good question. Why did we stop at 2? We should check for 3. Is it even possible to have 3 cities between A and D? No, it's not, right? We can maximum have 2 cities between A and D. And this is why these are all the possible cases. We did not miss any of them. Now, once we understand this addition and multiplication thing, that if it's an OR situation, add, AND situation, multiply. Now let's see our previous kind of problem, right? How many numbers can we form using the given digits if with repetition is allowed or not allowed? So in that case, what we are going to do for this kind of questions, we need to form 4-digit numbers, which means a number has 4 digits, the thousands place, hundreds place, tens place, and ones place. We have to fill all these 4 places using 1, 2, 3, 4, 5 these digits. So we have 5 options for each of these, but the first case is without repetition. Repetition is not allowed. If we've already used 1, then we cannot use 1 again. So for this place we have 5 options, right? We haven't filled any digit. We can fill any of these 5. But once we have filled this place, then we only have 4 options for this place. And then once we have, let's say 2 and 5, I have picked 2 and 5, then the remaining 3 digits, any of those 3 digits can come here. So 3 here and then 2 here. And 1 will have to be missing from this number, right? Because we have to pick only 4 digits out of these 5. It is without repetition. So total will be, we have to fill this and this and this and this. So multiply. This becomes 5 into 4 into 3 into 2, 120. Now let's see if repetition is allowed. Again, we have the same 4 places to fill, but now we have 5 options for this, just like before. But now we can fill any of those 5 again, because repetition is allowed. Even if I have filled, let's say 2 here, I can fill 2 again because repetition is allowed. So again 5 options for this, again 5 options and 5 options. So we are again going to multiply because we have to fill all of these, this and this and this and this. So 5 raised to power 4, 625 ways of forming a number. So this is how you calculate how many numbers we can form using digits, by filling the number of digits, those many places with the digits given. Good. Now let's see. It's a similar problem, except now we have a 0. If we form a 4-digit number, something like 0143, then it is not exactly a 4-digit number, right? This is a 3-digit number, which means if it has to be a 4-digit number, 0 cannot be in the thousands place. So now if repetition is not allowed, we have only 4 options for this. But once we have filled this place, let's say we use 2 for this or any of the other. Now we again have 4 options. 2 is not there, but 0 can be there now. 0 can be there, 1 can be there, 3 can be there and 4 can be there. So 4 options for this. And we have taken 1, so now we cannot use it in the other 2, which means this has only 3 options and this will have 2 options just like before. But when it comes to 0, we just have to remember that 0 cannot be in the leftmost position, otherwise it's fine. Once we have filled this with a non-zero digit, then it's the same as before. So this becomes 4 into 4 into 3 into 2, which is 96. Similarly, when repetition is allowed, for first place, again we only have 4 options. 0 cannot be there no matter what. And for the other places, we have all 5 options. Because repetition is also allowed, 0 is also allowed. So for these 3 positions, any of these 5 digits can be used. Only for the first, the leftmost position, we can only choose out of the 4 non-zero digits. So this becomes 4 into 125, that is 500. Okay, so this is how you can fill this just logically. Do not try to memorize any of this, just understand. Yes, 4 options are possible for this, and then we have to pick 1 out of the 5. So it's an AND situation, so we're going to multiply. It's all very logical. Do not try to memorize any of these, that if we are given 5 digits, then it will be something like 96. Chaliye. Now, how many ways can a student answer a multiple correct question with 4 options? We have one question which has 4 options A, B, C and D. It's a multiple correct question, which means you can choose more than one, but you have to answer. So you have to pick at least one, right? So it can be either only A or it can be B and C. So a lot of options. We cannot list all of them, right? That will be very long. So how do we calculate? Give it a minute, give it a thought, and then, okay, someone already has the answer. I want more of you to reach the answer. Ek baar just think, do it once in your head. What can be the options for this? How do we choose? And if you are struggling, don't worry, I will tell you exactly how to approach this kind of a problem. It's the same counting thing, it's the same addition, multiplication. Okay, 14. Okay, you're already using NCR. Well, that hasn't been covered yet, so that means you already have an idea, which is fine, which is you're using the right approach. It's correct. The issue is, if this number, for let's say it was some other problem, and in that case we had more than 4 options, would you count it for all the cases? No, right? You need something else. So let's see. Now, in his or her set of answers, so this is A, B, C, D. Let's say, if it helps you imagine, let's imagine an OMR sheet where there are options for A, B, C and D, right? Now that student can either mark this or not mark this. That means 2 options to fill this. Either they fill it or they don't fill it, they leave it blank. So 2 options to fill this blank, 2 options to fill this blank, 2 for this and 2 for this, right? So total we have 2 into 2 into 2 into 2, 16 ways of filling this, right? Either they fill this blank or they don't fill this blank, they leave it blank. Similarly for B, C, D, and this covers all of these cases. How? This means they filled A and they left B, C and D blank. So we did cover this case, right? When we counted 2 cases for this, 2 for this, 2 for this, 2 for this. So we have covered this case as well. And for this, they left A blank, filled B and C and left D blank, right? So that means there are 16 possible cases. But we're also counting this one case where this is also left blank, this is also left blank, this is also left blank and this is also left blank, which means they did not answer any question. And we have to answer a question. We have to choose at least one. So we are going to not count that one case. Out of these 16, that one case we're not going to count, but the other 15 are fine. So yes, there are 16 ways. If we could leave a question blank, if we could choose not to answer a question, then there are 16 ways of attempting or not attempting. But if we are answering a question, if we are attempting a question, then we have to choose at least one, right? We have to fill at least one of these 4 blanks. So we cannot count that option where we are leaving all of them blank, but the other 15, that is fine. So these 2 options were, we fill it or we leave it blank. We fill it or leave it blank, and so on. Okay. So once you are aware how to answer, how to solve these problems of multiple questions, multiple options, let's see. We are given 10 questions. We have to answer all of them. Okay, answer all of them. That means we cannot leave a question blank. Then the first part says all 10 questions are single correct, which means you can only pick one option, either A or B or C or D, but you can only pick one out of those 4 options. So how many ways of answering are there? 10 questions, all single correct. That means you have to pick exactly one option for all of them. So we have these 10 questions, right? For first question, we have 4 options. We can choose one out of these 4. We have to choose one out of these 4. We have to answer every question. Let's say there's no negative marking and we have to answer every question. Then it can be either A or B or C or D. So 4 ways of answering first question. Similarly, 4 ways of answering second. They are all independent of each other. No matter what you choose in first question, no matter what you choose in second question, there will still be 4 ways of answering every other question. So, and we have to answer all of them. That means we have to answer first, and we have to answer second, and we have to answer third. So it is an and situation, right? So that means we have to multiply 4 into 4 into 4 10 times. The answer is 4 raised to power 10. Or 2 raised to power 20, that is also correct. Okay, so very carefully, you don't have to jump to the answer, you don't have to be very quick, just patiently make sure that you're counting every case. For every question there is 4 options of answering. So that means 4 into 4 into 4 10 times. Now let's see if the questions were multiple correct, which means now there are not just 4 ways of answering. We again have 1, 2, 3 to 10. Each of them are multiple correct. No matter what option you choose in the first question, it will be an independent thing, which is very important to understand. Independent, that means no matter how you answer one thing, no matter which way you choose in one event, the other event will be independent. We will not care about what option we chose. For example, here we were going from A to D, let's say via B. No matter which of these 2 we chose from A to B, we will choose out of these 3. It doesn't matter, right? As long as we reached B, we don't care how we reach. So that means they're independent. The way we are choosing to go from B to D is independent of the way we chose to go from A to B. So whenever it's independent event, that is when we can simply multiply these. So even in these questions, let's say, so what would be an example of dependent event? How would these questions be answered dependently? Let's say there were negative marking, you're sure about the first 5 questions and you think you have marked the answers according to the cutoff. You know you will pass. You don't want to risk getting negative marks, so you won't answer. But if you were not sure in the first 5, then you would attempt, maybe you would take a guess in the rest of the questions, right? So something like that would be dependent. It depends on how you answered the previous questions, how confident you were about the previous questions. That is how you will answer the rest. So that would be a dependent event. But here it's independent. We don't have negative marking. We have to answer all of the questions. We can answer in any way. So that means for these independent questions, independent events, How many ways are there to answer one question? How many ways can a student answer a multiple correct question with 4 options? 15. For second question, there are again 15, and like that for each of them. So how many total ways are going to be there? Correct. Good. So we will multiply. Because they are independent, we are going to multiply 15 into 15 into 15 10 times, which means the answer is 15 raised to power 10. So if it was single correct, we would have 4 options for answering each question independent of the others. So 4 for each, 4 raised to power 10. Here we have 15 ways of answering each question, then 15 raised to power 10. Now, solve this and give me the correct option in the chat. There are 10 lamps in a hall. Each one of them can be switched on independently. That means there are 10 switches. No matter which switch is on, we can turn on any switch on and off independently. Number of ways in which the hall can be illuminated, which means at least one lamp should be on. At least one lamp should be on, otherwise the hall will be dark. So the hall needs to be illuminated, which means at least one of them should be on. The rest can be off, any number of lamps can be off. So if D is correct, C is not, because of this one condition. So as I mentioned, combinatorics is very important. The first step is to understand the question perfectly. Don't rush into the solution. First understand every word. They can try to trick you. Some words can be tricky. Just sit patiently and understand what the whole question means and then start answering. So here, for every lamp, lamp 1, lamp 2, lamp 10. For every one of these, we have 2 options, on or off. Independent, right? No matter what the condition, the situation, the state of this first lamp is, whether it's on or off, this one can also be on or off. Similarly, 2 for these, on or off. So total possible is 2 into 2 into 2, 10 times. That is 2 raised to power 10. But if this also counts the case where all of them are off, that is also possible. That cannot be the case because hall needs to be illuminated, which means we have to subtract that one case. You remember? We just did this before. There were 2 options, but we cannot have a multiple correct question in which none of the options was answered. That is why we subtracted that one case. The rest, all of them are fine, because they all count, the rest of them count the cases where at least one of them is on. But we have to subtract 1 for the case where all of them are off. So this becomes 1024 minus 1, 1023. So option D is correct. Now, how many 4-digit odd numbers can be formed using the digits 1, 2, 3, 4, 5? Repetition is not allowed. Okay. Are you checking all the odd numbers with it? 2 into 4 into 3 into 3. That's a weird way of counting, but sure. Let's see. So now we have to form 4-digit numbers. So just like before, we have 4 places to fill using these 5 digits. But it has to be odd. That means one's digit should be odd. As long as one's digit is odd, we don't care. The rest of the digits can be anything, just this digit. This one's digit needs to be odd. How many odd digits do we have? 1, 3, 5. These are the odd digits that we have. So there are 3 options for filling this. Once we have filled this place, the ones place is filled with an odd digit, then it doesn't matter what we fill in the rest 3 of them. As long as there is no repetition, we will get a valid number, right? So once we have fixed one digit for this place, we have 4 digits remaining. Now this can have 4 options, then we will have 3 options for this and 2 options remaining for this, just like before. The only catch here is this place will not have 5 options, this place will only have 3 options. So the total answer becomes 2 into 3 into 4 into 3, which is 72. Right? Okay, now let's take it one step up. Now we have to form 4-digit numbers divisible by 4. What is the divisibility rule for 4? Last 2 digits, yes. The number formed by last 2 digits should be divisible by 4. Very good. So that means we have a 4-digit number. As long as this is divisible by 4, we don't care what these 2 digits are. Again, without repetition. But this should be divisible by 4. Once we fill these 2 digits, then the remaining digits can be used for this and this. Let's see what numbers can we form using these, what 2-digit numbers we can form using these 5 numbers, these 5 digits that will be divisible by 4. So first of all, now we're not going to see all the numbers possible, right? We have to be smart about it. So it has to be even. That is given. That means last digit can be 0 or 2 or 4. Now with 0, it has to be another even digit, right? It can either be 20 or 40. 10 is not divisible, 30 is not divisible. But with 2, it has to be an odd digit. That means 12 or 32. With 4, again it has to be an even digit. It can either be 04 or 24. So these are all the options that we have for 2-digit numbers that are divisible by 4. So it has to be one out of these 6. But we can't just assume any of them and the rest will be the same. For example, let's say we fill 0 and 4. If we fill 0 and 4 here, what digits do we have left for these two? 1, 2 and 3, right? 1, 2 and 3, that means this place has 3 options, this place has 2 options. But if we fill, let's say 12, then we have remaining digits 0, 3 and 4. In that case, this place only has two options, 3 or 4, and the remaining 2 digits for this. So you have to be very careful. You cannot assume that, yeah, any 6 of them and then we have 3 digits, so 3 options for here, 2 options for here, and we're done. No, because if we miss this case, then it will end up being a 3-digit number instead of a 4-digit number. So we have to be very careful, which means if 0 is there in these 2 digits, if 0 is present, then we will have 6 options. Simple, right? 6 ways if 0 is present, and if 0 is not present here, then that means 0 can be here. So in that case, there are only 4 ways if 0 is not present. So in how many of these 0 is present? 1, 2 and 3. So for these 3 cases, we will have 6, and for the other 3, 12, 32 and 24, when 0 was not included in these last 2 digits, we will have 4 ways of filling the other 2. So 4 into 3 into 4. So the final answer is 30. I hope you all are smart while calculating this. You're not doing 18 plus 12. You are taking 3 common mentally, and 6 plus 4, 10, so 30. Right? Be smart with your calculations, do it much quicker. Anyway, but I hope this part is clear to everyone. How do we make sure that we are counting all the ways correctly? Because we saw 0, we remembered that 0 cannot be in the leftmost position, so we have to be careful with that. We cannot ignore that. And that is how we calculate all of these numbers. So total 30 ways of forming a 4-digit number divisible by 4 using these 5 digits without repetition. We have taken care of all of these conditions, and these are the only numbers possible. And with this, I think you will be able to solve any kind of basic counting problem in which we have to form a number of numbers or a few options to select. So I hope you learned something new, something interesting today, something that will help you understand the following lectures. It will only get more difficult, so make sure you revise everything that we did today. Just go through everything. That should be your general rule. Whatever you cover in one class, you should revise that before coming to the next class, so that you're able to apply all of these things very easily. I don't have to re-explain how that was applied. So we will start with permutations in the next class. It will be a new topic for most of you. So just come prepared with this. If you understand this, then permutations will be very easy. Otherwise, it could be a little tricky. So we will just understand the basics of factorial, what it is, and then we'll move on to how to arrange a few digits, a few people, a few objects in a specific way. How many ways of arranging a few things are there? So I will see you in the next class. Just make sure you revise everything. I hope you all learned a bunch of new things today. Even if you did or you did not, even if you knew these basics, just make sure you revise. Either way, it's going to be helpful for you. And students, there's something I would like to add, something I always tell all my students, that your one rule for any class you attend, whether it's your school, your coaching, or a free YouTube class even, you should have this one rule, that there should not be a single line that you do not understand. Everything that happens in the class, everything that your teacher says, no matter what you're trying to learn, you should be able to understand everything. If that is the goal you go with in the class, then it just saves a lot of your time when you go back and try to study it on your own. Because if you study, if you learn half of the things in the class and then you have to do all of it again on your own, it just takes double the amount of time. But if you make sure that you have 100% concentration in class, you try to understand everything that is going on, then you do not really have to study it all again. You can just revise and then move on to practice. So that should be, especially for maths, it should be your rule. No matter what class you're attending, you should aim to understand 100% of it. Okay, don't be satisfied until you understand 100%. I will keep reminding you of this, but make sure that is your goal. Okay, so there are some requests for me to take these classes a little later, because maybe you just came back from school, maybe you come back from school a little after 3 and you want to have lunch and then sit for studying. I get it, I'm sorry, but I have other classes and I am making time. This is the best time I could find, but if I can, for any day, if I can find time after 4, I will. I promise, and you will be informed in advance. I do care about you. I do want a lot of you to attend, all the sincere students to attend, and if timing is a problem, then definitely I will try my best to fix it. But sadly, I have other batches, other classes, and they are just as important. So whenever I can find time, I will definitely schedule it for later. Okay, but in case you miss some of it, the recordings are available throughout. You can refer to them anytime you want. You can watch it at any speed you prefer. You can re-watch it to understand something that maybe you missed during the class. So the recordings are there for you for whenever you need it. Okay, so let's start. I think all these students are ready now to start. Let's go. So before we start today's lesson, I just want to do a quick revision of factorial. I think most of you are familiar with what factorial is, what this operation is, but just a quick revision, it's very easy. It just denotes the product of all natural numbers until the given natural number. So if we want to find n factorial, we just multiply all the natural numbers starting from 1 up to n. So 1, 2, 3, 4 up to n. Simple. So for example, if we want to do 5 factorial, we will multiply 5 into 4 into 3 into 2 into 1. All the natural numbers from 1 to 5. So 120. 4 factorial similarly would be 24. 3 factorial, so we can find any numbers, any natural numbers factorial given this. But what about 0? We were starting from 1 and we were stopping at the given natural number. We were going in an increasing order, but what about 0? So if you want to memorize, 0 factorial is also 1, same as 1 factorial. So that is how we define it. But I know you students do not just sit back and just memorize things. You want to understand how, right? How is 0 factorial 1? It's very simple. See, if you notice a pattern between 5 factorial and 4 factorial, all these numbers are the same. The only difference is 5, which means we can write 4 factorial as 5 factorial divided by 5, right? It's the same thing. Similarly, we can write 3 factorial as 4 factorial divided by 4. 3 factorial divided by 3, that is how we can write 2 factorial. Similarly, 1 factorial becomes 2 factorial divided by 2. So by that logic, what is 0 factorial? One natural number, one number above 0, it's factorial divided by that number, right? For 1 it was 2 factorial divided by 2, so for 0 factorial it will be 1 factorial divided by 1, which is 1 by 1, which comes out to be 1. So this is how we define factorial. I hope this is very easy. Just the product of all natural numbers starting from 1 until n. Okay, now we can start today's lesson. So for today's lesson, we want to solve this kind of problems when we are trying to arrange our objects out of n available objects. So we have in total n objects. It can be letters, digits, any kind of thing. Books, people, it can be anything, but we have n objects and we want to take r out of them and arrange them in all possible ways. So how many ways are there to arrange our objects out of these n available? If you remember, we already solved one problem like this yesterday. What did we do? We had 5 digits. So n was 5. We had 1, 2, 3, 4 and 5. And we were trying to form 4-digit numbers out of this, right? So r was 4. So we had to take 4 digits out of these 5 available digits and we had to form a number with that. So we could arrange these 4 digits in any way. So we had to find how many numbers, how many ways we can arrange 4 objects out of these 5, right? Which means, I hope you all remember how we did it. We had to fill 4 places, and for first place we had 5 options. When we cannot repeat, then the next place we had only 4 options and 3 and 2. This is how we did it. So similarly, if it's n and r, in that case, for first place we have n options. For the next one we have n minus 1, and like this till the rth place we have n minus r plus 1. It keeps decreasing by 1, 1, 1, n minus 1, n minus 2. It keeps decreasing by 1 for each place, right? 5, 4, 3, 2. Similarly, for second place it was n minus 1. For third place it was n minus 2. So 1 less than this. So for rth place it will be n minus r minus 1, which is n minus r plus 1, right? So if we multiply all these numbers, we will find all the ways that we can arrange our objects out of n available objects. Now, we have something like n, n minus 1, n minus 2 up to n minus r plus 1, right? Starting from n minus r plus 1 up to n. We are multiplying all these natural numbers. If we multiply, what will be the next number? One smaller number after this, n minus r, right? Because this is 1 plus n minus r. So next number will be n minus r, then n minus r minus 1 up to 1. If we multiply these numbers, in the numerator we also have to divide with the same number. We can't just multiply with numbers, right? So we will multiply both numerator and denominator with this product. Now what is this product? This is product of all natural numbers starting from 1 up to n minus r. So that means this denominator is nothing but n minus r factorial. Similarly, numerator, it is the product of all natural numbers from 1 till n, right? Because we took 1 to n minus r and then n minus r plus 1 up to n. So this is n factorial. So the number of ways of arranging our objects out of total n available objects is n factorial divided by n minus r factorial. And we define this as NPR. So NPR is equal to n factorial divided by n minus r factorial. Alright. So if we apply this formula to our previous problem, we had 5 digits and we had to take 4 out of these 5. So the answer should simply be 5p4, which is 5 factorial divided by 5 minus 4 factorial. So 5 factorial divided by 1 factorial, which becomes 120 by 1, 120. And this is the same as the answer we got yesterday. This is the same as the answer we got just now. 5 into 4 into 3 into 2, that is 120. Okay, so we can directly do it because this is only possible when we have a small number of places to fill, right? But if it were, let's say, 100 digits, we cannot keep writing all of this. We cannot multiply all of this. In that case, we will need some sort of a formula. So this formula comes in handy. Okay, so when we are given r, we are given n objects and we have to take r out of them and arrange them. The number of ways of doing that is npr, which is equal to n factorial by n minus r factorial. Now let's take a look at a few examples. So we have 3 seats and 5 passengers. In how many ways can these 3 seats be filled with 5 passengers? Assuming only 1 passenger per seat, okay, no one has to adjust, no one has to compromise, only 1 passenger per seat, then so we only have 3 seats available and 5 passengers. So what will be the answer? Okay, so the answer will be 5p3 because we had to take 3 passengers. We had seat 1, seat 2 and seat 3, right? 5 passengers. So out of these 5 passengers, we have to take 3 and arrange them in these 3 seats. They can be sitting in any order. So we have to take all the orders into consideration, which means 5p3. So 5 factorial by 2 factorial, which is 120 by 2, 60. Simple. So how many 3-digit numbers can be formed with only odd digits without repetition? Very important. Without repetition, how many odd digits do we have? 1, 3, 5, 7 and 9. These are all of the odd digits that we have. We have 10 digits. Out of those, 5 are odd, 5 are even. So 5 odd digits, we have to choose 3 out of them and arrange them to form a number. Since 0 is not here, we don't have to worry about that case, which means we can choose any 3 and arrange them and we will have a 3-digit number. So simply it again becomes 5p3 and we just calculated the value of this is 60. Simple. Now, how many 4-letter words can be created using the letters of the word algorithm? Words may be meaningless. We just want to form a word that means a sequence of letters. It doesn't have to have a meaning. It can be meaningless. That means if we have something like LGRO, it doesn't mean anything, but it still counts as a word. So how many arrangements of 4 letters out of these given letters can be there? Now let's first count how many letters do we have. What is that? N, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means out of these 9 letters, we have to choose 4 letters to form a word, and to form a word, we can have any arrangement. So R becomes 4 and the answer is 9p4. If you want to calculate, this just becomes 9 factorial divided by 9 minus 4 factorial, which is 9 factorial by 5 factorial. So you're not going to calculate the entire thing, the entire 9 factorial. You will just write 9 into 8 into 7 into 6 and then the rest is 5 factorial divided by 5 factorial. So we'll just cancel 5 factorial and 5 factorial. Now we only have to multiply these 4 numbers. So what does it become? A lot of calculations, right? So this becomes 9 into 8, 72 into 7, 4, 504 and 504 into 6 is 3024 if I'm not wrong. That's what you get. Right? Okay, so the calculation part is something you can easily handle. We just had to make sure that we have 9 different letters, right? We have 9 different objects. These are all distinct letters, which is why we can do this. So 9 distinct letters. Now let's take a look at an example, a problem which is solely based on the formula n minus 1 pr r into n minus 1 pr minus 1. what will be the answer? Just expand these. What does it mean? N minus 1 PR is n minus 1 factorial divided by n minus 1 minus r factorial plus r multiplied by n minus 1 PR minus 1. So n minus 1 factorial divided by n minus 1 minus r minus 1 factorial. Right? Which option is correct? Try to see what you can take common out of both the terms, how you can have the common denominator and multiply. Just try it once. I'll give you a few seconds. I know you can do it very quickly. You guys are very smart. I can already tell how you are solving each question just like that. So I'll give you a few seconds. Do try and tell me the correct option in the chat. So yes, that is amazing. Option B is correct. Let's see how. So this is n minus 1 factorial divided by n minus 1 minus r plus r multiplied by n minus 1 factorial divided by n minus 1 minus r plus 1. So 1 gets cancelled and this is n minus r factorial. Now n minus 1 factorial we can take common out of both the terms, right? So this is n minus 1 factorial. Now we have these two denominators. If you look at it closely, this is n minus r factorial and this is the factorial of one smaller natural number, just smaller natural number, because this is n minus r minus 1, right? So this is one smaller natural number than this. So we will take the larger one, that is the LCM of it. So the denominator becomes n minus r factorial. How will we make this n minus r factorial? By multiplying numerator and denominator with n minus r. Now n minus r into n minus r minus 1 factorial becomes n minus r factorial. Now we can simply take the denominator common and the numerator from first term is n minus r and from the second term it is plus r. So r gets cancelled. N into n minus 1 factorial is nothing but n factorial. So this is n factorial divided by n minus r factorial, which is nothing but npr. Okay. So any of these questions you can just solve by expanding, by looking closely what we can take in common, how we can form the same denominator, what should be multiplied so that, just like LCM, what should be multiplied so that they both have the same denominator. Okay. Now, in case we had to take all n objects out of the n available objects and arrange them. Earlier we had to pick a certain number r out of those, but if we could take all of them, we had to take all of them, all n of them, and then arrange it. In that case, r becomes n, which means npr is nothing but npn. So that is n factorial by n minus n factorial. So n factorial by 0 factorial. 0 factorial is 1. So the answer is n factorial. Okay. So what does that mean? If we are given n objects and we have to just arrange them. Now this is kind of stupid to say we have to take n objects out of them and then arrange them. That just means we are given all n objects and we have to just arrange them. We have to find all possible arrangements given n objects. So for example, if we had 1, 2, 3, 4 and we had to form 4-digit numbers, that means we have to use all 4 of these because no repetition is allowed. Without repetition, we have to form 4-digit numbers out of these 4 digits. That means we have to arrange these 4 digits. The number of arrangements is the number of numbers we can form. So that will be 4 factorial. If you just want to confirm using yesterday's method, you easily can. We have 4 places. 4 options for the first place, 3 options for the second place, 2 options for the third place, and 1 option for the last place. 4 into 3 into 2 into 1 is nothing but 4 factorial. Okay. So now we have Delhi. The word Delhi, we have 5 different letters. We have to arrange these letters to form different words. If we are asked how many different words we can form using these letters, that means how many arrangements of these 5 letters can be done, right? So because words can be meaningless. So this is nothing but we are arranging 5 different letters in all possible ways. So this directly comes out to be 5 factorial. So using these 5 different letters, we can form 120 different words without meaning that will only have these letters without repetition. Now, how many numbers of 5 digits can be formed from the numbers 20537? Now we remember earlier we just had to make sure that 0 cannot be in the leftmost position, otherwise it will be a 4-digit number, right? So we remember yesterday's method. Now let's take a look how we can do it much quicker using permutation. So we can form, if we for a second, let's ignore about the 0. We are given 5 different digits. How many arrangements are there? 5 factorial. But these will also have the arrangements where first place, the leftmost position has a 0, and then these 4 digits can be anything out of 2, 5, 3 and 7, right? So how many numbers like this can be formed? We have fixed 0 in this position. That means we have to arrange 2, 5, 3, 7, 4 digits in these 4 places. That is nothing but 4 factorial. So out of these 5 factorial, all the possible numbers, we just have to exclude these 4 factorial numbers. The rest are fine. The rest do not have 0 in the leftmost position. So that is an acceptable 5-digit number, right? So that means 5 factorial minus 4 factorial, which is 120 minus 2496. If you want to confirm, we can quickly check that as well using yesterday's method. There are 4 options for the leftmost position, then remaining 4 for the second, and then 3, 2 and 1. So 4 into 4 into 3 into 2 into 1 is nothing but 4 into 4 factorial, 4 into 24, 96. Okay? So that is why this is much faster. Right now we are just trying to understand, so this still took us a few seconds, right? But once you get the hang of it, this is nothing but a 5-second problem. Okay. Now, words are created by rearranging letters of the word table. 5 distinct letters, words can be arranged, letters can be arranged. So how many possible arrangements? 120, right? 5 factorial. So 120 total words possible. Now these 120 words are arranged alphabetically, right? In an alphabetical order as you would find it in a dictionary. Then what is the position of the word table? Out of those 120 words, what is the position of the word table once we arrange them alphabetically? Okay, I see a doubt in the chat. Let's take a look at it. Sure, of course. So I see a doubt that we are only arranging 4 digits and we are finding the permutation of the digits. So how can it be 0? See, bache, we have, if we arrange all these 5 digits in any way, we don't care if it's forming a 5-digit number or a 4-digit number, we're just arranging these 5 digits in all possible orders. So Let's say one of them could be 2, I mean as it's given 20537. One of them could be 20573. Like this, 120 permutations are possible. Out of these, some will be like this, right? Where the leftmost position has a 0, which is not allowed because we need numbers of 5 digits. A 5-digit number, right? So this ends up being a 4-digit number, which is not allowed. So out of these 120, we are excluding the ones which look like this, which are essentially 4-digit numbers. How many 4-digit numbers can we form? For that, we have to put 0 here and then 2537. We have to arrange these, all possible arrangements, which is 4 factorial. So as we arrange these, we get all possible 4-digit numbers. So total 24. Out of these 120, 24 will look like this, which has 0 in the leftmost position. So you just exclude those. We don't count those 24 numbers. The remaining 96 numbers are the 5-digit numbers that we were looking for. I hope this helps. If you still stuck after this class, just sit and think about it on your own. I'm sure you will get it. Now, back to this question. So, okay, 97, 98. Let's see how to actually approach this problem in the perfect way. So, first step is, if we're talking about arranging it alphabetically, let's first see what comes first. We arrange these letters T, A, B, L, E, these 5 letters alphabetically. So, the first one will be A, then B, then E, then L, and finally T. Right? This is the order. We don't care about the meaning, so it doesn't matter if T comes first, A comes first. We will see all possible arrangements of these 5 letters, and we know A comes first, then B, then E, then L, then T. Now, when we arrange all these 120 words, the first words, the top words will have A as their first letter, right? That means we have to first count how many words are there which start with an A. So we have fixed A in the first position. How many words, how many letters do we have to arrange now? The remaining 4. So how many words, just like before, how we were arranging these 4 digits after fixing the first digit as 0. Similarly, once we fix the first digit as A, now it's just 4 factorial. So 4 factorial, 24 words are there in out of these 120 words which start with an A. Similarly, next will be B. These words that start with B, these will again be 4 factorial, so 24. So up until now we have 48 words, right? Then comes E. Again, table is still not anywhere here, right? So we still have to count all the words that are there before table. That means we will count now the words starting with an E. This is 4 factorial, again 24. So the words up until now become 72. 24 plus 24 plus 24, 72. Then next L. Again we haven't reached table. So L, again 4 factorial. So now the count is up to 96. Now we have reached T. Now we can't count all the possible words, right? Now we have to find table. So now we again do the same process for the remaining 4 letters. So just like before, the first, as soon as we start with the words that start with T, the first few words will have A as the second letter, right? But we are also looking for a word that has A as the second letter. So we're not going to count how many words are there. We know 3 factorial yani ki 6. 3 factorial, that is 6 words, right? So 6 words are possible which start with TA. But we're not going to count all of them because we are looking for one of those words, one of those 6 words. So next comes after A, B. Again we are looking for such a word. Then after that we have, what are the 2 letters remaining? L and E. First comes E, which is not what we're looking for. So this will be the 97th word. And finally, TABLE, this will be 98th word. So the correct answer is 98. What is the position of the word table? 98. Clear? So, yes, this is how you tell the position, the rank of the word table once we arrange all of the possible words alphabetically with or without meaning. Then this is the rank. Let's take another problem like this. Very similar method. I want you to try the same method. First arrange the letters alphabetically and then form the words, see which position random is at. Okay, I'll give you a minute or so. I'm waiting for your answer. But I hope you all know by now how to approach this problem, how to actually start and reach the word random. So 98 is the 619. I think it's close from, but we'll see. Just recheck your calculations, see if you didn't miss anything, see if you didn't count anything twice. You check the order correctly, and if you're sure, we'll see in a minute. Okay, so someone is saying 619, someone is saying 618, very close numbers. Let's see. So, first step is to arrange all these letters alphabetically. So, first comes A, then B, then M, N, O, and then R. Right? We have arranged all these 6 letters alphabetically. Now, just like before, we start with A. And now we have 5 possible letters, right? 5 remaining letters that we have to arrange. So that is nothing but 5 factorial, 120. Then comes D. So for D again, we have 5 factorial, which is 120. Then M, again 5 factorial, 120. N and O similarly, because R is the last one. So for N we have 120, for O we have 120. So 120 into 5, 600. Up until now we have 600 words that do not start with R. Right? Now we have to look at the words that start with R. So what was the order? A, D, M, N, O, R. Right? Now we start with R. That is fixed. We are looking for the word random. So the next letter will be A, which is what we want. Next will be D. Right? We're going alphabetically. Now we have 3 remaining letters. We have to find all the possible arrangements for these 3 letters. So that is 6. Then after D comes M. Again, we haven't reached N. So we'll count all possible words. So this is again 6. So we had up until now 600. Now we're up to 606 and 612. Right? Now comes N. Once we have N, we can't count all the words. So what will be the next letter? We have picked A, R, N. So what will be the next alphabetical letter? D, which is again what we're looking for. Then we'll have M and O. The first order will be M, O, and then O, M. right? So now this word will be random, which is what we're looking for. So this was 612, that means this is 613 and this is 614. So the rank of the word is 614. So bachas, I see a lot of 614, that's amazing. But if you were getting some other numbers, maybe you missed something, maybe you added something, maybe you got confused in the order, the alphabetical order of the letters. Either way, just be very careful, learn from your mistakes and make sure you never repeat them. Okay? But a pretty straightforward way. Yes, we have to count all of them. We have to go through this process. In a lot of these PNC problems, you will have to consider all cases. But a very important thing to remember here is go in an order so that you don't miss any case, you don't count any case twice. You get the right answer and you are a little smart in calculating the number of cases. Okay. Now, this was when all our n objects were distinct. What if they are not distinct? What if some of them are identical? For example, here we have total n objects. Out of this, P are of one kind. P objects are identical to each other. Q objects are identical to each other but different from P. And then the rest are all distinct. So P are alike of one kind, Q are alike of second kind and R are distinct. For example, if we had the letters, let's say we were doing the similar problem as before, but now our word is, instead of random, it's arrays. Now we have 2 A's, 2 R's, and then this is how we arrange them alphabetically. Now we have 2 of one kind, 2 of second kind, and then 2 are distinct. So in this case, P is 2, Q is 2, and R is also 2. P of one kind, Q of one kind, and remaining are distinct, right? So in this case, why is it different from before? Let's take a look. So when we were finding all possible arrangements of the word random, we said there will be 720 words, right? 6 factorial. We have 6 letters, so 6 factorial words were possible. We could form 720 words. Now, out of these 720 words, one of them would be random and another one would be random, where let's call them letter 1, letter 2, letter 3, letter 4, letter 5 and letter 6. So one word is letter 1, letter 2, letter 3, letter 4, letter 5, letter 6, and another word is letter 1, letter 3, letter 2, letter 4, letter 5 and letter 6. Right? These are two different words and we are counting all such words, and we said that there are 720 words possible. But if we say in a similar way that there are 720 words, 720 arrangements possible for this, in that case, let's look at this example again. So if we call this letter 1, letter 2, letter 3, letter 4, letter 5, letter 6, so this is one word arrays. And another word we are saying is when we swap letter 2 and letter 3 and the rest remain the same. So in this case, if we swap letter 2 and letter 3, it again becomes ARRAYS. We counted these two as two separate words, but in this case, these are identical. There is no difference between the first R and the second R, right? No matter which R we write first, it's going to be the same word. So in that case, we have to eliminate the words. We are definitely counting a lot of words repeatedly. We are repeating. We are counting them again. We are double counting perhaps. So how many times these words are being repeated? Now, be very careful. Listen. It's very important to understand. You can easily memorize the formula, but it's much more important to understand where that formula is coming from. Okay? So, 100% concentration, you're going to listen exactly what I'm saying, and I hope you are able to understand and follow. So that means for every such word, we are counting twice. One when first are in this position and second are in this position, and repeatedly when those words, those letters are swapped. They end up being identical. That means how many arrangements of these two R's are there? 2 factorial, right? So 2 factorial, that is 2. So there are two ways of arranging first R and second R. If we call them R1 and R2, then we can arrange first R1 on the left and R2 after R1, or the other way around, R2 on the left and R1 after that, right? There are two possible permutations, but actually they are not different. They are not R1 and R2. They are identical. So there are going to be 2 factorial words where we are counting them as different R's, where they are actually the same. Similarly, for the A's are also identical. We are doing the same thing for A's as well. So multiplied by 2 factorial. 2 factorial words are being treated as like 2 factorial times. Each word is being counted 2 factorial times, and then again each word is again being counted 2 factorial times for these two A's. So let's say total actual possible number of arrangements for this was X. So we are counting these X words 2 factorial into 2 factorial, that is 4 times. It was only X, but we are counting them 4 times, so it actually became 4X. So this is how this 4X was what? 720. These 6 factorial words, we were counting these X words 4 times. So X actually comes out to be 720 by 4, which is 180, right? So that is nothing but 6 factorial by 2 factorial, 2 factorial, right? Because we were counting each of these X words 2 factorial times for the 2 R's, and then again 2 factorial times each of those words, again each 2 factorial times for the 2 A's. So like this, that means we had to do the entire n factorial divided by the number of repetitions, their individual arrangements. So for the formula we get, if I just erase this part, then the formula that we get is n factorial divided by p factorial and q factorial. So in general, whatever we have identical repeated, we will take the n factorial like before, n, where n is p plus q plus r. The entire total number of words that we have, we take all possible arrangements. But we know that because some of the objects are identical, we're counting them again. So we will just divide those by individual repetition. So if it were, let's say, P1 of one kind, P2 of one kind, a second kind, P3 of second kind, third kind, P4 of fourth kind, like this, we have something like this situation. In that case, we will have n factorial by P1 factorial, P2 factorial, P3 factorial, P4 factorial, and so on. So no matter what kind of objects they are, if a certain group is identical to each other, then we will divide that number of objects that are identical to each other, its factorial. Okay, so the formula should be clear, but it also should be just as clear how we reached this formula. Okay, so the most important thing to remember here is this formula. We will just take all the objects, all the arrangements, and then divide it by the number of repetitions that we have. Let's take a look at an example. It will be much more clear. So now we have 3 digits, 1, 2 and 2, and we have to form 3-digit numbers. That means we have to arrange these 3 digits. So our n is 3. We have to do 3 factorial, but 2 of the objects are identical. So we will just divide it by 2 factorial. So this becomes 3 into 2 factorial by 2 factorial, which is 3. If you want to just confirm, because it's such a small number, we can just check. We have 3 digits. One can be in the first position, or one can be in the second position, or one can be in the third position. And once we have fixed 1, the remaining 2 are 2's. There is no other way of forming the number possible, right? So total only 3 numbers, which is what we are getting. Okay, so the formula should be clear, as well as how we reached this. Let's take a look at another example. Now we have 4 digits. We have to form 4-digit numbers out of this. So we have to arrange all of this just like before. Entire 4 digits, so 4 factorial divided by these 3 2's are identical. So 3 factorial, which is 4 into 3 factorial by 3 factorial, so 4. So just like before, one can be in the first position or second position or third position or fourth position. If we fix the digit 1, then the other digits will be 2, just like before. So only 4 different options for the digit 1, and that means only 4 possible numbers. So we have also confirmed it. Okay. Now, how many words can be created by rearranging the letters of the word Mumbai? In such cases, whenever we are given a word, you have to make sure that you're writing all the letters that are there. So how many letters? This is a small word, so you can easily calculate that there are 2 M's and the other are distinct. But in general, it helps that you start writing. First letter is M, second letter is U, then third letter is M again. So M is, the count for M is 2. Then B 1, A 1, I 1. So we have counted all of them correctly. So now total how many letters are there? 1, 2, 3, 4, 5, 6. 6 factorial divided by, only 2 of them are identical, the rest are distinct. So by 2 factorial. So this becomes 720 by 2, 360. Alright. So this is how you can do it. Now this was a fairly easy word. Let's take a look at a longer word. If we have the word mathematics, we're going to follow the same method as before. We'll start with M. So the count is 1, A 1, T 1, H 1, E 1, then M again 2, A again 2, T again 2, I, it's a new one, 1, C 1 and S 1. So now we have this count of every letter. Now total number of letters 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? Just want to confirm the count. You can do it from here as well. 2 plus 2 plus 2, 6, 7, 8, 9, 10, 11. So yeah, we've counted them all correctly. So the total number of arrangements will be 11 factorial divided by 2 factorial for M, 2 factorial for A, 2 factorial for T, and the rest are distinct, so it's fine. And this is our final answer. This is the number of words that we will get by rearranging the letters of mathematics. Okay, if you want to calculate, you can, but it's very important to understand how it's being calculated. Now, if an insect wants to travel from square A to square B, from the top left square to the top right square, then we have a grid, a net of sorts, which is 5 cross 3, right? So we have 15 total squares. How many ways are there to go from square A to square B? The condition is there has to be shortest possible path. Now that doesn't mean you will go directly like this. They can only travel, the insect can only travel from one square to another. Either right or left, up or down. Okay? So right, left, up or down. It cannot go sideways. That means if it wants to reach this square, it will have to go either like this or like this. Okay? So first right, then down, or first down, then right. So how many total ways are there of reaching A to B? It can go like this, or it can go like this, or it can go like this. So there are a lot of ways clearly. How do we calculate? And why is this thing here with the rest of our slides? We were just talking about the arrangements, but this seems to be a very different problem, right? Or is it? So if you think closely, how do we calculate this? This is a small grid. Maybe we can count all possible ways in some order. But what if it were a very large grid? What would we do then? So if we think about it, in order to reach from A to B, it has to follow the shortest path, which means it cannot take such a path where it goes here and then back and then here and then here, something like this. Now this is taking extra steps, right? Because it went forward and then it went back and then it's going forward again. Took extra steps. It has to go 1, 2, 3, 4. 4 squares right and 1, 2, 2 squares down. It has to go that much, right? Otherwise it cannot reach B. But anything more than that will not be the shortest possible path. So for example, if you check any of these orange paths, it's taking 4 rights and 2 downs, right? For example, if we say this, 1 right, 1 down, 2 right, 2 down, 3 right, 4 right, right? So 4 rights and 2 downs it has to take. But in case of the red route, it's going 1 down, 2 down, 3, 1 right, 2 right, and then 1 up, an extra step, 1 left, and then 1 up, and then 2 right and 1 down, and 1 right, 1 down, clearly much more than just 6 steps. So that is what we mean by shortest possible path, that they should not, if once they have gone forward, once the insect has gone forward, you don't want the insect to go back, it will take a longer path. Okay, so is that clear? What we mean by shortest path, what do we have to do? We have to take 4 rights and 2 downs, right? 4 rights and 2 downs. Once we do this in any order, whether it's, for example, this first one that we just saw, it was right, then down, then right, then down, then right, right. So we arranged 4 rights and 2 downs like this. Or let's say this second, the topmost path, in that case we are doing 1 right, 2 right, 3 right, 4 right. So right, 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 and then 1 down, 2 down. So down, down. So that means now it must be clear. All we have to do is arrange these 4 R's and 2 D's in any order. As long as it's doing 4 R's and 2 D's, it's going to reach B, which means we have to arrange these 6 digits, 6 letters, 6 directions, 6 steps, whatever you want to see this as, but basically these 6 letters R and D, where 4 of them are of one kind, 2 of them are of one kind. So this comes out to be 6 into 5 into 4 factorial divided by 4 factorial into 2. 4 factorial gets cancelled and we get cancelled 2 as well. So we are left with 15. So 15 possible ways of going from A to B as long as it's taking the shortest possible path. Okay. So with this we are done with today's class. I hope now you are clear with arrangements. Just practice as many as you can. How many ways of arranging? Try to come up with questions on your own. It's definitely going to help you. And I will see you in the next class with another advanced topic. Alright? Okay, can you explain? I see some doubts. So, if condition is not allowed, does that mean like it doesn't have to take shortest possible path? If it can take any path, then you want to find the number of ways? Okay, if that is your question, I am not sure. Okay, so if that is your, okay, yes, that is your question. So that means I will just erase this. Now, very good. If you're asking, ki, ma'am, what if the insect did not have to take shortest possible path, then how many ways of reaching B? It can go from here to here to here to here to here, or it can go from here and then back here and then here. Does that give you a hint? That means no matter how many ways we count from A to B, it can always come back to A and then another way will be added to the list, right? So it can come back to any square and then it will act as a new path. So that means there are infinite ways of going from A to B if it can just keep going back and forth, back and forth. What ifs as simple as it started from here and went here and then back here and then went here and back here and back here. So it can do this infinite number of times and then for the last one it will reach B. So it can do this 2 times or 3 times or 4 times, any number of times. So that means there are infinite ways of reaching from A to B if it can take as long a path as it can. So that is why infinite number of ways, that is why we had to mention that the insect has to take shortest possible path. Alright? It's 2 downs or 3 downs. Actually, 1 down will bring it to this square, another down will bring it to this square. This is why we have 2 downs. And 1 right will take it to second square, 2 rights to third square, 3 rights to fourth square and 4 rights to fifth square. So it's going from position 1, 1 to 5, 3 or rather 3, 5. So it's going from 1, 1 to 3, 5. That means what is the difference? 2 down and 5 minus 1, 4 right. Okay, right? So I hope by now you are comfortable with the counting principle. When do you add, when do you multiply, and what is permutation? How do you find the number of arrangements possible when different scenarios are given to you, right? So today we are going to do something that is just as important, something that gets you started, part of PNC, We have done the P part of PNC. Now it's time for the C part, combination. So good afternoon, students. Good evening, whatever you prefer. Without wasting any more time, let's get started. Okay, and yes, I did remember to bring you some practice questions for homework as well as a JEE level question at the end of this class. So yes, we are going to study basics of PNC, the C part today, and after that we are going to solve a JEE level question as well as I will give you some practice questions just so that you are ready for applying all of these things in advanced questions. Alright, let's start. So students, I hope you remember what permutation was. Permutations is number of arrangements, number of ways you can arrange R objects out of the given N objects. Okay, we are taking R out of N and we are arranging them. But here we are just selecting. So combinations is only selecting R objects out of the N available objects. We are given N objects and we just have to take R objects out of this. The order doesn't matter. So it's important to understand the distinction. Let's look at an example. We have a group of 3 boys. Let's say boy 1, boy 2, boy 3. We have a group of 3 boys, and the first way that we already studied was number of ways 2 boys out of these 3 can be arranged, which means maybe something like this, that there are 2 seats and we want to arrange 2 of these 3 boys in these 2 seats. So the order here matters. It can be the first boy can be in the leftmost position, or it can be B2 and something, or B3 and something. What will be that something? It can either be B2 or B1, B3. Similarly, B2, B1, B2, B3, or with B3, it can either be B1 or B2. So like this, we get 6 possible arrangements, which is what we learned yesterday, right? 3p2, which is 3 factorial by 3 minus 2 factorial. So 3 factorial by 1 factorial, which is 6. Holds true. Now, the second part is the different problem now that we have is now we just need to select 2 boys. Let's say we want to form a team of 2 boys out of these 3. Now the order doesn't matter. It's a group, it's a team of 2 boys, right? The order doesn't matter. We are just taking 2 boys. Doesn't matter who comes first, who comes second. They're both together at the same level. So now how many ways are there? We can either select B1 and B2, or we can select B2 and B3, or we can select B3 and B1, right? No other possible combination of 2 boys, because if you're selecting 2 boys, that means we're leaving out 1. We can either leave out 3rd boy, or we can leave out 1st boy, or we can leave out 2nd boy, nothing else. So that means there are 3 ways of selecting 2 boys out of a group of 3 boys. So what is happening here? What's the difference? It's just that the order here does not matter. In this case, in our previous case, when we selected B1 and B2, we were either placing B1, B2 in this order or the opposite order, B2 and B1, right? Similarly, for B2 and B3, we were either placing B2 first or B3 first. Similarly for B3 and B1. So we were counting each of these cases how many times? 2 times, right? Why 2 times? Because there are 2 ways of arranging B1 and B2. Where does this 2 come from? Because there are how many ways of arranging R objects? R factorial. So in this case, R is 2. So we have to arrange 2 boys. R boys, or in this case 2 boys. So there are two ways of arranging each of this combination, which is why all these combinations were occurring 2 times or r factorial times, which means the total number of selections will be NPR by r factorial. In this case, it will be 3P2, which is all the possible arrangements, but we were counting each selection r factorial times or 2 times. So it becomes, we know 3P2 is 6 divided by 2, so 3. Right? So that means we know how to get to permutations, right? We fill the first place, we have n options, then n minus 1. So we know what NPR is. Here, just like P was the symbol here we use the symbol C. So now NCR, number of ways of selecting R objects out of N objects, is NPR by R factorial, because in case of arrangements we are taking all of these NCR selections R factorial times. We are counting them again and again in all possible orders, but now since order doesn't matter, so we'll divide this by R factorial. So I hope bache, this is clear to you. You don't learn this very often, you just memorize the formulas, and probably after using you might forget where these formulas were coming from, but it's very important to understand every single thing, why we are doing what we are doing. Okay. No, it's not recorded. My favorite teacher, my mom. Will I cover combinatorics at RMO level theory or just JE level? No. We are going to do entire Olympiad syllabus. We are not going to just stop at JE level, but JE level is the beginning of the syllabus. So this part might seem common, but we are going to the Olympiad level, because as the thumbnail says, as the video title says, it's IOQM level. So we need to learn more concepts other than the JE syllabus, like pigeonhole and beggar problem and other things. So yes, we will be covering entire syllabus, but we have to start with the basics, right? So it's also useful for JE for sure. The basics are I think the last couple of lectures will be the additional syllabus, but the other syllabus is common in both, because if you haven't got the idea by now, all the problems that we do in PNC, they are just based on common sense. We just have to consider all the cases smartly, of course, but it's basically understanding logically how do we count all the cases, right? It's all about counting. So that is why the syllabus might vary, but it's definitely something that everyone can understand and apply in their difficult problems. Anyway, let's continue. This is a very beginner level class, students. So because we are just introducing combinations, NCR is just introduced, so of course we can't just move up to high level problems. We have to take it one step at a time. That's the normal course for any kind of student. Even if you're the smartest student out there, even then you have to learn step by step. So this is third class, the third step out of 12 steps. So yes, it's going to go one level up with each class, but right now I would say it's a beginner level class. All right, let's continue now. So that's what we got. NCR is equal to NPR by R factorial, or NPR is equal to NCR into R factorial. So that means we can find the formula for NCR directly, because NPR is n factorial by n minus R factorial, and we divide this by R factorial, so we multiply the denominator with R factorial. So this is the formula of NCR. We take factorial of the total n objects, so n factorial, all the arrangements, and divide this by the ones that were taken and the ones that were not taken. So R were taken and the remaining n minus R were not taken, so R factorial and n minus R factorial. Alright, now let's take a look at an example. In how many ways can a team of 4 boys and 4 girls be selected? We need to form a team of 4 boys and 4 girls. So total 8 students, exactly 4 boys, exactly 4 girls out of 6 boys and 5 girls. So now we know we only have a group of 6 boys. We have to select 4 boys, exactly 4 boys out of these 6, which means we have to select 4 out of 6, 6C4. Similarly, we have to select 4 girls out of 5, so 5C4. And it's an AND situation. We have to select 4 boys and we have to select 4 girls, so we multiply these. And this is our answer. 6 factorial by n minus r, 2 factorial r, 4 factorial, multiplied by 5 factorial by 1 factorial and 4 factorial. So it's an easy way of doing this is we just expand it up to the bigger factorial number. So here in this case it's 4, so we will write 6 into 5 into 4 factorial is left as it is so that it gets cancelled. Divided by 2 factorial we know is 2, multiplied by 4 factorial, and then here again 5 multiplied by 4 factorial divided by 4 factorial because 1 factorial is 1. Simple calculations. So this becomes 6 multiplied by 5, 30 by 2, 15 and 5. So 75. I just showed you the entire calculation process so that for once and for all you know how to calculate NCR in the most efficient way. So whichever bigger number is there, either r or n minus r, you expand n factorial up to that factorial and then you expand the rest normally. Perfect. Easy question. Now let's take a look here. In how many ways can a team of 4 boys and 4 girls can be selected out of 6 boys and 5 girls just like before? But now we have another condition. If a particular boy and a particular girl refuse to work together, which means let's say we had 6 boys B1 to B6 and we had 5 girls G1 to G5. So we had these 11 students. Now one particular boy can be anything but it's fixed. Let's say it was B1 and one particular girl G1. They do not want to work together. So we can either, when we form the team of 8 students, we can either select B1 but then we can't select G1, or we can select G1 but we can't select B1, or we don't select either of them. That is also fine. The only condition is they both should not be there in the team. So, bache, there are 2 ways of solving this. One is the lengthier way. We make all the cases. Only B1, only G1, neither B1 nor G1. So we count each of these. There are different cases, or this or this or this. So we add up the number that comes out of each of them. Okay, so this is one method. Let's just quickly look at it, how we can do it just for practice. So if we want B1 to be there but G1 to not be there, which means B1 is here and now we need 3 boys and 4 girls. But how many boys do we have to choose from? We have already chosen B1. The remaining 5 we can choose any 3 out of these 5. So that means 5C3 multiplied by, now we cannot choose G1. So out of these 5 we can only select out of 4. How many do we have to select? 4. So 4C4. And this becomes, if you calculate, but NCN is, you can verify it's always 1. Logically even, that's obvious, right? How many ways of selecting 4 girls out of 4 girls is there? 1. So 5C3 is 10 into 1, 1, 10. Similarly G1. Now we have selected G1. That means we need 3 girls and 4 boys. So G1 is already selected. We have 4 remaining girls. We have to select 3. So 4C3 multiplied by, out of 6 we cannot choose B1. So out of 5 we have to pick 4. So 5C4, which means 4C3 is 4, 5C4 is 5. So 20. And now neither B1 nor G1. Now we need 4 boys out of 5 remaining, 4 girls out of 4 remaining. So 5C4 into 4C4, which is 5. So 20 plus 10, 35. So the answer is 35. But this was clearly a long way to go, especially if there were more cases. Then we would have to select all of them, evaluate all of them. There's another way of looking at it, the opposite way. When this case, that needs to be true. In this case, B1 and G1 cannot be together. What if its opposite was true? What if they were together? We just exclude those cases. So we just have to, we have to count which option has less number of cases. This has 3 number of cases versus when B1 and G1 are together, that is just 1 case. So we will only evaluate 1 case, which means when B1 and G1 are together. So now in that case we have to select 3 boys out of 5 and 3 girls out of 4. So that means 5C3 multiplied by 4C3. So this is 10 multiplied by 4, which is 40. Now out of total 75 cases, that total 75 ways of forming the team, 40 ways are there in which B1 and G1 are together. So we will exclude those 40 and the remaining 75 minus 40 is equal to 35. This is our answer. So we get the same answer. If you do it the correct way, you will get the same answer, but it's always better, of course, to do it the faster way. So just check which cases, which option has less number of cases. Maybe the opposite had more cases and evaluating it directly was faster. So you just have to check which option, which method has more number of cases, which option has less, and which option will save you, which method will save you time and calculations. Alright, now let's take a look at this problem. A debate club consists of 6 girls and 4 boys. A team of 4 members. Out of these 10 students, we have to form a team of 4 members, as well as we have to select a captain out of those 4 members. Okay, so we have to select 4 students out of these 10 and we have to choose a captain out of them as well. Now there's a condition. If the team has to include at most 1 boy, then the number of ways of selecting the team is what? Try solving it. Bache, I usually teach in Hindi, but this is especially a course which is purely in English for all those students who are not comfortable with Hindi. So yes, I will bring another course, and there are already other courses running that are in English or Hindi, depending on what you prefer. But right now this course is specifically for English speaking audience. So I'm sorry if you're not comfortable with English, don't worry. We'll bring another course for you if you are more comfortable with Hindi. Okay, but now this one is purely in English. As you can see in the title, it is an English course. So this is purely for those students who are not comfortable with Hindi. Alright. Okay, 1260. 1260 is not even in the option. I see option A380, which is correct. Let's see how. So now, if the team has to include at most 1 boy, that means we have two options. Case 1, 0 boy. Case 2, 1 boy. So out of 4 members, either we can have 0 boys or 1 boy, but not more than 1, right? So at most that means this is also allowed, this is also allowed. So in this case we have 4 girls, in this case we have 3 girls, right? So let's see, let's first form a team. We'll choose the captain later, but let's form a team. Now we cannot select any boys, so that means we have to select 4 girls out of the 6 girls. So 6C4, which is 6 multiplied by 5 divided by 2, 15. In this case, we have to select 1 boy out of 4. So 4C1 multiplied by, we have to select 3 girls, so 6C3. This becomes 4 multiplied by 6 into 5 into 4 by 6. So 4 into 20, 80. So total 95 teams can be formed. But we are counting, let's say there were in first case G1, G2, G5, G6. We formed this team. Now this is one team, but we are counting this method. Like for example, let's see the captain was, let's say the captain was G1. Then this is one way of forming the team. If the captain was G2, then it is another way of forming the team because the captain has changed. So that is a new method, a new way of forming the team, right? Similarly for G5 and G6. So for every team, we have 4C1. We have to pick one captain. So 4C1 ways of choosing the captain. That means for every team, there are 4 ways of forming that team, depending on who is the captain. So we will multiply this entire thing by 4 and that comes out to be 380. Okay. Now, a box contains 2 white colored balls, 3 black colored balls and 4 red colored balls. In how many ways can 3 balls be drawn from the box? Again, there's a condition. If at least one black ball is to be included in the draw. An important thing to note here is, are those 2 white colored balls identical or they are different? Do we treat them as the same? It doesn't matter which out of those 2 we chose, or it matters. So in this case, they are distinct, which means we have 2 options of choosing a white colored ball. So again, at least one black ball needs to be drawn. That means either one black ball and then for the other 2 we have either white or white red or red, right? So if we have chosen one black ball, then we have to choose 2 balls. Can be any colors, but we have to choose 2 balls out of the remaining 6. Then the case where we choose 2 black balls and then we have to choose 1 ball out of the remaining 6, or we choose all 3 black balls. So there are these 3 cases, because at least one black ball when we are choosing 3 balls. We can evaluate these 3, but the opposite seems smaller, faster, shorter, because we will just count all possible ways and then exclude when not even one black ball is chosen. That means 0 black ball is chosen. So total number of ways is, we have in total 2 plus 3, 5 plus 4, 9. 9 balls. We can choose any 3. So 9C3. And choosing 0 black ball, that means we have to pick all 3 using those 6 balls. So 6C3. So we will just subtract these two. We will exclude these cases, these number of ways of choosing the 3 balls when 0 black ball was chosen. That is the case. We don't want to count. The others are fine, right? So this comes out to be 9 into 8 into 7 by 6 minus 6 into 5 into 4 by 6. So this becomes 4, 3, 12 into 7, 84 and minus 20, 64. Correct? Now, if you want to confirm, you can confirm. We should get the same answer. How will we get? So we have to choose one black ball. That means out of 3 we will choose 1, and then we have to choose 2 out of the remaining 6. Similarly, we choose 2 out of 3 black balls and then 1 out of remaining 6 and then 3C3. And we add these up and we should get the same answer, 64. So this comes out to be 3 multiplied by 6 into 5 by 2, 15. That is 45. Here we have 3 multiplied by 6, that is 18. And here we have 1. So 46 plus 18, that is 64. So you can choose any method as long as you're counting all the cases, you're excluding all the right cases, it's correct. If you think of all the possible cases, then you can choose any method, you will get the right answer. Just make sure in PNC problems, the only tricky part is to make sure that you're not missing any case, you're not counting any case repeatedly. You're counting every case exactly once, not skipping it, not repeating it. Okay? So yeah, 64 is the right answer. What if distinct part was not there? What if they were identical? Very good question. What if these 2 white balls, in that case, they were identical, which means we have WW, then black, 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 and then red, 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 red. So this is the contents of our box. Now we have to choose 3 balls out of this. Now we have to count the number of ways we can count. So total number of ways. Let's first see total number of ways in which we can have our selection. That means we can either have all B's or So that means we are taking and arranging, not even arranging, we are selecting out of these 3. So what are all options do we have? 0 black ball, that is, or let's just take the case where we have to take at least 1 black ball. So 1 black ball, then we counted there are 3 possible ways of forming this, right? So we select 1 black and then either WW or WR, because we're selecting, it doesn't matter the order is RW or WR, we're selecting 1 black, 1 white, 1 red, and RR. When we have chosen 2 black balls, then we have 1 white or 1 red, or we choose all 3. So these are all the possible ways we can form this. Now because they are identical, that doesn't mean, so that means there is exactly 1 way of forming this, one of this. So total 1, 2, 3, 4, 5, 6. 6 ways of selecting 3 balls out of these 9. If white balls are identical, black balls are identical, and red balls are identical. So in that case, we just have to count the number of ways we can form it, because there's no distinction. When there was distinction, that is when we gave this 3 options, that out of those 3 it can be any of them, but now it doesn't matter. So now we're not going to give it 3 options. Now there's only 1 option for this to be black. and these are exactly one option. So total 6. Clear? What if white are identical, black and red are not? I'm sure you can do it. Just treat all the whites as the same. There are no other ways of forming this. If we chose one white, then there is only one way of choosing the white out of these two. But if they were different, there are two ways of choosing one white. So similarly for black and red, you can, I'm sure, count. It's a good exercise. That's a very interesting question. So if some of them are identical and some of them are distinct, what will happen in that case? After the class, you should try. It will help you learn all possible ways of solving such questions. Okay, let's move forward. Now, let's see in geometry how we can use this, something that doesn't seem like a PNC problem or a combination problem, but actually happens to be. So lines L1 and L2 are parallel. We have one L1, one L2. Okay, they both are parallel. 3 points are taken on L1. P1, P2, P3. And 4 points are taken on L2. So Q1, Q2, Q3 and Q4. Okay. Now, how many new straight lines? New, not L1 or L2. So, other than these two lines, how many new straight lines can we draw passing through these points? They are 3 distinct points on L1, 4 distinct points on L2. Now, so total we have 7 points. If we just selected any 2 points, then see, first of all, is it possible to have any 3 points collinear? No, because if we are taking 3 points, 2 of them should be on the same line, and either if we are taking 1 from here and 2 from here, or 1 from here and 1 from here. Basically, what I'm saying is, if we select 1 point out of these 3 and 1 point out of these 4. So if I select 1 from here, 1 from here, and I join it. Let's say I took 2 and 3. So I just join this. Now for every such case, when we are selecting a new point from L1 and a new point from L2, then we are forming a new line. It will not be the same line. Can it ever be the same line? Can P3 and Q2 be the same line as, let's say, P2 or P4, Q4, or P1 and Q1? No, because they are different points. This P1 cannot lie on this, because P1 already lies on L1. If it also lies on this L3, that means P1 and P3 are the same thing, because they both lie on both of these lines and they only intersect at one point. So it's only possible to have one intersecting point. That means if P1 is different, it cannot lie on this line. I hope this was clear to everyone. It's very important to understand. We're not missing anything. We're not counting anything again. Yeah. So if we select 1 out of this and 1 out of this, then we will form a line. So how many ways of selecting 1 from here and 1 from here? 3C1 into 4C1, 12. If we had just taken any 2 points out of these 7, then we would form a line, yes, but a lot of them would be L1 and a lot of them would be L2. So that is why 7C2 is 7 into 6 by 2, that is 21. So out of this, only 12 lines are new, 9 would again be L1. Do you want to confirm? We should be able to confirm. If both the points were from L1, then we would get L1, right? So how many will be L1? 3C2, which is 3. How many would be L2? If we selected 2 points out of those 4. So 4C2, which is 4 into 3 by 2, that is 6. So total 3 plus 6 lines will be the same as the old ones, either L1 or L2, and the remaining 12 will be the new lines. Now of course, you should not calculate first total number of lines and then how many will be L1, how many will be L2. You would get the same answer, but that's such a tedious and long way of getting there, right? We just have to get 1 point from each line and that will form a new line. Okay? Now, we have a chessboard, an 8 cross 8 chessboard, the standard chessboard, right? Count the number of rectangles in a chessboard. For example, this is a rectangle. This is also a rectangle. Even this small square is also a rectangle. So how many ways of forming a rectangle in this chessboard are there? Option B, yes, that is correct. So let's see how. We see in such questions, it's not about how we can apply NC2 or any other permutation or combination. It's about how we can efficiently count the number of cases without repeating and without skipping, right? Now, in case of a rectangle, let's say we're talking about this rectangle. For any rectangle, there will be a start point and an end point. As soon as we fix the start point and the end point, then the remaining rectangle can be completed. For example, if I choose this as my start point and this as my end point, then I just have to complete the rectangle and I will get my rectangle. As soon as I have two distinct points, that means, oh, option A was correct. I'm sorry, I think I did not see the problem, the options actually, but yeah. So as soon as I have 2 points, then I will have all the rectangles. That means if this point is x1, y1, where this length is x1 and this is, let's say, y1. For example, if this is 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have 0 to 8, total 9 possibilities for x1 and 9 possibilities for x2. Then if we choose x1 and x2 out of these 9, we will have the breadth of the rectangle, right? If we choose this x1 and x2, we have the breadth. That means we have to select 9C2 to find the breadth. Now we need length. For a given breadth, there can be any sized rectangle depending on the length. So now we have to choose any 2 out of these 9 points. Let's say any 2 out of these 9. These are also 0, 1, 2, 3, 4, 5, 6, 7, 8. Out of these 9, we can select any 2 and we will again form a rectangle. So for example, if I had selected, let's say 2 and 7 and I selected 3 and 5. That means I will go to 2, 3. So 3, 5 is my length of the rectangle. Now it can be anywhere. The breadth is 2 to 7. So from 3 to 5 and 2 to 7, this would be the rectangle. So as soon as I select 2 out of these and 2 out of these, I will get a unique rectangle. It's very important. The unique part is very important. I'm taking my time explaining this question. I know you have already understood. If we just multiply 9C2 for length and 9C2 for breadth, then we have the answer. Option A is correct. But it's very important to understand why are we sure that this is giving us all unique rectangles. We're not repeating any, because that happens most often. Whenever you're counting such cases, you might end up counting some of the rectangles again. We have to be very careful. As soon as I fix 2 out of these and 2 out of these, then it will get me a unique rectangle. So yes, squares are also rectangles. This includes all possible rectangles, including the ones where, let's say, if I had selected 2 and 4, 3 and 5. So in that case, my rectangle would have been this, which is a square, or even the smallest 1 unit squares are also rectangles. So if I had selected 7 and 8 and 0 and 1, then I would get this square or this rectangle. So yes, we are counting all of them, which means 9C2 into 9C2 is going to give us all possible rectangles. Now, so yes, squares are also rectangles, but how many of them were squares? Out of these 9C2 whole square, some of them were rectangles which had different length and breadth. But what about the squares? What about number of squares? That means the length and breadth have to be equal. A little tricky? Let's see. Now we are going to see it case by case, how we can form a square, how we can form a unique square, how do we count all of them. Now let's fix the length of the square. What is the smallest length possible? 1. Let's call this length 1 unit. Then length will go from 1 to maximum is the entire chessboard. So 1, 2, 3, 8 cross 8. So 1 to 8. So length can go from 1 to 8, right? For each length, let's say we start with 1. How many, if we fix the top left point of the square, then we'll get a unique square. We know the length and we know the top left point. So for here we have this point. Let's say I fix this point and I fix the length as 1. Then I will get this square, right? So that means if I fix this 1 point and this length, then I will get a unique square. Similarly, if I had say length equal to 3 and I fix the top left point, so I fix this point and I need length equal to 3, then this is my unique square. Nothing else is possible because length is unique and length is unique, top left point is unique. No square will be repeated. It's impossible to repeat any square, and I will count all of them, right? Because I'm counting all possible squares of all possible lengths. Now, how do we find the number of squares for each length? Let's say the length was 1. In that case, how many top left points can I choose? This is going from 0, 1, 2, 3, 4, 5, 6, 7, 8 points. I cannot choose this line, right? I cannot choose a point on this line because if this is the top left point, then I cannot form a square, right? So it has to be up until 7. Similarly, I cannot choose this line. This 8th line I cannot choose, because again, if this is the top left point, then how can I form a square? So I will have to select out of these 8 lines, and out of these 8 lines, accordingly, I will get a point. So that means for length 1, I get 8 square. Now for length 2, let's say length is 2. Okay, then in that case, my last square will be this. If I had selected this point, then I could not form a square of length 2. So now I have to stop at this 7th line. We started from 0. Bacha, you have to be careful. If it confuses you, you can start from 1, 2, 3, 4, 5, 6, 7, 8, 9. So now out of these 7 lines, we can choose up to 7, and similarly here up to 7. So for length 2, we get 7 square. Similarly, we are going 1, we are decreasing it by 1. If it's length 3, then up to 6 square. So for each length, we get, for length 1, 8 square, length 2, 7 square, length 3, 6 square, and likewise for length 8. How many options do I have of selecting the top left point? Only 1. So it will go up to 1 square. So for each of these lengths, we are doing n minus 8 minus that length and its square. So for length 1, it's actually 9 minus L square, or similarly 1 square plus 2 square up to 8 square. So which is nothing but option B. So as we go from length 1 to length 8, we will go from 8 square to 1 square, which is the same as what's written here. We have just summed up all the squares from 1 to 8. And we know what this is. I hope you all know. Sigma r square, r goes from 1 to n, is n plus 1 to n plus 1 by 6. So in this case, it's going from 1 to 8. So we are just going to substitute 8 here. So 8 multiplied by 9 multiplied by 17 by 6. And that gives us 12 multiplied by 17. That is 204. Alright. So again, very important to understand how we are counting, how we are making sure that all of the squares are counted, and however we are picking our square, it's a unique way of finding the square. We're not repeating any square. Okay. If there is still some confusion, if you still want to think more about it, feel free to do so. It will only help you, but after the class. Now, let n greater than equal to 2 be an integer. N is an integer. N distinct points on a circle. We have n distinct points on a circle. So there is a circle and we have n different points. It doesn't even have to be a regular polygon or anything like that, equally spaced. No, they are just randomly placed n points, n different points on a circle. Now we are joining each pair of points by a line segment. The line segment joining every pair of adjacent points is blue and the others are red. So which ones are blue? The adjacent point, the line segment joining the adjacent points. But if it's not adjacent, for example here they are not adjacent, so this is red. Any of these are red, but all of these are blue. So whenever we choose a line segment, we are basically choosing two different points. As soon as we take 2 points out of these n, we have a new line segment, right? If we take this and this, we have a new line segment. If we take this and this, we have a new line segment. This and this, we have a new line segment, right? So how many total line segments we'll get? NC2. Now out of these, how many of them are blue? If we fix 1 point, then we get 1 to its right, right? If we count 2 line segments per n point, then we are counting this line segment, every line segment 2 times, right? So, but if we do something like this, if we are counting it like as soon as we fix a point, we get 1 line segment to its right, and we do this for every point. If we fix this, we get this line segment. We fix this, we get this line segment. Similarly, all the way, if we choose this point, we get this line segment. So we take, in general, it's very helpful to remember, bache, in a circle only go in one order, otherwise you'll end up repeating. Only go maybe clockwise or anti-clockwise, just choose one order of counting to make sure that you're not double counting anything. Alright, so as soon as we fix a point, we're getting 1 line segment to its right. That means how many total line segments? N. Right? You can also see this as this will make a n-sided polygon. If we join all the adjacent vertices, so n-sided polygon, that means n line segments because n sides are there in the polygon. Anyway, the question says if the number of red and blue line segments are equal, then what is the value of n? Red will be the remaining, which is NC2 minus n. The question says that this blue and red, these two numbers are equal. Let's solve it. NC2 minus n is equal to n. That means NC2 is equal to 2n. Let's expand NC2. N factorial by n minus 2 factorial and 2 factorial is equal to 2n. And we can write this as n minus 1 and then n minus 2 factorial divided by n minus 2 factorial, and 2 factorial is 2. So n minus 2 factorial gets cancelled, and because n is greater than or equal to 2, that means we can cancel n from both sides. But when n can be 0, then you can't just cancel it. But here n cannot be 0, so we can cancel n. So what do we have? N minus 1 is equal to, we take 2 here, so n minus 1 equal to 2 or n equal to 5. So I can see a lot of you got it. Amazing. So this is how we first had to calculate the number of blue line segments, the number of red line segments, and then it was purely mathematical, just doing operations on NCR. Okay, now as promised, a JEE main level question, because we're just on 3rd class. Of course, we cannot really be solving JEE advanced level questions just yet. We can, but it might be a little too high for this class. So in the following classes, there will be Olympiad PYQs and JEE mains and JEE advanced PYQs every now and then. But for now, let's take a look at this problem that you can do if you just know how to count all the cases perfectly. So let's take a look at the question. The number of 4-digit numbers that are strictly greater than 4321 using the digits 0, 1, 2, 3, 4, 5. So we have 6 possible digits that are with us, but we need to form a number that is greater than 4321. So how many ways of forming such a number are there? We'll count the cases in an increasing order. Just like how we were doing alphabetically, the same way we are going to do it for these digits. But before we do, I want you to give it a shot. Just quickly try and see if you can get the answer. So yes, 310 is correct. Good job. Let's see how. We will go in the ascending order as I just said. So 4, 3, 2, 1. We need a number bigger than this. Let's start from the last digit. Now we need, let's fix 432 and consider all the numbers that are going to be, all the digits that are going to be greater than 1. All the numbers that we can form by just replacing this digit. So how many options do we have for this digit? 2, 3, 4 or 5. It cannot be 1, it cannot be 0 because they will not be strictly greater than 4, 3, 2, 1. So 4 numbers. Then we move on to the next digit. Now we have fixed 4 and 3, but we have these two options. Now if we fill this with anything greater than 2, because we have considered equal to 2, we cannot go less than 2. So we have to move on to the next digit, that is 3 or 4 or 5. That means 3 options for this digit, and then as soon as we fix 3 or 4 or 5, if this digit can be anything, it will always be greater than 4, 3, 2, 1 because 4, 3, 3 something will always be greater, right? So then there are 6 options. All 6 digits are an option for this digit. So this means 18 such numbers can be formed. Now, next digit. We fixed 4 and these 3 digits can be anything. So now we have to go above 3 because we have considered all the numbers until 43 something. So now this can be, again, repetition is allowed. You had to be very careful with that, okay? Because repetition is allowed, that is why we chose 6. Otherwise, we would have selected out of the remaining numbers, right? So there are 4 options. There is only an option of 4 or 5. That means 2 options for this digit. And the remaining, again, just like before, can be anything. So 6 multiplied by 6, which is 72. Now, the last option, when this is not 4, we have to go above 4. The only option is 5. So we fix 5 in the leftmost digit, and then the remaining can be anything. It will always be greater than 4, 3, 2, 1. So 6 into 6 into 6, which is 216. So 216 plus 94, that is 310. So most of the, I would say, medium level problems just want to test that if you can count all the unique cases correctly. If you go in an order so that you don't miss anything and you don't repeat anything, then you will get the right answer. Okay, and we will not have a class tomorrow. We will have the next class day after tomorrow. So for that time, you can practice these questions. You can pause the video if you need these questions. The answers are here so that you can verify your answers. These are roughly simple questions just for your practice, just so that you are very comfortable with what we have learned so far. You're able to apply all of it in the problems and you are ready to take it up a level. So in today's lesson, we are going to do a certain kind of problems where we are either taking a situation where we have to keep certain objects together, or certain objects, as the title says, bundle and gap. Bundle stands for when certain objects have to stay together, or gap when there has to be a gap between certain objects. Those objects can never be together. If you remember from our previous class, we did consider one of those cases when one particular boy and one particular girl could never be together. There always had to be, in a way, a gap between them. So now, in case we have to arrange those students where we have to keep certain students together, or we have to maintain a gap between certain students, they can never stand next to each other. So for example, such cases can be handled using bundle method or gap method. It's very easy, very logical. We'll just understand how to go through those scenarios, how to make sure we're counting all the cases, excluding all the right cases, and you're going to find that kind of questions very easy by the end of this lesson. Alright. So first of all, we're going to start with bundle method. Bundle, as I mentioned, certain objects have to stay together. Let's take a look at this example. A library has 3 mathematics, 2 physics and 5 chemistry books, which are to be arranged on a shelf. In how many ways these can be arranged such that all books of same subject are together? These 3 stay together, these 2 stay together and these 5 stay together. Now, we have 2 options. Either these books are identical. For example, they are all NCERTs. We just have 3 different copies of maths NCERTs, 2 different copies of physics NCERTs, 5 copies of chemistry NCERTs, but they are same book. In which case, it won't matter what order these books are in. It's the same situation. But the second case, they are distinct. Books of same subject are also distinct. That means we have 5 different kind of chemistry books, 3 different kinds of maths books, in which case the order is going to matter, right? So let's take a look at this one by one. One thing that stays common, the bundle, we have to form the bundle. Let's see. So the first case, when books of same subject are identical, that means we have 3 maths books, 2 physics books and 5 chemistry books. Now these 3 have to stay together. That means this is one bundle. These 2 have to stay together, this is one bundle, and these 5 have to stay together, so this is one bundle. In total, we have 3 bundles with us. Now the order can be this M bundle, this P bundle, this C bundle. The order can be PMC, MPC, MCP and so on. Because they are identical, it doesn't matter how we are arranging these 3 maths books as long as the bundle is together, because the books of same subject have to stay together. So we just have to arrange these 3 bundles, which means 3 factorial. So as soon as we find one arrangement of M, P and C, we know what order these books are in, because the M represents the M bundle, P represents the P bundle, C represents the C bundle, or I like to call it, instead of bundle, unit. So this is one unit, this is one unit, this is one unit. Now we have to arrange 3 different units. But in the other case, when the books are distinct, now this is M1, M2, M3. This is the M unit or M bundle. Then there was P1, P2, the P bundle, and C1, C2, C3, C4, C5, the C bundle. Now just like before, we have to arrange these bundles, yes. So 3 factorial. But as soon as we arrange the bundle, that does not guarantee that we have a unique arrangement, because within the bundle, this M1, M2, M3 can be arranged in 3 factorial ways. Within this bundle, P1, P2 can be arranged in 2 factorial ways, and C1, C2, C3, C4, C5, these can be arranged in 5 factorial ways. So for each of these arrangements, we will have this many arrangements for each of these. So 3 factorial multiplied by the number of arrangements possible within each bundle or unit. So this will be the final answer. So just to reiterate, what we did was, whenever we have to make sure that certain things are always together, we keep them together. Now you are together, you act as one unit. Now we arrange this one unit along with the other objects, and if within that unit there can be multiple arrangements, we multiply the total number of arrangements with that smaller number of arrangements which can happen within the unit. Okay, let's take a look at another example. If now earlier all these books of same subject had to be together, like M books had to be together, P books had to be together and C books had to be together. Now we only have the condition that mathematics books are together. The rest can be anywhere. We just care about mathematics books. They should be together. All three of them should be together. So now we only have one maths unit and two separate physics units, because each unit for its own. They can be together, they can be separate, they can be arranged in any way. And similarly 5 different chemistry books. So now we have M1, M2, M3 and then P1, P2, C1, C2 like this. This is one unit. So how many total things to arrange, total objects to arrange? This one unit and 1, 2, 3, 4, 5, 6, 7. So 2 plus 5, 7 plus 1, 8. So now we have to arrange these 8 factorial objects. But in the first case, books of same subject are identical. In that case, books of same subject are identical, which means, if you remember from the permutation lecture, P1 and P2 are identical. We have 2 identical P's and 5 identical C's. So divided by 2 factorial, 5 factorial. Right? Because P1, P2 are identical, so we just divided by 2 factorial and 5 factorial. Now if books of same subject are distinct, then we arrange these 8 units, 8 factorial, and now we also have to arrange within the unit. So multiplied by 3 factorial. Simply, logically, this is how you handle such problems. Okay, so students are giving the answers. If you want, yes, you can calculate. So this comes out to be 876 by 2. I cancelled 5 factorial. So that becomes 21 into 8, 168. And here, a big number. So 8 factorial would be, I know until 6 factorial, 720. So 8 into 7 into 720 into 3, a big number, as I said. So yes, okay, why did we multiply with 3 factorial? But just like before, we arranged all these 1, 2, 3, 4, 5, 6, 7 and this one unit 8. But that doesn't guarantee that we get all the arrangements. We can also have M2, M1, M3, M3, M1, M2. So for each of those arrangements within the unit, we can have 6 arrangements for every arrangement of these 8 things. The only thing that changes in such problems is we treat this as one new object, and then we just make sure that within this one new object, can there be multiple arrangements? If yes, then we multiply that 3 factorial. If not, then we just don't multiply anything. That is one object, just like before. So here the M books were identical. That means only one arrangement is possible, M, M, M. There is no M1, M2, M3. All 3 are identical. So we did not have to multiply with anything. This one object is just one object. Okay. Let's take a look at more problems. You will get more clarity. Okay. So now we have a word imagination, and we need to arrange the letters of this word, and we have 4 problems related to it. So first of all, if you remember from the previous class, what is the first step of such problems? We count all the number of letters in this. Okay. So we have I, then M, then A, G, then I, then N, A, T, then I, then O and N. Just to get the right count of letters. So if we had to arrange all the letters of this, just see how many permutations are possible. We'll just count them all. 3 plus 1, 4 plus 2, 6 plus 1, 7 plus 2, 9 plus 1 plus 1, 11. So 11 factorial divided by, these are tally marks bache, in case someone is getting confused, this is not 11, this is 2. Okay, I was just using tally marks to count the number of letters, the number of appearances of each letter. Okay, so 11 factorial divided by 3 for I, then 2 for A and 2 for N. Okay, so these are the total number of arrangements that we can have for these letters. Now let's take a look at the special cases that needs to be handled. Now our first condition is both A's are together. We have two A's, they have to be together. The rest can be in any form, but these two A's belong together, which means now instead of two A's, we have one unit AA. Because two A's are identical, there's no difference between the first A and the second A, then we don't need to arrange within this unit, but now this acts as one unit. Earlier we were arranging 11 things, now we will arrange 10 things. Instead of two A's, we have one AA unit. So we will arrange 10 things, and now how many repetitions do we have? Now this is one unit. There are not two different A's, so we will not divide 2 factorial for this. This is just one unit, it acts as one object. The rest we have 3 factorial for I's and 2 factorial for N's. Okay. Next problem. Both A's, both N's and all 3 I's are together. That means these 3 I's are also one unit now, and these 2 N's are also one unit now. They all don't have to be together, just I's have to be together with each other, A's have to be with each other, N's have to be with each other. Now how many units do we have in total? How many objects do we have to arrange? 1, instead of 3 we have 1, plus 1, 2, plus 1, 3, plus 1, 4, plus 1, 5, plus 6, plus 7. So now we only have 7 objects to arrange. Okay, so now we have 7 objects to arrange, and because there are no repetitions left, that is it. Is that clear to everyone? Now let's take a look at the next condition. Now we are saying all vowels have to be together. Now, okay, there's a bit of chaos there, so let's write them again. Except this time we put the vowels in one unit. So what all vowels do we have? We have 3 I's. Now they are not saying that the 3 I's have to be together. I's can be arranged in any way as long as it's next to a vowel. Okay. So 3 I's. Then we have 2 A's and 1 O. So in total we have 6 vowels and the remaining consonants M, G, N, N and T. So now how many things to arrange? 1 unit plus 2 plus 3 plus 4 plus 5 plus 6. 6 objects to arrange. So 6 factorial. Now we were arranging these 6 objects, but there is a repetition. 2 objects are of the same kind. The rest are different, but 2 objects are of the same kind. So we will divide this by 2 factorial. And we have to check within this unit, can there be multiple arrangements? Certainly can. How many? 6 factorial divided by 3 for I's, 2 for A's, and this is your final answer. It is not a recorded lecture. What reply? What do you want to ask? Yes. So Karthik, your answer is correct. Yes. Yeah, a lot of you are giving correct answers. That is correct. Clear to everyone? If you have any doubts, that's the whole point of a live lecture, a live class. If you have any doubts, if you have a problem understanding any part of it, feel free to ask. Why did we divide with 2 factorial? But just see, now, okay, for those students who have a problem understanding this, let's look at it this way. I call this unit, this object, my unit vowel. Okay, what other objects do I have to arrange? One of M, one of G, one of N, another one of N, and another one of T. Right? So 1, 2, 3, 4, 5, 6, I have to arrange these 6 objects. So 6 factorial. But 2 of them are identical. We remember from our permutation lecture that whenever we have a repetition, we have to divide it by the number of repetitions there are, right? So because the n is appearing twice, we have to divide it by 2 factorial. If you still have some doubts, bacha, I recommend that you re-watch the permutation lecture. You keep revising this. If this is all very new to you, you might be forgetting some topics. It's okay. Just revise the old topics before coming to the new class. Okay. So that is why we arrange this. But this one unit is not unique. It can be I, A, 0, or O can be here, or I's can be separated. It has multiple possibilities. How do we calculate the number of possibilities? 6 factorial by the I's were repeated 3 times. By 3 factorial, A's are repeated 2 times. So 2 factorial as well. And this is how we get the answer. Very logically, step by step, make sure you're considering all cases. That is all PNC is about. Combinatorics is about counting all the cases. Okay, now let's take a look at the last problem. All vowels are together and all consonants are together. Now, how is it different from our previous case? From our previous case, these vowels had to be together, but it could be between the consonants as well. The consonants could have been separated. But we also want the consonants to be together, which means we have our old unit I, A's, O, and we have another unit because consonants have to be together. So M, G, N, and T. Now we have 2 units. So 2 factorial. Within first unit, how many arrangements can be there? 6 factorial by 3 factorial, 2 factorial. Within the second unit, 5 factorial by 2 factorial. And this is how we calculate the number of cases. It's a tough question. It's okay. It's not tough. Trust me. It's not tough. It's just new. Okay, there's a difference between new and tough. It might be new. It might not be as obvious as our old lectures. As I mentioned, it is only going to get harder and harder. That means you have to revise before coming to the class. You have to revise. If you're not 100% confident on your old concepts, then understanding a new concept will seem very difficult. But if we take it one step at a time, making sure the old steps are perfect, then the new step becomes very easy. It's okay. Take your time, revise, understand at your own pace, but make sure you understand. So, just to repeat the last one, all vowels have to be together, which means there has to be a unit, a bundle of vowels. All consonants are together, there has to be a bundle or a unit of consonants. So how many objects to arrange now? Only 2 units. So 2 factorial. Now within first unit, we get 6 factorial by 3 factorial, 2 factorial. And here we get 5 factorial by 2 factorial. That is the number of arrangements within the second unit. Okay. Now, gap method. This is to count the number of cases when we have to keep certain objects apart. Up until now, we were keeping certain objects together. We were bundling them together. Now we have to put a gap between those objects. Let's look at an example. Just like before, we have 3 maths, 2 physics, 5 chemistry books. Now the condition is maths books are separate. All these 3 books, no 2 of them should be together. There has to be a gap between the maths books. So if we have something like, we arrange this. Let's say this is an arrangement of the rest of the books. Now, the maths books cannot be together, which means there has to be at least one of these books between the maths books, right? We cannot have MM like this here, because in that case, we will have the maths books together. We don't want that, which means there has to be at least one of these between 2 maths books. Now it can be multiple of these between 2 maths books, that is also allowed, right? Or maths book can be here, that is also fine. Just that 2 books should not be together, 2 books should not go into the gaps between these books. So what are we going to do? First, we are going to find the arrangement for the rest of the things. What are the rest of the things? 2 physics and 5 chemistry. Let's look at the first case. Same subject books are identical. Okay, so no P1, P2, PP, CCC. Okay, so that means how many arrangements can we have? 7 factorial divided by 2 factorial, 5 factorial. Right? Now, once we have an arrangement of P books and C books, we have to find some places to keep our M books. Where can these M books go? They can only go in the gaps between these. Now, how many gaps do we have? It can also be here or here, between the gaps, like this. So, how many of them are there? 8. One more than the objects that we had already placed, right? Because after every object that we had placed, there is one space and there's also one in the beginning. So however you want to count, just one more than the objects we had already placed. In this case, we had placed 7 objects, so this becomes 8 gaps. Out of these 8, we have to pick 3, any 3. As soon as we pick 3 out of these 8 gaps, we have found our positions for the M books. And because we are only placing M books in different gaps, that means they are not together. So this is the gap method. We arrange the rest of the things first, and then whichever objects need to be separate, we fill them between the gaps to make sure that they go in separate gaps. There is at least one other object between 2 of maths books. Okay, so this is how you get your 7 factorial by 2 factorial, 5 factorial into 8C3, the number of arrangements such that, first of all, maths books are identical to each other, physics books are identical to each other, chemistry books are identical to each other. In addition, no 2 maths books are together. All of the maths books are placed separately. Okay, now let's take a look at the other case when same subject books are distinct, which means now we have P1, P2, C1, C2 and so on. So now, just like before, we are going to find an arrangement for the rest of the objects. In this case, because they are all unique, we just have to do a 7 factorial. No repetition, so no dividing by 2 factorial, 5 factorial. Okay. Now we have to place our maths books between these gaps, right? So out of these 8, we select 3. Additional thing now is, let's say I picked this, this and this. Let's say these are the 3 I selected. Now that doesn't mean that we are done here. Within these 3 gaps, there could also be another order when we just shuffle these like this. Now this is another unique arrangement because maths books are distinct. So within these 3 gaps, we have to arrange these 3 maths books, because there will be, once we have selected the gaps, we can still get 6 different arrangements. We have finalized the position of physics and chemistry books. We have finalized where maths books are going to go, and still we can arrange maths books within those gaps, right? Out of those 3, the first one could be M1, then M2, then M3, or it can be M2, M1, M3, M3, M1, M2, like that. We can have 3 factorial arrangements for the maths books. So that is why we have to multiply the entire thing with 3 factorial. Yes, if you are able to follow along the entire course, if you are practicing, if you are understanding everything, if you are able to use your mind, you're not just listening, you're understanding and you're able to think on your own, then definitely you can solve any problem. Most of it, we still struggle. There can be tricky questions. Combinatorics is not an easy topic, but still, yes, you will be able to solve all the questions if you're able to understand all of it, okay, and able to think on your own. Don't just listen, think. If you want, you can pause later. Once you're revising, pause first, try to think on your own how we can count the number of cases and make sure you got the right answer, okay. And even in case of new problems, don't look at the solutions directly. First, try to think on your own, develop that thinking capability, thinking habit. That is how you make sure your brain is active all the time. Your brain is able to apply whatever it has learned onto new questions. Okay, right? So this is how we do it. Now an interesting thing, I just can't move on without addressing this. This is nothing but 7C2, right? 7 factorial by 2 factorial, 5 factorial. This is clearly 7C2. Is this a coincidence that the number of arrangements of P's and C's was 7C2, or we could have got it directly from 7C2? See, we had to arrange 2P and 5C, right? How many arrangements? We did see that we arranged all of them 7 factorial and divided by 2 factorial and 5 factorial, we get it. But is there another way of looking at it? We first fix the 1, 2, 3, 4, 5. We first fix these 5 C's, right? This is a unique thing because they are all identical. We can just arrange them in one order. Now we have to place 2 P's. Now it can be anywhere. Here, let's first place the first P, okay? P1, first we are placing. There's no difference between the first P and the second P, just we are placing the first P and then we will place the second P. Because they are identical, we do not have to order them, okay? So we can place them here or here or here, anywhere, right? The P has to go in one of these 6 spaces, correct? Now, what about the other one? Where can it go? Either it can go okay. I hope you all are listening and not just talking in the chat. Okay. For all the students who are asking for guidance, by the way, We will have a separate session. We will have separate videos for that. This is a purely academic class. I know you want guidance. You are still somewhat struggling how to go about this journey, how to find the right path. I know that from time to time you need those guidance from your mentors, and we will have separate sessions for that, but right now we're just studying. Okay, you are listening? So I want you to reply as well, right? First we place the P out of these 6, right? Now where can the second P go? We will not count this and this separately, right? So P can either come here before all the C's, maybe the P is already there, or it can come here. Now let's say if P wasn't here, if we had placed the first P here, even in that case we won't count this one and this one separately, right? Because if we place the P here or here, it doesn't matter. There will be 2 P's between 2 C's and 3 C's. So it doesn't matter, we cannot treat them as a different thing. They are the same. So that means the second P also has 6 options, no matter where we place the P. Does that mean we have 36 cases? Does that mean we can have 36 possible arrangements? We earlier counted 7 factorial by 2 factorial, 5 factorial. How much is that? 7 into 6 into 5 factorial by 2 into 5 factorial. So this comes out to be 21. Here we are saying we have 36. Did we miss some cases there? Did we count some extra here? I want you all to actually think about it and reply to me now. So for all those who weren't listening, who weren't paying attention, or who missed it somehow, what we did in this case, earlier we had counted that we can just arrange these 7 2P's and 5 C's in this way, 7 factorial, and then because there were 2 repetitions for P and 5 for C. So we do 7 factorial by 2 factorial, 5 factorial, right? Now we are saying that we have 5 C's. So we put 5 C's. They will be there, right? Now both P's can be here or here or here, or they can be separate. We don't know. We have to count all the cases. So we first see where the first P can go. It can go either here or here or here, between the gaps, right? It has to go somewhere, right? Let's say we only had 5 C's and 1 P. In this case, even if we went by that logic, 6 factorial by 5 factorial for the 5 repetitions, that means 6. And even if we go by this method, we get 6 places to place our first P. Now what about the second P? I am saying the second P also has the same option, the same number of options. Right? If I had placed the second P here, then the first P here, then second P also has these 6 options. What am I counting extra in this? That seems correct, right? That seems like, yeah, that makes sense. We counted the number of permutations. We know that is the correct formula. We derived this formula the other day. We know that is the correct answer. Why are we getting 36 here? What is the extra that we are counting? Come on, think. I want some of you to answer. I'll answer. If you guys don't, I will tell you what is the extra. But yeah, whoever got it, yes, tell me. Which cases is, like, for example, just 2 cases, which will be counted multiple times or twice. Yes, that is correct. No, I get it. What some students are saying is, I just want you to answer this one problem. I will tell you what we are counting multiple times. We are counting this P as my first P, and let's say I place the second one here. Now what if I had placed the first one here and the second one here? Because there is no difference between the two, then that means these are being counted twice. These are the cases that are being repeated. So bache, this is what I'm trying to tell you. In combinatorics, it might seem like you're going the right way, but you have to be very careful that, are you sure you're not repeating any case? So yes, you guys are suggesting right, that what we can do is, we treat them as 2 separate P's. In which case, now there are 2 possibilities even here. Even when we have placed P1 here, then one can be before P1 or after P1, right? So we do that. We arrange, how many places will we have? Because we've already placed 6 things, we get 1 extra space. So 7 things now. We had already placed first P in 6 ways. Now we are finding 7 spaces for the second P. But they are not actually different. We treated them as 1 and 2, and we thought that their order matters. But the order doesn't matter, so we will divide it by 2 factorial. So this is the same. Yes. Now, why could we not divide this by 2? Why could we not just divide this by 2? Because we had not taken all of them. The total cases were 42. We had not taken all of them because we did not count these 2 as separate. Here we treated them as identical P's, but when we did not, so basically when we are placing them together, they are identical, but when we are placing them separately, then we counted those cases twice. So we had to actually check how many cases are there when the 2 of them are together, how many cases are there when the 2 of them are separate. The separate ones are being counted twice, so we'll just remove those. So in total, 6 ways of placing them together, right? If PP are together, then there are 6 spaces for P and P together, and the remaining 30 ways of being separate. So we only divide these by 2. So then we get 6 plus 15 equal to 21. So I'm just saying that whichever method you take, as long as you're being careful, you're removing all the repeated cases, you're counting all the missed cases, in that way you will get the same answer. The answer cannot be different. But why was it 7C2? Is that a coincidence? This is what I'm asking. Okay. Go home and think about it. We'll definitely answer this in the next class. I want you to expand your brain. Think about it on your own. I know you can reach the answer. We will think about it, okay? and we will discuss this in the next class. I want all of you to come prepared with this. Why? How is it 7C2? How can we reach this? How are we, what is it that we are selecting 2 out of total available 7, or maybe 5 out of total available 7? Okay? Do think about it. Trust me, if you just keep hearing the solutions, it will definitely not help you as much as when you think of the solutions on your own, when you think of such things on your own, when you think of different methods of approaching the same problem on your own. Here we discussed 3 different ways of reaching the same answer, right? So just like that, I want all of you to think about this additional method. Anyway, continuing. So coming back about the gap thing. Whenever things have to be separate, we will first place the things that don't matter. They can be anywhere. So we place the P's and the C's, and then the N's had to be separate. So we have to fill them between the gaps. Okay. Now, coming back to our imagination word, both A's are separate now. If you guys need this, we'll do this again. But because I remember from the last time, and I'm sure you do too, to some extent, we have 3 I's, 2 A's, 2 N's, and the rest were 1 E, G, M, T, O. 1 each. Right? So 3 plus 4, 7 plus 4, 11. We have total 11 letters. This is what the count was for the word. Now, we need the condition when both A's are separate. Both A's are separate. Again, the total number of permutations for imagination will be 11 factorial by 3 factorial, 2 factorial, 2 factorial. These are the total number of words possible. Out of these, how many are there when both A's are separate? So we arrange the rest of them. Remove the 2, arrange the rest. 9 factorial divided by 3 factorial. I's are identical. And N's are identical. Now we have arranged the 9 things, right? Now we have arranged 9 things. That means we have 1 extra gap, 10 gaps. Out of those 10, we have to place the 2 A's. So we have to select 2 A's. Because the 2 A's are identical, we do not have to arrange the A's between the gaps. So this is our final answer. Right? Everyone gets this? Now, no 2 I's are together. No 2 I's are together. That means all 3 I's are separate. What do we do then? Achha, before we move on, both A's can either be separate or can be together. There's no other option, right? The 2 A's can either have some letters between them or they will not have any letters between them. We had earlier counted when both A's were together. This was the total number of cases possible. Out of the total, these many were when both A's are together. Once we have this, we can just count the number of cases remaining, which will be the cases when both A's are separate. Let's take a look. 10, 3, 2. Let's just do this in the corner. Make sure that this is actually the same. So we are subtracting from our total number of words the number of cases when both A's were together, which was 10 factorial by 3 factorial, 2 factorial. Again, we are looking at multiple ways of solving a problem. The more chapters you will, the more topics you will learn in this chapter, the more number of ways are there to solve a problem, as long as you are not counting any case again, you're not missing any case. Then you will get the same answer. It's very important to understand all of those methods so that in the exam, whichever method comes to you first, you are able to use it to get the right answer. Anyway, coming back here. Now just some manipulations here. We take this common, So what is left in the first one? 11. And here we have taken this common, so the denominator becomes this. In order to make it this, we multiply 2 factorial with the numerator and denominator. So 11 minus 2. So this is 9 factorial by 3 factorial, 2 factorial into, I took 10 out, so remaining 9 factorial, and then 10 and 9 from here, and this remaining 2. So this is the same as this, 9 factorial by 3 factorial, 2 factorial, and then 10 into 9 by 2 is nothing but 10c2, right? If you multiply this by 8 factorial with in the numerator and denominator, we get 10c2. So that is why both ways are correct. If we had already calculated this and this, then you should not have to calculate this again, you can just subtract. But if this were an independent question, if you see just this problem, then this is the quicker way of finding this, because otherwise you will have to calculate multiple things. Now coming back, let's take a look at when no two i's are together. Now we cannot use the same method. We did see, okay, we did not see, but doesn't matter. Let's say we had seen when all i's are together. In that case, if we just subtract those cases when all i's are together, do we get the case when no two i's are together? No, because there's a third case possible when two of the i's are together and one is separate, right? So how many cases do we have with the i's? Because there are 3 i's, either all of them are together or 2 of them are together and there are some letters between them and then the third I, or all 3 of them are separate. So now we can't just subtract total number of cases when the 3 i's are together from the total number of words possible, because this is also there. We want to calculate this case when the 3 i's are separate. So we'll use the gap method directly now, just like before. We arrange the remaining 4 plus 2 plus 2, 8. So 8 factorial divided by any repetitions? Yes. 2 factorial, 2 factorial. And then we have to place the 3 i's. We have arranged 8. So we have 9 gaps. So 9C3. And this is your answer. Okay. Now, the next condition is all vowels and consonants are alternate. How many vowels do we have? 3 plus 2 plus 1, 6 vowels and 5 consonants, right? So that means in the 11 letters, we need to have vowel, consonant, no other way, right? Because they have to be alternate. So it will start with a vowel, then consonant, then vowel, then consonant, and like this. So 5 consonants and 6 vowels. 2, 3, 4, 5, 6. Something like this. Correct? Now, bache, just for future reference, this is a different number of consonants and vowels here, right? We have 6, we have more vowels, less consonants. If they were equal, then we could not say that it will start with a vowel. Then it could also start with a consonant. But in this case, if it started with a consonant, we will have 2 vowels remaining at the end. So it has to start with a vowel. When one thing is extra, then it will start with that. But if both are equal, then we have to consider both the cases. We will do a 2 factorial to count all of them. Okay. Now coming back here, we have 6 vowels, right? 6 positions. We know vowels have to go here. So if we just arrange the vowels in the order, then we get one particular arrangement of vowels. That means we get V1, V2, V3 and we place them here. Similarly, for the remaining consonants, we just have to arrange them in these 5 spaces. So we arrange the the vowels 6 factorial by 3 factorial and 2 factorial, and then O is unique. And we arrange the consonants 5 factorial divided by, there's a repetition here as well, and just like that we can solve such a problem. Okay, but if this weren't true, if there were, let's say, 5 vowels and 5 consonants, then we would multiply this with a 2 factorial to count the number of cases when it starts with a consonant instead of a vowel. Clear? Okay, now last one. 2 eyes are together but separated from third eye. That means this case, when these two eyes are together but this eye is separate. Now it's using bundle method to make sure 2 of them are together and the gap method to make sure the third eye is separate. So what we are going to do is, we are going to split the 3 eyes into 2 units, 2 bundles. One is I1 which has 1 eye and one is I2 which has 2 eyes. Okay, these are now different. I1 is different from I2. They are 2 eyes is different from 1 eye, right? So that means now we have to arrange how many units? 2 from here and the remaining 8 from here. So now we have to arrange 10 objects. How many repetitions are there? I'm sorry. Yeah. No, we can't just do that, because we have to keep these separate as well. So what we are going to do? We are going to arrange the remaining. I'm so sorry, Vijay. We are going to arrange the remaining. That means we have to arrange 4 plus 4, 8. We will arrange these 8 factorial by 2 factorial, 2 factorial, just like before. But now instead of choosing 3 from the remaining 9 gaps, we choose 2 from the 9 gaps to place I1 and I2. But now the order matters. If you remember the M1, M2, when they were distinct books, when the order mattered, we had to arrange those M's in those gaps. So we will multiply this 2 factorial to arrange I1 and I2. The I2 could be first or I1 can be first. Okay, so just like this case, we first arrange the remaining 8 objects, the remaining 8 letters, and then instead of finding 3 spaces, we find 2 spaces, because 1 unit is there and 1 unit is this. So we select 2 spaces and then the order can be different. It may I1 first and then I2, or I2 on the left, I1 after that. So 2 factorial. Okay. Yeah. Now, in how many ways 5 boys and 3 girls stand in a queue such that no 2 girls are together? That means all girls are separate. This is a gap method problem. So we arrange the remaining 5 boys, 5 factorial, and out of those 6 gaps, we have arranged 5 boys, so 1 extra, 6 gaps. From those 6, we find 3 for these 3 girls, and then we have to arrange these 3 girls, so 3 factorial. Okay, directly applying this, not repeating this. Now, by now you are very clear on the theory. Let's look at the second case, when exactly 2 girls are together. Just like the eyes, G1, G2 is 1 unit, G3 is 1 unit. Also, G2, G3 can be 1 unit and G1 can be another unit, or G1, G3 can be 1 unit and G2 can be another unit. So in total, how many ways can we do this? To select 2 girls, the 2 girls which are going to be together, 3C2, right? Out of 3, we have to select 2. So there are 3 ways of choosing 2 girls out of that. So first we form the unit. Okay. Now that we have the unit, in this case, again, it can be G1, G2 or G2, G1, G3, G2, like this. So within the unit, there can be 2 factorial arrangements. Now we have the unit. Okay. Now let's arrange these. 2 girls are together, the third is separate, so the gap method is there, which means First we arrange the boys, and out of those 6 gaps we choose 2. Instead of 3 now we choose 2, just like before, because 1 gap is for this unit, 1 gap is for the remaining girl, to make sure that these 2 units are placed separately. They are never together. So we place them in the gaps. So 6C2. But because these units are not identical, they are different. So another 2 factorial to arrange these 2 units. Alright. So this is the final answer. Just make sure you're counting every case and keep multiplying, because for each of these 6C2, there will be 2 possible arrangements, the unit first and then the independent girl, or the independent girl on the left and then the unit together. Alright, so this is how we can calculate. Now let's move on to our last problem. I want you to try this first. I'm going to give you some time and then we're going to discuss the solution. So it's based on everything we've done so far. N be the number of ways in which 5 girls and 5 boys can stand in a queue in such a way that all the girls stand consecutively. All the girls are together. That means there is one bundle containing all the girls and the boys can be anywhere. That is N. M is the number of ways in which they can stand in a queue in such a way that exactly 4 girls can stand consecutively. 4 are bundled up together, 1 is separate. There has to be a gap between this and this, otherwise 5 girls will end up standing next to each other. We want exactly 4 and then a boy and then a girl, or 1 girl and then at least 1 boy and then the 4 ones. Okay, so that is M. So we have to form, we have to tell what M by N is. So first of all, what is N? Easier? Just tell me in the answers quickly. Even in factorial terms, because we anyway have to divide it, so it's okay when it gets cancelled. You don't have to calculate exactly, just in the factorial terms. We have arranged, we have bundled the 5 girls together. Now how many arrangements do we have? 5 boys plus 1 bundle of girls. So 6 factorial, right? But within that bundle, within that unit, girls can have different arrangements. So into 5 factorial. That is N. Right? Did everyone get this answer? That is very sweet, bache. I hope you're not compromising your other classes, but I'm glad that you're liking this class and you're prioritizing this class. Anyway, did you get this answer? Good. So, now time for counting M. Just like the eyes thing, the girls think, exactly the same way we are forming the bundle. So firstly, we have to form the group of 4 girls. We have to select which 4 girls are standing together, right? And then rearrange them. So these are all our units. Once we have our unit, then we have to first arrange the boys. So we arrange them, 5 factorial. Now out of the 6 gaps, because we've arranged the boys, out of the 6 gaps, we have to select 2 gaps to fill 1 unit of 4 girls and the 5th remaining girl. So 6C2. And then because the unit and the independent girl are distinct, we have to arrange them as well. And this is our M. Correct? 5 into 4 fact factorial into 5 factorial, 62 into 2 factorial. Perfect. Very good, bache. So now we just have to calculate m by n. So we divide this entire thing by 6 factorial and 5 factorial. Right? So 5 factorial gets cancelled. And we can write 6 factorial as 6 into 5 into 4 factorial. Correct? 4 factorial gets cancelled. Then 5c4 is nothing but 5. 5 by 4 factorial into 1 factorial. So this is 5. So we cancel this with this 5. Now what is remaining? 6c2. In the numerator, what is remaining? 6c2, that is 6 into 5 by 2 into 2 factorial into 2. Even that gets cancelled. Divided by what's in the denominator? Only 6. So what's left? 5. I hope everyone got this answer. Yes? So it's just as important to be careful with your calculations, especially with factorial and combination operator, because I know this is also very new to you. So even if you got this answer, it's also important to get to this answer. To get these calculations right, just with practice, you'll get the hang of it. You'll be very, very comfortable with it. This is not very difficult, right? This is the easiest part. Coming up with this whole thing was the hardest part, and I know you all can do it. So just make sure you revise all of what we did today. It's all very logical. Do not try to memorize any of it. Just try to understand. Combinatorics cannot be memorized. Combinatorics is just something that you have to understand logically, and it will be very easy for you to come up with the answer for any problem if you understand it completely. Okay? So I will see you in the next class. Make sure everything that we have covered so far, it's been very basic, I know, but you are able to solve any of those problems so that in the next class, whenever we are applying any of the old things, you're not struggling with that. Today we are going to do two important topics, very important, but again, we are going to understand how we actually calculate. We're not going to memorize any formulas. But this is one thing you have to remember. Do not try to memorize formulas when it comes to combinatorics, because there are always exceptions. So always understand where these formulas are coming from. And yes, if it's a very standard problem, then you can apply your formula, but you should be able to solve any special kind of problems, as we'll see today. So, all right. Let's start without wasting any further time. Yes? So the first topic for today is circular permutations. So far we have been arranging the objects in a somewhat linear manner, right? We were arranging books. The books were supposed to be one after another in sort of a linear manner. Either students were queuing up, or we were arranging books on a shelf, or what else did we do? We were picking some options, but now we are going to see how we can arrange certain objects around a circular thing, either a table or a round necklace, and how do we actually take care of all cases. Maybe there are certain repetitions, so how do we make sure that we are not counting any case more than once? Okay, let's start. Okay. There are a lot of doubts going on in the chat, which are kind of not relevant, so I don't want to get into any prep related doubts. I know you always are wondering. So if you are, but just for short, if you are worried how to manage school as well as Olympiad, as you get closer to your Olympiad or your exam, whichever exam you're preparing for, you should focus more on that exam. But on a regular basis, maybe you should maintain a balance. But if you are sure that your Olympiad, your exam is more important, is the main goal, your school exams can, you can get maybe 90% in school exams and that is fine. You do not need 95%, 96%. Then you can ignore your school classes somewhat if you have to focus more on your, let's say, Olympiad. But at the same time, make sure you're not compromising your entire school education, because it is not just about maths. Even though yes, I love maths, I know you all are enjoying maths as well, but it is not the only thing you need to learn in life. So there should be a balance, but maybe let's say 60-40. Okay, I will get more into how to actually manage in big detail, how to manage Olympiad versus school, how to manage boards versus JEE, all of those things. I have been getting into it in different videos, but if you want, I can make a special video for that. But for now, let's start. Okay. Hello, hi, all the students who are just joining. Good afternoon. So circular permutations. Circular permutations, the first problem is when anti-clockwise and clockwise are different things. You can ignore this for now. We will see when are they the same thing. Clockwise and anti-clockwise, they're always different, right? We'll see when it is actually the same. But for now, let's take a look at this kind of a problem when we are, let's say, there is a circular table and we have a certain number of people and we want to seat them around this table. Now, why is it different? If let's say we number our seats, just like in this figure, in this diagram, we have 5 people that need to sit around the table and there are 5 seats. Okay, so if we number these seats, that this is seat 1, this is always seat 1, this is seat 2, this is seat 3, seat 4 and seat 5. Okay, we have numbered these. Now they are fixed seats. So if A sits here, B sits here, C, D and E. These 5 people are sitting around the table in this order, versus if let's say we make them shift by 1 seat. Everyone shifts by 1 seat. So now A is sitting here, B is sitting here, C, D and E. Like this, everyone shifted by 1 seat. Now this is different. This is not the same as before because we numbered the seats, right? Earlier A was sitting on the first seat. Now E is sitting on the first seat. Clearly they are different. But in most cases, when there is a round table, we don't number the seats, right? It can be in any order. We don't number. So when the seats are not numbered, in that case, both of these cases are the same, because let's say I was A, earlier B was on my right, E was on my left, and then after B there was C, after E there was D, right? Even if everyone shifted by 1 position, the arrangement is still the same. B is still on my right, E is still on my left, after B there's C, after E there's D. We just shifted the entire table, we just rotated the entire table, but the arrangement is the same, which is why we study circular permutations separately. Okay, so earlier if we started with A and ended up with E, versus if we started with E and ended up with D. For example, A, B, C, D, E versus E, A, B, C, D. When we were arranging them linearly, they were different cases, but now they are the same because they are connected, and then this becomes the same case. That is all you need to understand, bache. First of all, this should be clear why this is not the same as linear permutation. In case of linear permutation, we had a simple 5 factorial. There are 5 factorial ways of arranging these 5 people, but now these two are the same, which means we are counting certain cases more than once. The answer is less than 5 factorial, right? Now, how many times are we counting these? we start with A in the same order, then we get A, B, C, D, E. If we start with E in the same order, it's the same. Or if we started with B, B, C, D, E, A, then again it's the same arrangement. So we can start with any of these 5, but as soon as we fix the first one, then the arrangement is the same, right? The rest of the arrangement is fixed, which means there are 5 repetitions for each case. So we divide our 5 factorial by 5 because we are counting each circular permutation 5 times, right? Like this with E, or if we started with B, then after that, after B comes C, then D, then E, then A. Or if we started with C, D, E, A, B, or with D, E, A, B, C. All these 5 arrangements are identical because once you place these arrangements around the table, they will end up being the same. Okay? So, yes, you can do 5 factorial by 5, which means 4 factorial, right? So, the number of people minus 1, 5 minus 1 factorial. Another way of looking at this is, if we fix the first one, okay, we can fix anyone, it doesn't matter. We fix one person on one seat. Now the rest of the order will be different. For example, let's see if we just had 3 people, okay, we only have 3 people here, A, B and C, and we have to seat them around the circular table, around the round table. Now let's say we fix A. Now either A can have B on its right, on their right, and C on their left, or the other way around, B on my right and C on my left. So there are 2 possible arrangements. Now where is this 2 coming from? Because B and C can be arranged in 2 different ways, 2 factorial ways, right? So that means once we fix one person, the rest remaining n minus 1 people, they can be arranged in n minus 1 factorial just like before, but now it is not cyclic. We cannot say that if we had A fixed here, okay, let's see, for 4 people, we have A and then B, C, D. So if we have B, C, D, now if we make all of them shift by 1 position, that means B comes here, C comes here and D comes here. Within B, C, D, it's the same arrangement, right? But now with respect to A, because A is also sitting here, we cannot ignore A, then it is a different arrangement. Because A was earlier between B and D, now A is between C and D. Which is why we can just find the number of permutations, the number of arrangements, the number of ways of arranging the remaining people, and with that we will get all the possible cases. Alright. So n minus 1 factorial. Now once we fix A, there were 2 ways, either B on my left, C on my right, or B on my right, C on my left. But if everyone rotates in such a way that now B is sitting here, C is here, everyone, let's say, moves 1 position left. So B goes here, A comes here, C goes here. We can see that these 2 are the same arrangements. So that is the whole point of circular permutation, that once you rotate the entire table, if you get the same arrangement, that means we should count them as one single case and not 2 separate cases. As long as the seats are not numbered, the seats are identical. If there is a difference in the seats, maybe one is the boss's seat, maybe one is for different position, then we will have to be very careful. So it's important to not just memorize the formula, understand where it's coming from. Alright. So for linear, we had 3 factorial. For circular, we now have, we fix one person and we arrange the remaining persons around that one person. So 3 minus 1 the remaining 2, 2 factorial. So any form of, we understood this same formula in two different ways, either n factorial by n, or directly we fix one person and arrange the remaining n minus 1 people. Whichever way you feel more easy to understand, whichever way you feel is easier to understand, you should go with that. But I would actually prefer if you understand both of these perfectly, because the more you understand, the more you are able to apply any kind of solution on any kind of problem. Now, the other case that we were talking about, the clockwise and anti-clockwise usually are different, right? But when are they same? When we can lift our circle and flip it. Let's see how. We have, let's say, a necklace. Okay, we can lift this circle. Earlier, we cannot lift the table and turn it around, right? People cannot be upside down. But in case of a necklace, let's say we have 3 beads around a necklace. Okay, so we arrange them in this way, A and then C and then B. And now I picked this necklace up and flipped it. Once I flipped it, B is now on this side, C is now on that side, which means every case we count, its mirror image should be the same. As soon as we flip it, it should be the same, which means we are counting every case twice. So all we are going to do is, we count the number of arrangements. In this case, 3 beads. So 3 minus 1 factorial, 2 factorial, and then we divide it by 2. So the general formula comes out to be, if we have n beads, n different beads, then n minus 1 factorial and then divided by 2, because we are counting every case twice. Because in case of a necklace, this form and its mirror image is the same thing. Right? Now, let's look at some applications of this theory. Very easy. Once, if clockwise and anti-clockwise are different, then n minus 1 factorial if the seats are identical. If clockwise and anti-clockwise is the same thing, then n minus 1 factorial by 2. Now, let's take a look here. It's a circular table, which means clockwise and anti-clockwise are different, so n minus 1 factorial kind of a thing. Now, we are going to combine this formula with our older knowledge, the bundle and gap method, right, from the last class. So, in how many ways can 5 boys and 4 girls sit on a circular table? If there is no condition, then we have 9 students sitting around a table, so 9 minus 1, 8 factorial ways of doing it. Now let's look at the conditions. No 2 girls are together. No 2 girls are together, which means the gap method. We first place the remaining people. The 5 boys, let's first make them sit around the table. So a number of ways that 5 boys can sit around a table is 5 minus 1 factorial. Okay, now the boys are seated, which means we have B1, let's say B2, B3, B4 and B5. Now we have to fill the girls between the gaps. Earlier we had 5 plus 1, 6 gaps, because 1 on the left and then 1 on the right. But here we have 1, 2, 3, 4, 5. Exactly 5 gaps. There is no left and right, because it comes to be a circle, it completes a circle, it forms a circle. So only 5 remaining gaps. In case of linear arrangement, we have 5 plus 1, 6 gaps. But in this case, we have only 5 gaps. Alright. So out of these 5 gaps, we have to select 4 gaps for these 4 girls, right? So 5C, 4. Okay, let's say we picked these 4. Now we have to also arrange the 4 girls here. Now it is not a circular arrangement, it is like linear arrangement. Why? Because the order matters. It is not the same if G1, G2, G3 and G4 are sitting like this versus if we make them shift by 1. G1, G2, G3, G4. Now these are different arrangements, even though within the girls it's the same arrangement, but earlier G1 was between B1 and B5. Now G1 is between B1 and B2. They are totally different arrangements. So now we are just going to arrange these 4 girls in 4 different places. So 4 factorial. And this is your final answer. So this is how you combine your gap method with the circular permutation. Okay. So we get 4 factorial multiplied by 5 into 4 factorial. So 4 factorial into 5 factorial. I combine these two to form 4 factorial into 5 factorial. Of course, you can calculate 24 into 120, but I'm going to stop here. What is 144? I don't think 4 factorial into 5 factorial is 144. Anyway, but if you're getting another answer, if you are confused, maybe you forgot to count something, maybe you forgot or you added something extra, maybe you counted some case more than once, make sure you check your solution what was wrong. That is the best way of learning combinatorics. Try your method, and if your answer is incorrect, make sure you check what went wrong there. That is very crucial. Alright, now let's take a look at second condition. All girls are together. Now it is the bundle method. All girls are together, which means G1, G2, G3, G4. They make a single bundle, a single unit. Then we have the 5 boys. So total number of units to arrange around the table is 5 plus 1, 6. So 6 minus 1 factorial. Right? Now that is not enough. Within this unit, there are multiple ways of arranging the girls. So then it becomes 4 factorial. We have to multiply all these arrangements by 4 factorial. Right? Because within this unit, we had this circle. Let's say we get this arrangement B1, B2, B3, B4, B5, and our 4 girls were seated here between B3 and B5. Now all the 4 factorial arrangements will be unique, right? Even if we make them like this, G2, G3, G4, G1, we make all of them shift by 1. Even in that case, these are different arrangements, because earlier G1 was adjacent to B5, now G2 is adjacent to B5. So all 4 factorials will be treated as linear arrangements. So this will be your final answer. We first arrange all the possible units, 1 unit for all the 4 girls and 5 separate units for all the 5 boys, because there is no condition on the boys. These girls can be between any of the boys, right? Now, the last case, girls G1 and G2. There are, if we numbered all the girls, then G1 and G2, they sit together but not adjacent to G3. Okay, I'm going to take it on the next slide. We have 5 boys and then G1, G2, they are sitting next to each other but not adjacent to G3, and then there is another G4. So here there needs to be a gap. What we are going to do is, we are going to first count all possible cases when G1 and G2 are together. No matter where G3 is sitting, G1 and G2 should be together. So in that case, we have 5 plus 1 plus 2. That means 8 different units to arrange around the table. So 8 minus 1 factorial. These are all the possible cases when G1 and G2 are together. Now G3 should not be adjacent to G1 and G2, which means G3 should not be adjacent. Oh, I'm sorry. That is not, we are not done here. We also have to arrange G1 and G2, right? So 2 factorial for the 2 girls within that unit. Don't forget that special thing, right? Now we have to exclude all the cases when G1, G2 unit, this one unit, that unit was adjacent to G3. Either G1 was adjacent to G3 and then G2 was basically either G2, G1, G3, something like this, that G1 was between G2 and G3 or G2 was between G1 and G3. But the main thing is G3 is adjacent to the unit of G1 and G2. Alright. So now what we are going to do is, I want all of you to listen very carefully. Now we are counting the number of cases when G1, G2, their unit, they have to be adjacent to each other. If we have something like G1, G3, G2. So we anyway did not count this case here. We only counted the cases when G1 and G2 were adjacent to each other. So we do not have to remove any such case, right? This was not counted. We only counted the cases when G1 and G2 were adjacent to each other. So in this case, G1, G2, G3, this is one unit. And then with G3, there is a second unit, a super unit. Okay. So now we form a separate unit where G1, G2, there is another unit within this unit and G3 is also there in this unit. Now how many units do we have to arrange around the table? 5 plus 1, 6 plus 1, 7. So 7 minus 1 factorial. And now within this super unit, there are 2 ways of arranging G1, G2 and G3. This unit and G3. So into 2 factorial. And within the further smaller unit, there are again 2 factorial ways, 2 ways of arranging G1 and G2. Okay. So this is how you have to be very careful while counting all the cases. And this is your final answer. 7 factorial into 2 factorial minus 6 factorial into 2 factorial into 2 factorial. We take 6 factorial into 2 factorial common. What's remaining? 7 from here and 2 from here. So 6 factorial into 2 into 5. Alright, so 7200. Is that the same answer that you all are getting? Yes. Perfect. Okay. So it's just about counting, making sure that we're not counting any case more than once, and as well as we're not missing any case. I keep repeating, that is all what combinatorics is all about. Okay. Now, coming to the other kind of problem, how many different necklaces can be made from 10 different beads such that 3 particular beads always come together? So for now, forget that clockwise and anti-clockwise are same or different. How many ways are there of arranging this? This is one bundle, right? 3 and the remaining 7. So total 7 plus 1, 8 units that we have to arrange around the circle. So 8 minus 1 factorial multiplied by 3 factorial, right? For arranging the 3 beads within the unit. Now coming back, that it's actually a necklace and not a table, which means we are counting every case twice, clockwise and anti-clockwise. So we will multiply with a half. And that is your final answer. Alright. Now, 8 people, including A and B, are to be seated around 2 identical tables. There is no difference between the 2 tables. Each of them has a capacity of 4. We have 2 tables, 1 and 2, but we are not numbering them. It doesn't matter which table is which. Okay, we just have two tables, two identical tables. Each of them have a capacity of 4. We have to find the number of arrangements such that A and B are not at the same table. A is at one table, B is at another table. It doesn't matter which one because they both are identical. Just A is, let's say A is here, B is here. We do not have to count the other case as well when B is here and A is there. Why? Because they are identical. Okay, when the tables are identical, that means there is no difference. There is no table 1, table 2. There is no left table, right table. They are just two identical tables. A is on one of them, B is on the other. Okay, so these are all the cases that we can get. Now we have to seat the remaining 6 people. What's the answer? Three 360, 1440, 720, 2880. I'll give you a little time. Okay, 720. Let's see. Now, out of the remaining 6, we have to pick 3 for the table for A, right? So, we pick 3 people for this table. Which table? There is no left table or right table, but now there is a difference between the tables. One table has A and one table has B. So, now there is a difference in the tables. So, we select 6. Out of 6, we select 3 and the remaining 3 will go there. If you want, you can check 3C3, which is nothing but 1. So, we do not really have to count this. So, we just select 3 and the remaining 3 will go there. Alright, now we have the people for each table. Now, we have to find the arrangements for each table. So, 4 here, which means 4 minus 1, 3 factorial here and 4 minus 1, 3 factorial here. So, what is the final answer? This is how we will calculate, and the final answer is 6 factorial, which is 720. So yes, bachcho, your answer was perfect. Some of them were saying 360. Okay, why are you dividing it by 2? Help. Let's clarify your doubts. Why do you think we should divide it by 2? All the students who were saying 360? If you want, please share, because I want you to learn. I want you to, maybe I'm wrong, feel free to tell me. Combinatorics is such a topic, there are so many ways of looking at it that I might miss something, you might miss something. We need to help each other out for sure. Identical tables. Yes, they were identical, but we made them separate. We did not, if we were counting them separately, that B is here and A is here, this as a separate case, then we would have to divide by 2, but we did not do that. And once we placed A on one and B on the other, now the tables are no more identical. One is the table with A and one is table with B. Okay, think about it. We're not counting any case twice. If you think we are, still feel free to tell me. But once we fixed A and B, we gave one table to A and one table to B. Now they are no more identical. They are two separate tables. One is table which has A, one is table which has B. Okay? Yes, bache who keeps asking for time for solving, I did give you time for solving. I'll wait until at least one of you gives me the answer. Okay? And if you still feel that time is not enough, you can pause the video, take your sweet time, make sure you solve it first. Of course, that is a very good way of learning. But I cannot keep waiting for everyone, each one of you to solve, right? So that is why I wait for at least a couple of you to solve it and then I start with the solution, but you can still keep going and then check your final answer. If it doesn't match, you can rewind and rewatch the solution. Alright. Now, 8 people are to be seated, the same situation as before. Now the number of arrangements in which A and B, oh my bad, now there is a difference. 4 of them are at a round table and 4 at a straight table. There is one round table and one straight table. Let's say something like this. So 4 will sit here, 4 will sit here. Number of arrangements in which A and B are not at the round table. Now they are not saying now at the same table. They are saying not at the round table. Read your questions very carefully. Okay. So now they are not at the round table, which means A and B will go here. Where we don't know, we will have to find. But A and B are not here for sure. So what do we have to do? Again, like before, we have 6 people remaining. This is very easy, which is why I'm not even giving you enough time to solve. I'm sure you got it. Okay, you want some time? Sure, go ahead. So A and B have to go here and the remaining 6 have to be arranged in between these remaining 6 spots. 2 here and 4 here. Make sure you count all the cases and tell me what is the correct option. If you don't think any 3 of them is correct, then mention option D. 2160, yes, that is correct, bache. Very good. Option D is correct. Very easy, right? So, out of the remaining 6 people, we will select 2 to sit here. And the remaining 4 will sit here. And bacha, I hope you have observed by now that 6C2 is equal to 6C4. Right? Both of them will be 6 factorial divided by 2 factorial, 4 factorial. Both of them are the same. So even if you thought of it like this, that out of 6 people, we will select 4 to sit at the round table. Remaining 2 will go to the straight table. Even that would be the same thing. We are basically just choosing 4 and the remaining 2 will go there, or 2 and the remaining 4 will go there. So it has to be the same number of options, right? So 6C2 or 6C4, both of them are correct, whichever way you want to write it. But we first selected the people, okay? Now we know which people are sitting at which table. Now we have to just arrange. So we have 4 people for here. So the number of arrangements for those 4 people is 4 minus 1, 3 factorial. And for here, we have 4 people including A and B. 2 out of the 6 and A and B. There is no other condition. So 4 factorial for these 4 people. So our final answer will be 6 into 5 into 4 factorial divided by 2 factorial 4 factorial into 3 into 2 factorial into 4 factorial. So 2 factorial 4 factorial gets cancelled and we have 6 into 5 into 4 factorial, basically 6 factorial, that is 720 into 3. So 2160, option B is correct. Okay. So just take it step by step, make sure you are counting all the arrangements and you will reach the right answer. Now, the second topic for today's class, which we just did actually, division into groups. What did we just do? We divided the remaining 6 people into groups of 3 and 3 or groups of 4 and 2, right? We were dividing them. So how many ways of doing this? We already are solving it, but let's take a look at how different cases will be different, how we can do it in a simpler way. Okay, so there is a formula, but I'm not saying that you have to rely on the formula. If it's a standard case, go with the formula. Otherwise, you should know how to do it step by step. Let's see. So, a simple case, we have 10 people and we have to form groups of 6 and 4. We are dividing these 10 people into 2 separate groups. One has 6 members, the other one has 4 members. So, if we just select 6 people out of these 10, the remaining 4 will go here and we're done. As soon as we select 6, we find the number of ways of selecting 6 people out of these 10. We will get our answer. Which reminds me of a problem from our earlier classes. I asked you to think about why it was 7C2 when we were arranging 2 P's and 5 C's. Does anyone remember? Before we start with this, I want to just discuss that. We had 2 physics books and 5 chemistry books, right? So, all possible ways of arranging these was 7 factorial divided by, these are repeated and these are repeated 5 times. So, this is nothing but 7C2. Why is it so? Why was this equal to 7C2? How can we come to this 7C2 directly? Did anyone think about it? We will get to the ordering of same size in a bit, but I want you to answer this one. Did you think about this in the last class? Yes, 7C5 and 7C2 is same, that is true, but we did not select anything. We were just arranging them, right? We were just forming the permutations. We saw that there are 7 books, so 7 factorial ways of arranging these, and these 2 are identical, so 2 factorial we divided by 2 factorial. These 5 are identical, so we divided by 5 factorial. So, where is selection coming from? We are just arranging, we are just permuting, we are just finding the number of permutations. Why this C? Where is this selection coming from? Did anyone think about this? Okay. We have to select 2 spots. Perfect. Good. So, another way of looking at this same problem is, there are these 7 spots for these 7 books. 1, 2, 3, 4, 5, 6, 7. Right? And we have to arrange these 7 books in these 7 positions. Now, if we just select 2 out of these 7, we select 2 for physics, then the remaining will go to chemistry and we find all the permutations. Or we select 5 and the 5 positions will be filled by chemistry books and the remaining 2 will be occupied by the physics books. So that is why these 2 formulas look the same, because they actually are just 2 different ways of solving the same problem. Both are correct, and clearly because both are giving the same answer. Alright, now coming back here. So as soon as we select, it doesn't matter, there is no naming the team, that this is team A, this is team B. No, we just have 2 different groups. We are dividing them into 2 groups, 6 and 4, that is the size of the groups. So as soon as we select 6 or 4, 10C6 or 10C4, same thing, right? So, bache, if you are still not familiar with this, then this is something you should remember. NCR is equal to NCN minus R. Alright? Because n factorial divided by n minus R factorial, R factorial. Both of them will be equal to that same quantity. So these are the same, which is why 6C2 is equal to 6C4, 7C2 is equal to 7C5. As soon as these 2 add up to the n, then their values will be the same. So in this case, 10C6 or 10C4 is the same thing. Okay, now 10C6, that is the total number of ways of forming the group. We can expand this and see that this is equal to 10 factorial divided by 6 factorial, 4 factorial, right? If you want to see, you can do it that out of the remaining 4, we select 4 for this. But that is anyway 1, so we ignore this. Now let's say we are forming 3 different groups, one of size 5, one of size 3, one of size 2. So first we select 5 out of these 10. Then how many do we have left? 5. Out of these 5 we select 3. So out of the remaining 5 we select 3, and then out of remaining 2 we select 2, or we can just say the remaining 2 will go here. So this is anyway 1, we can ignore this. So final answer is 10C5 into 5C3. So this is a common way, something you already know, something you can already do. That is a way of doing it. But if you look at a formula, we expand this, okay? So 10C5 is 10 factorial divided by 5 factorial, 5 factorial. And then 5C3 is 5 factorial divided by 3 factorial, 2 factorial. 5 factorial gets cancelled and it is 10 factorial divided by 5 factorial, 3 factorial, 2 factorial. So earlier we had 10 factorial divided by 6 factorial, 4 factorial. Here we have 10 factorial divided by 5 factorial, 3 factorial, 2 factorial. So if they are all distinct sizes, then the general formula, if we have m and n are different, okay? So we have m plus n objects, distinct objects, and we have to form 2 groups, one of size m, one of size n. M is not equal to n. Then m plus n factorial divided by m factorial n factorial, or we can just say m plus n cm or cn. Same thing. If it's, let's say m, one group is of size m, one is of size n, and one of size p, then it's m plus p factorial divided by m factorial n factorial p factorial. So that's a formula. You can use the formula directly, or you can do the C method. We are selecting m out of these, then n out of the remaining, and then p. So that is fine. Now, this is when the group sizes are distinct. What if the group sizes are the same? Will that affect our problem? Will that affect our solution? Will that affect the number of ways we can form the groups? Let's see. A simple case, we have 4 objects, 4 distinct objects, okay? We have 4 distinct objects, A, B, C and D. And we have to divide them into 2 groups, one of 2 and the other is also of size 2. Now, same sized group. For example, let's say we had these A, B, C, D and we select 2, 4C2, okay? Let's say we selected A and B. So, the remaining C and D go to the other group. Or let's say we selected C and D and the other 2 remaining A and B go to the other group. But we did not say that there is first group and second group. We did not say that. We just wanted to divide them into 2 groups. We did not say there is team A and team B. For example, you all are playing, alright? You all decide to play a game and you all decide that you have to split among 2 different teams. Now, it doesn't matter as long as the same exact students are in one team and the same exact students are in the other team. It doesn't matter which we selected first, right? It will still be the same division. So now these 2 cases have to be identical, which means we are counting every case twice. So we will divide it by 2 or 2 factorial. Now where is this 2 factorial? If we expand this, so the same as before, 4 factorial divided by 2 factorial, but we also divided by 2 factorial. What is this 2? Is the size of the group? No. This is the number of repetitions of the same sized group. Let's look at another example here. Let's say we have 6 objects A, B, C, D, E, F. Now same as before, we first select the first 2. Let's say I selected first A and B. The remaining C, D, E, F, out of them I select, let's say C, D. And then E, F goes to the remaining group. That is one case. But now instead, let's say instead of choosing A and B, I had picked C and D. Now remaining A, B and EF, those four, out of those four remaining, let's say I selected A and B, then EF would go here. Or let's say I had selected A and B first, but out of remaining C, D and EF, I selected EF for the second group, and then the remaining two C and D will go to the remaining group. So like this, we can have many such cases which actually happen to be the same case, right? Just like before, we are dividing the 6 objects into 3 groups of size 2. Now, whether we select AB first or CD first, it doesn't matter because we are not numbering the group. The groups are identical. It doesn't matter who was selected first. But if it mattered, let's say the first 2 were going for a quiz. The second 2 were going for a debate competition, and the remaining 2 were going for, let's say, a modeling competition, and not a fashion modeling, maybe like a science model, because just to keep it in the academic area, or anything, it can be anything. But let's say we are selecting 3 different competitions, then it matters, right? Then these are separate cases, because earlier AB was going for the quiz, but now CD is going for the quiz. But if there is no distinction between the groups, in that case, all of these are identical cases, which means we are counting the same case how many times? The number of ways of arranging these 3 groups, right? So 3 factorial. We are counting this case. We are counting every case, in fact, 3 factorial times. So we have to divide the entire answer by 3 factorial. So what was our answer? 6 factorial divided by 2 factorial, 2 factorial, 2 factorial, and we have to divide this entire thing by 3 factorial. So even in the previous case, 4 factorial by 2 factorial, 2 factorial, and we have to divide this entire thing by number of ways of arranging these 2 identical size groups. So by 2 factorial. Now let's see if we have something like this. We have 12 objects. We have to divide them like this. 2 groups of size 3, 3 groups of size 2. So basic 12 factorial by 3 factorial, 3 factorial, 2 factorial, 2 factorial, 2 factorial. Now how many repetitions are there? We will look at it one by one. 3 is appearing twice. So we will divide it by 2 factorial for this. 2 is appearing thrice. So we will divide it by 3 factorial. Just like this, then just like before, you remember when we were checking the number of permutations, this is exactly that. So the number of times an identical size is appearing, we will divide the entire thing by the number of arrangements possible for that, basically 2 factorial. Okay. Now it should be clear where we're coming from. The formula should be very clear, but also the derivation where this formula is coming from, that should be even clearer, okay? Because there might be certain problems when we cannot apply the formula directly, but we can apply a modification of the formula, a modification of the derivation to the problem. We'll see. So number of ways of dividing 2n distinct objects into groups of size n each. One group of n, the other of n. So 2n factorial by n factorial, and we will divide the entire thing by 2 factorial. If let's say 3n objects each of size n, then 3n factorial by n factorial, n factorial, n factorial, and number of arrangements for these 3 factorial. So we will divide the entire thing by 3 factorial. Like this, I know you can do any kind of repetitions in the sizes, any form of distinct sizes and repeated sizes, you can take care of that. Now let's take a look at a problem. In how many ways can 8 distinct books be distributed among 2 students in the ratio 1:3? We have student A and student B. Now the order matters. The group are not identical. One group is going to A, the other group is going to B, right? So in the ratio 1:3, that means A gets X books, B gets 3X books, total 4X, which is equal to 8, which means X is 2. So that means A is getting 2 books, B is getting 6 books. So we have to divide 8 books into these two groups, one of size 2, one of size 6. You do not have to use the formula. You can directly just think, out of these 8 books, I have to select 2 books for A and the remaining 6 will go to B. So 8C2. Same answer, same thing. You can do it with any solution. Both are correct. You should just know all of them, and you should not, again, you should not repeat any case. You should not miss any case. If you're making sure of that, then you will get the right answer no matter which method you choose. Okay? Now, in how many ways can 8 distinct books be distributed among 3 students such that each student gets at least 2 books? We have 3 students, A, B and C. Each of them is getting at least 2 books. So 2, 2, 2, 6 books. Now we have 2 still left. How many ways we can distribute these 2 books? Either all the 2 remaining books will go to one of these students, right? So it will be either 2, 2, 4, or 4 can be here or 4 can be here, right? And the remaining 2 will be 2, right? The remaining 2 books will go to one single student. So, or 4, 2, 2 or 2, 4, 2. So, total 3, C1. We are just picking one student who gets 4 and that the remaining will get 2, so we do not have to do anything. So 3C1 is equal to 3 cases. I'm writing this even though we had counted all the 3 cases, but I'm just counting in case the number was greater than 3 or something like that. Then you should know how to directly count the number of cases under this possibility 1. Option 2 is, we have 2 books. Now each of them is getting at least 2. We have 2 extra books now, and we have to distribute those. We cannot just keep it ourselves. We have to distribute the 2 extra books. Either we gave the 2 books to one student, or what we are going to do is we are going to split those 2 books and give one to one and the remaining one to someone else, which means it will be something like 2, 3, 3. Now the order can be different. One of them will get 2 books, the other will get 3 books, right? So how many ways of doing this? We have to select one student who will get 2 books. So again 3C1. So either A will get 2 books, or B will get 2 books, or C will get 2 books, and the remaining 2 will get 3 books. Now for each case, let's see how many ways of distributing the books are there. For first one, there are 3C1 cases, right? 3C1 possibilities, 3C1 arrangements. Now once we have fixed the order, let's say it was 2, 2, 4, then we have to divide it in this order. Now you might say that, ma'am, 2 and 2 are identical, so we should divide it by 2 factorial. But no, not in this case, because in this case AB is going to, let's say, book A and book B is going to student A, and book C and book D is going to student B, or the other way around. Book C and book D are going to book student A, and book A and book B are going to student B. These two are separate cases. Earlier we were counting these as the same cases, but not anymore, because this left one is going to student A and this right one is going to student B, right? So now these are separate cases. Either student B gets CD or AB. So we are not counting any repeated cases, which means we do not have to divide this by 2 factorial. Likewise, for second case, we get 3C1 and then 8 factorial divided by 2 factorial, 3 factorial, 3 factorial. Again, if these two groups were identical, it did not matter first group or in second group, they don't matter, then in that case we would divide it by 2 factorial. But because it matters here, the first group will go to B and the second group will go to C, then we will not divide it by anything, and this is our final answer for second. We will just add these two and we will get our final number of ways possible. So from here we get 3. Let's just add it first. So bache, this is one tip I would say. Before adding, make sure that you take whatever you can common. So whenever we add, we can take 3 common from 3C1 and 8 factorial divided by 2 factorial and then common LCM 3 factorial, 3 factorial, 2 factorial, 4 factorial, and what do we have? Here we have 3 factorial, that is 6 into 6, 36, plus here we have 2 factorial, 4 factorial, 2 into 24, 48, and then you can solve it, right? What's the answer? What are you getting? Okay. So for all the students who were dividing it by 2 factorial, you do not have to divide it in this case. Be very careful when the groups are numbered. There is a first group and there is a second group, then they are separate cases. But if there is no distinction, one group and one group, there is no distinction which one comes first, which one comes second, which one goes where. Remember, if we fix the competition for each team, then they are separate teams. But if they are just 3 teams there playing together, just in 3 different teams, then we are counting the cases repeatedly. So be very careful while understanding this. After this class, make sure you sit and think about this distinction. It's very important to actually think. You don't have to memorize. I keep repeating, do not memorize when we will count, when we won't. Understand it yourself, when the cases will be repeated versus when the cases will be unique. Okay, the final answer is, if you want me to calculate, I will do it just to check your answer, just to verify your answer. So 8 into 7 into 6 into 5 into 4 factorial, and then 3 from here, and 36 plus 48 is 84 divided by 2 into 6 into 6 into 2 into 4 factorial. 4 factorial gets cancelled. 2 and 6 is 12, which is 12 into 7 is 84. What else is there? 6 gets cancelled. 2 is this. So we finally have 4 into 7 into 5 into 3, which is 21 into 20. So I think it's 420. Right? I'm not missing anything. 21 into 20. Yeah, is this what everyone is getting? Oh, into 7. My bad. Into 7. So 420 into 7 is 2940. So this is the final answer. So for all of those who were dividing it by 2 factorial, you will get the wrong answer. You must be getting half of this. So be very careful. Alright. We have to be very careful when we are dividing this. You just don't memorize. Again, don't memorize when we divide by 2 factorial. Oh, we saw the same sized groups, we have to divide it by 2 factorial. No, only when the groups are identical, in the sense that this group and this group are identical, there is no distinction. But here there is a distinction. This group is going to student A, this group is going to student B. I keep repeating this so that this is absolutely clear to everyone. Okay, if you still need some clarification, I suggest that you sit down and just think about this. I'm sure you will reach the conclusion on your own. I hope so far you have been with me. I hope so far you have been able to follow everything, because we are taking it very slow. We're not rushing this. We are making sure that we understand everything, right? I could have just come and told you the formulas and you would have been able to somewhat solve the problems, but that's not what our goal is, right? We are taking it slow. We are understanding every single formula, every single derivation, where it's coming from, how are we actually making sure that we're counting all the cases, and how to apply the formula, as well as how to identify when the formula might not be enough and we actually have to make sure that maybe the exceptions are taken care of. Like we saw in the last class, at the very end, the last problem, we saw that we cannot just memorize a formula and apply it. We actually have to see when we can apply it and when we cannot. But the one thing that will always work is understanding where the formulas are coming from and applying that derivation directly, counting all the cases one by one, and that is how you can make sure that you get the right answer every single time. Now, moving on, today we are actually doing another kind of problem. As you can see in the title or behind me, we are just discussing one kind of problem, but it's very important when we actually have to choose at least one object. We are choosing some objects, but we have to choose at least one under different conditions and different scenarios. We're going to see this kind of problem one by one, and a very important application of this kind of problem is when we have to count the number of divisors of any natural number. So let's start. If there is any doubt, feel free to ask in the chat. Who will be teaching us RMO? I saw this question last time as well, and I don't know what exactly your problem, what exactly your question is, in the sense that are you wondering about YouTube, or are you wondering about the classes, the batch that is running on Unacademy? So different teachers, a mix of teachers will be there for you. I am here. I'm not a full-time IOQM teacher. I will keep making appearances on this channel, but I'm mainly a JE educator. But because combinatorics and combinatorics for JE and combinatorics for IOQM is very similar, so that is why I thought I can take this up for you guys, because this is one of my favorite topics. This is something that I would love to teach. This is something I feel I can teach you well, because I have been good at it. I know how to make sure that every case is counted, which is why I'm telling you my thought process behind every single question, how to actually make sure that you are counting every single case. Okay, but a mix of teachers are going to be teaching you for RMO, for IOQM, just like how it's been. But if you're wondering about the batch, then that is a separate question. Okay, let's start. So what exactly do we mean when we say we have to select at least one object? Let's look at an example here. We have a bunch of fruits. Okay, we have a fruit basket where there is one banana, one mango, one apple, one pear and one orange. So we have 5 different fruits, one of each, in our basket, as you can see. Now we have to select at least one. We can select any number of objects out of these, any number of fruits out of these, but we have to select at least one. We have to eat at least one fruit, but it's up to us that we can select more than one, maybe 2 of these or 3 of these or 4 of these. Now you might make cases, right? Like maybe we take 1. That is one case. So selecting 1 out of these 5, 5C1. Or we select 2, 5C2, or we select 3, or we select 4, or we select all 5. These are all the cases. Now if this number were higher, this would have been a lot of calculations, right? If there were more than 5 fruits here, if there were more than 5 objects, then it would have been really large calculations, right? We don't want to get into that. So let's take a look at this problem from another angle. We have solved, by the way, we have solved this kind of a problem where in the first class, in the very first class, when we were thinking about selecting 1 or more options in a multi-correct problem. Do you remember? How did we solve that? We had a problem that we have to answer a multi-correct question. Now we can either select 1 out of those, or 2 out of those, or 3 out of those, or all 4. We can mark all 4, we can mark 3 of those, we can mark any 2 of those, or we can mark any 1 of those, but we have to mark 1. It's a very similar problem. Even in that case, we had to select at least 1 option out of the 4 options. Now, just applying that same method here, we have an option of selecting the banana or not selecting the banana. So we may select it or we may not select it. Same for mango, we may select it or we may not select it. So we have 2 options for each of these fruits, right? 2 options for this, then 2 options for this, then 2 options for this, and these are not or situations, these are and situations, so we multiply all of this, right? Either we select this or we don't select this, and either we select this or we don't select this. So like this we multiply, which means we get 2 raised to power 5. But just like in that problem, we are counting one case when all of them are not selected, right? One such case would be we don't select banana, we don't select the mango, we don't select the apple, we don't select the pear, and we don't select the orange. We don't select any of these. That is also counted in this 2 raised to power 5. But we have to select at least 1 fruit. So that means we will just exclude that case, we will just ignore that case, and the rest will be fine, right? In all other cases, in all the rest, so what is this? 2 raised to power 5, 32. Out of those 32 cases, only 1 case is there where we don't select any of these. The rest 31 cases are making sure that we are selecting at least 1, and we are counting all the possible scenarios where we select maybe apple and pear and nothing else. We're counting that case as well. So we're counting all possible combinations. So we just have to subtract 1 where we don't select any one of them, and the rest will be fine. So what is the total answer? 31. Okay. Old information, right? Just revising that same thing. So if we have 5 distinct objects, then we have to select at least 1. How do we do it? 2 raised to power 5 minus 1. Even in that case, even in that problem, how are we counting all the possible number of cases? 2 raised to power 4, because there were 4 options, minus 1, because we have to remove that case when we are not marking any of those 4 options. So 15 was the answer back then, if you all remember. Now, what if we have multiple of one type of fruit? Let's assume all mangoes are identical. Okay, so let's say we have 3 mangoes, 4 apples and 5 bananas. Okay, we have 5 bananas, 4 apples and 3 mangoes. They are identical to each other. All 4 apples are identical. Okay, so now we have to select at least 1 fruit. How do we approach this problem? what we're going to do is, there are 3 mangoes, right? Just look at the mango basket, okay, for now. Forget about apples and bananas. Now, we can either take 0 mango, or we can take 1 mango, or we can take 2 mangoes, or we can take 3 mangoes, right? So, in total, we have 4 options now. Earlier we had, if we look at this in the same way, for this mango, we had either we took 0 mango or we took 1 mango, and that's it. So, number of mangoes available plus 1, that was the number of cases we could make, right? Number of mangoes plus 1 for this case when we are not taking any mango. So, just like this, 3 plus 1. So, we have 4 options, 4 number of cases. Just like that, even here we can take 0, 1, we have 4 apples, so 0, 1, 2, 3, 4. We can take any number of these because they are identical, we don't have to choose. Now, but this is something very important, this is a very basic thing that students get confused over. If we are taking this case, when we are choosing 1 apple out of those 4, now it's not going to be 4C1. Why? Because all 4 are identical, it is 1 case. We won't have to take 4 cases, that either we choose the first apple or the second apple or the third apple or the fourth apple. No, because they're all identical, so we're counting that as 1 case. Okay, so be very careful with that. Now, that means we have 5 options for the apples, and just like that we have 5 bananas, so we have 5 plus 1, 6 options for the bananas. So we have 4 options for mangoes, 5 options for apples, 6 options for bananas. Total how many options? 4 into 5, 20, into 6, 120. But just like before, it is possible that we take 0 mango and 0 apple and 0 banana. That case is also being counted here. So we have to remove that one case. So we'll just do minus 1, and the final answer is 119. Alright, because there is at least 1 fruit. If that condition was not there, if the question was that how many ways of choosing, even if you don't choose any, that is also counted, right? That case is also counted, then the answer would have been 120. But if we have to select at least 1, then we have to remove the case when none of these are being chosen. So, the formula, let's discuss the formula. How did we get in, like we understood the derivation for the formula, now let's just formalize it. So, if we have n distinct objects, so for each of them we have 2 options, either we take them or we don't take them. So, 2 raised to power n minus 1 for that one case when we don't select any one of them, right? If we have p objects of one kind, q objects of second kind, and r objects of third kind, okay, we total have p plus q plus r objects, and out of that p are of one kind, q are of second kind, and r are of third kind. Then what was the answer? We have p plus 1 options for the first kind, q plus 1 for the second kind, r plus 1 for the third kind, and we have to remove that one case when none of them is being chosen, so minus 1. Now let's combine the 2. Now what if we have p objects of one kind, q objects of second kind, and the rest are distinct. We in total had n objects, and we have to select at least 1. Okay, so we have p of one kind, q of second kind, and remaining n minus p minus q, which are all distinct. So for the p identical objects, we have p plus 1 options. For the q identical objects, we have q plus 1 options, and for the remaining n minus p minus q, we have 2 options for each of them. So 2 raised to power n minus p minus q, and out of all these cases, we have to remove that one case when none of them is being chosen. Now, bacha, another way of looking at it is, please, it's my humble request to all of you, do not ever memorize a formula. Understand where we get it from, and with practice, you will immediately see, oh, I remember, I've practiced it enough that this is 2 raised to power n minus 1. But do not just memorize the formula, always understand where it's coming from. So, let's say we had p objects of one kind, and then q objects of second kind, and we said the rest were n minus p minus q were all distinct. So 1, what color is left? Like this, let's say. So these are n minus p minus q, because in total we have n objects. Now we have p identical objects. So out of these we have how many options of choosing? 0, 1, 2, 3, 4 up to p. So p plus 1. From here, just like this, we have q plus 1. Then for this one, just this one object, there's exactly one object of this kind. So just like here, p plus 1 option, 0, 1, 2 up to p, here that p is 1, 0, 1, and that's it. The list ended because p was 1. There's exactly one object of this kind. Here there were p objects of this kind, so p plus 1. Here there's one object of this kind, so 1 plus 1, 2. Similarly, 2 for this, 2 for this, 2 for this, 2 and 2. So that is where we are getting this. It's not a different problem, it's exactly the same problem. Here we had p which was greater than 1, here p was equal to 1. We're still doing p plus 1, 1 plus 1, 2. So now we can just combine this, because how many times are we writing? 2 n minus p minus q times. So this becomes 2 raised to power n minus p minus q. So we combine all of these and then remove that one case when none of them is being chosen. Okay. Any doubts? Now, this is the problem that we did in the first class, if you all remember. We have 10 bulbs which can be switched on independently, right? They have 10 independent switches. It doesn't matter which has been turned on already. We can turn it on and off without, irrespective of the other bulbs. Now, in how many ways can the room be illuminated? Now, we have 2 options for each of those 10 bulbs, right? We have 2 options, on or off, on or off, on or off for each of those 10. So 2 raised to power 10 options. But this also has one such case when all of them are off. And in that case, the room is not illuminated, the room is dark. We had to illuminate the room, so we will remove that one case where all the bulbs are switched off. And that is our final answer, 1023. Okay, so this is how you can do it. Very logically, do not memorize the formulas, understand, and you will never get any question wrong. Okay. Now, a very important application is whenever we have to count the number of divisors of a natural number. In that case, it is a very similar problem. Let me show you how. Let's say we have a natural number n and we have its prime factorization. Prime factorization, which means all these p1, p2, p3 up to pk are distinct prime numbers. Not composite numbers, they have to be prime numbers and they have to be distinct. That is how we write a number's prime factorization, right? And they each will have some exponent in the expansion, right? For example, if we are doing it for 24, then it will be 2 raised to power 3 into 3, and which means the exponent for 3 is, the power of 3 is 1. So they are all distinct prime numbers. P1 is 2, P2 is 3. We're not going to write 4 or 8, 6, any such number because they are composite. We have to write the prime numbers. That is how we write any number's prime factorization. Now, if we need to calculate the number of divisors of 24. What are the divisors of 24? It's 1. 1 also divides 24. Then 2 divides 24. 3, 4, 6, 8, 12 and 24. Now 24 is a small number. We can calculate the number of divisors. 1, 2, 3, 4, 5, 6, 7, 8. In total we have 8 divisors. But for any number, if we have its prime factorization, how can we calculate the number of divisors? Just like before, our new problem is, out of these, we have to select any divisor, right? Any prime number. Now, for this, we have 3 2's, right? This means we have 3 2's and this means we have 1 3. So, for this, we have 3 2's. So, we have 4 options. We can either select 0 2's or 1 2's or 2 2's or 3 2's, right? We can either select 0 2's or 1 2's or 2 2's or 3 2's. Just for this one prime number, there are 3 plus 1 options. Where is this 3 coming from? From the power of that prime number. Then for 3, we again, just like before, we have, this is 1. So we either have option for selecting 0 3's or 1 3. Right? So that means we have 4 options for selecting 2's, including not selecting any, and 2 options for selecting 3. So in total, how many options of making a divisor is there? 4 into 2, 8, which is what we were getting. Now we're not subtracting 1. Why? Because what is that case when we do not select any of them? We select 0 for here, 0 for here, we get 1, right? 1 would be the divisor. If we are saying that we are including 1 as the divisor, then we are not going to subtract 1. If we were not including 1, then we would have to subtract that case when we are not selecting any of these prime numbers. So, bacha, I hope this is clear that as we select a bunch of 2's, a bunch of 3's, a bunch of these prime numbers, we are making a new divisor, right? Each of those divisors can be written as product of some of these prime numbers. We are just seeing how many cases can be there, how many divisors we can make, how many cases of choosing some prime numbers can be there. So, in general, what will be the formula? Alpha 1 plus 1 options for P1, alpha 2 plus 1 options for P2, alpha 3 plus 1 options for P3, and like that, alpha k plus 1 options for Pk. If the power is 1, then 1 plus 1, 2. Alright. Now, if we are not including 1 and n, we're not counting 1, we're not counting the natural number itself. Other than those two, we are counting all of them. So, out of the total, we will just subtract 2 and we'll get our answer, right? The number of divisors, the total number of divisors stays the same. We'll just subtract 2 When all of them were taken, that is n. When none of them was taken, 1. So in that case, we would get 1 and n, and we'll just subtract those two cases. The other cases are fine. Now, if we need to find the sum of all these divisors, what is the sum of all divisors of 24? 1 plus 2 plus 3 plus 4 plus 6 plus 8 plus 12 plus 24. What's the sum? 3, 6, 10, 16, 24, 36 and 60. We'll come to questions. We have to discuss the theory before we get into the questions part. Don't be impatient. Listen to whatever we are discussing. Even if you think you know everything, there might still be something that you learn, something new that you learn today. Do not ever be that overconfident. A good student is always paying attention to their teachers. That is how you differentiate from a good student versus an average student. So do not ever be impatient. Always listen to your teachers. There could always be something new, a new angle of looking at things. Every time you study something, even if you're repeating something you already knew, even then there could be some new angle, a new perspective that you might yourself gain. So just be patient. Okay, so the sum of all the divisors is 60. This was anyway very long. We had only 8 divisors and we had to calculate the entire sum, and this was a lot of work. Now what if we had an even larger number? In that case, we'll just count all the possible cases. For 24, we had 2 raised to power 3 into 3 raised to power 1. So for 2, we had either an option of selecting 0 or 1 or 2 or 3. And for 3, we had this. Now, if you expand all of this, let's expand this product. Then we get 2 raised to power 0, 3 raised to power 0 plus 2 raised to power 0, 3 raised to power 1, 2 raised to power 1, 3 raised to power 0, 2 raised to power 1, 3 raised to power 1, 2 raised to power 2, 3 raised to power 0, 2 raised to power 2, 3 raised to power 1, 2 raised to power 3, 3 raised to power 0, 2 raised to power 3, 3 raised to power 1. What are all of these? These are all the possible divisors, and we are trying to find the sum, which is why we express them as these products. Okay, so if you want to check, this is 1 plus 3 plus 2 plus 6 plus 4 plus 12 plus 8 plus 24. This is nothing but all the divisors, and we are finding the sum. So if we just find this sum, which is easier because we have to find the individual brackets and just multiply instead of adding all of these numbers, right? Now, so to generalize, we have p1 raised to power 0 plus p1 raised to power 1 plus p1 raised to power 2 up to alpha 1, and like that for each of these prime numbers we'll do that. But now it still seems like a lot of work, but if you students know what a GP is, this is, each individual bracket is a GP with the first term as 1 and common ratio as P1, and number of terms is alpha 1 plus 1. So like that we can form a GP of every single bracket. For each of them, the first term will be 1, the common ratio will be that prime number, and the number of terms will be power plus 1. So what is the sum of a GP? A r raised to power n minus 1 divided by r minus 1, right, where a is the first term, r is the common ratio, n is the total number of terms. So in this case, if we have to calculate the entire sum, it will be A is 1 for all of them. P1 raised to power alpha 1 plus 1 minus 1 by P1 minus 1 into P2 raised to power alpha 2 plus 1 minus 1 by P2 minus 1 into P3 raised to power alpha 3 plus 1 minus 1 by P3 minus 1 and so on. So if you want to verify, let's verify for 24. We have this GP. So what is this? 1 into R2. How many terms do we have? 3 plus 1, 4 minus 1 by 2 minus 1. And similarly for the other bracket, what's the first term? 1. What's the common ratio? 3. How many terms? 1 plus 1, 2 minus 1 by 3 minus 1. So if we just simplify this, 16 minus 1, 15 by 1 into 9 minus 1, 8 by 3 minus 1, 2. So we get 15 into 4, 60, same as before. Now this is definitely easier, this is definitely simpler, this is definitely faster. Okay. So one last topic before we get into the questions. Now, but bache, for all the students who were asking for questions, trust me, these are also questions. These are not something that we are studying just like that. These are also problems, but instead of fixed number, we have a variable instead of the number. It's still a problem. You still see such questions, right? When we do not have a specific number, we have a generic formula, a generic expression. Okay, so one last topic, number of ways in which n can be resolved as a product of two factors. We have n, the same as before, that is its prime factorization. Now we have to resolve it into two factors. What does that mean? For 24, it can be either 1 into 24 or 2 into 12 or 3 into 8 or 4 into 6, and that's it, right? 8 into 3, which has already been taken, 12 into 2 already been taken, 24 into 1 already been taken. So what exactly did we do here? We split them into pairs, correct? We split them into pairs. So 1 pair, 2 pair, 3 pairs, 4 pairs. We had total 8 factors, correct? We had total 8 factors. That means there can be 4 pairs in those 8 factors. So if the total number of factors is even, we can just divide it by 2. But what if the total number of terms is odd? When can that happen? Let's take a look. The total number of terms here is, the total number of divisors here is alpha 1 plus 1, alpha 2 plus 1, alpha 3 plus 1, alpha k plus 1. If any single one of them is odd, then that term odd plus 1 will be even and the final product will be even, the number of divisors will be even, and we can just divide it by 2, right? If any of these powers is odd, then there will be even number of factors. But if all of them are even, if all alpha 1, alpha 2, alpha 3, alpha k are even, in that case, this will be odd, even plus 1, odd, even plus 1, odd, even plus 1, odd, even plus 1, odd. All of them will be odd and the final product will be odd, which means the total number of divisors will be odd. When does that happen? If all of them are even, let's say n is 2 raised to power 4, 5 raised to power 2, 7 raised to power 4 and 11 raised to power 2. We have all even powers. In that case, we can do 2 raised to power 2, 5 raised to power 1, 7 raised to power 2, 11 raised to power 1, whole raised to power 2. That means n is a perfect square, right? If all the powers are even, then we can do this to the prime factorization, which means n is a perfect square. Correct? So, if n is a perfect square, in that case the number of divisors will be odd, but if n is not a perfect square, then the number of divisors will be even. So, if n is not a perfect square, then the number of divisors is even and we can just divide it by 2. We can just multiply the entire number of divisors by half. But if n is a perfect square, then what is happening? Then we are having odd number of divisors. Why are we having odd number of divisors? Let's see. Let's make it simple. Let's make it 100. Okay. So 100 is equal to 2 raised to power 2, 5 raised to power 2. It's a perfect square clearly. 2 into 5 whole raised to power 2, 10 raised to power 2. So 100 is a perfect square. Now what are the divisors? The divisors are 1, 100, 250, 425 and 520. How many divisors in total do we have? 3 into 3, 2 plus 1, 3, 2 plus 1, 3, 9. So we have taken 1, 2, 3, 4, 5, 6, 7, 8. We have taken 8 of them. What is remaining? 10. Now to make the pair, we have to count 10 twice. But while counting the number of divisors, we only took 10 once, right? So the total number of divisors for 100 was 3 into 3, 9. Which 9? 100, 250, 425, 520 and 10. These are all the 9 divisors. But now we need to form the pairs. So we need to add 1, 10 again. The root of this perfect square, the square root of this perfect square, we need to add this one term again. And now we can split all of these in 2 pairs by dividing it by 2. So if we just add 1 here, we get 10 and then we divide it by 2. So we get 5, right? So 5 is the number of pairs we can get for this particular natural number. How did we get to this? By adding 1 to the total number of divisors and then dividing it by 2. So we add 1 to the total number of divisors and then divide it by 2. So this is how you get the number of pairs, the number of ways in which we can divide the divisors into products. Alright, now let's look at a problem. So we have n is equal to 2700 and we have to find certain things. We have to find total number of divisors, number of divisors divisible by 15 but not by 4, sum of divisors and sum of even divisors, like that. So we will look at this one by one, but first of all we have to find its prime factorization. Without doing that, we cannot proceed. So what's the prime factorization? I'm not asking for the answer, I'm sure you can do it, but let's discuss this step by step. Again, maybe you might learn something, so answer. What is the prime factorization of 2700? Yes, bache, we will also cover pigeonhole principle. Thank you so much. 3 raised to power 3, 2 raised to power 2, 5 raised to power 2. That is correct because this is 27 into 100. So 2 raised to power 2, 3 raised to power 3 and 5 raised to power 2. 27 into 100. We now have the prime factorization, right? So we have 2 2's, 3 3's and 2 5's. We have to count the total number of divisors. Total number of divisors, this is simple. We have 3 options. We have 2 2's, so we have 3 options for 2, 4 options, 3 plus 1, 4 options for 3 and 3 options for 5, 2 plus 1, 3. So in total we have 3 into 4 into 3, that is 36. Total number of divisors. When nothing else is mentioned, then we are also counting 1, we are also counting the number itself. So total number of divisors comes out to be 36. Now let's take a look at the next problem. We applied a condition to our problem. Total number of divisors that are divisible by 15 but not by 4. What are we doing in that case? We are making sure that at least 15 is there. At least 1 3 and 1 5. 15 is what? 3 into 5. So at least 1 3 and 1 5 should be there in our divisors. Then we are making sure that it is divisible by 15. But not by 4. What does that mean? No 2 2's should be there. This is 2 square. So 2 square should not be there as soon as we add 2 square. For example, let's say we have 2 square into 3 into 5. What is this? 4 into 3, 12 into 5, 60. In that case, 60 is divisible by 4, but it is also divisible by 4. 60 is divisible by 15, but also divisible by 4, which is not what we want. Also, if we do not have at least 1 and at least 1 3 and 1 5, then also we will not have a number which is divisible by 15. So we have to make sure that we at least take 1 3. That means now we have how many options? We can either take 1 3 or 2 3's or 3 3's. At least 1. Here as well, we have to take at least 1. We can take 1, we can take more, that is also fine. But we have to take at least 1. 5 raised to power 0 is not an option. As soon as we do not take a 5, then it is not possible that we get a number which is divisible by 15. But here 2 raised to power 2 should not be there. No 2 2's should be there. 0 2's, that is okay. 1 2, that is also okay. It will only be an even number, but it won't be divisible by 4. But as soon as we take both the 2's, then it will be divisible by 4. So that means in total we have 2 options for 2, 3 options for 3 and 2 options for 5. So in total 12 possible divisors can be made that are divisible by 15 but not by 4. Okay, so this is how very logically you will approach this problem. You will not memorize anything. You just have to be very careful while counting the number of divisors. What's the next problem? We have to count the total sum of all divisors. So 2 raised to power 0 plus 2 raised to power 1 plus 2 raised to power 2, 3 raised to power 0 plus 3 raised to power 1 plus 3 raised to power 2 plus 3 raised to power 3 and 5 raised to power 0 plus 5 raised to power 1 plus 5 raised to power 2. Right? This is how we are counting all the possible divisors. Now these are individual GPs. All first terms are 1. So how many terms? 2 plus 1 3 minus 1 by 2 minus 1. Common ratio 3, how many terms? 3 plus 1 4 minus 1 divided by 3 minus 1. Common ratio 5, how many terms? 2 plus 1 3 divided by common ratio minus 1. So we will simplify this. 8 minus 1 7 by 1. 81 minus 1 80 by 2. 5 raised to power 3, that is 125 minus 1, 124 by 4. So we just simplify this, and what is the final answer that we are getting? 7 into 31, that is 217. 217 into 4, that is 8680. Is that what we are getting? Right? 8680, that is correct. Yeah. So this is how we will calculate the sum using sum of a GP. Okay? Because if we count this individually, it will be a lot more work. But using GP, it becomes easier, but it's up to you. If you do not know GP yet, then you can just simplify all of this. 1 plus 2 plus 4, 1 plus 3 plus 9 plus 27, 1 plus 5 plus 25. So here we will get 7, here we will get 40, here we will get 31. And we will get the same answers, we will get the final same solution. Okay, just a different method. It depends on you, whichever you find more comfortable, whichever can make sure that you get the right answer and you don't make a mistake. Alright, so this is how you calculate the sum of all possible divisors of any natural number. Now, we need to find the sum of all even divisors. Even divisors, that means at least 1, 2 should be there. 2 raised to power 0 is not an option now, right? 2 raised to power 0 is not an option. 2 raised to power 1. As soon as we add at least 1, 2, it becomes even and then it's fine. But if we do not take any 2, then it's an odd number and that is not what we are considering here. So now the problem becomes 2 raised to power 1, 2 raised to power 2. The others will remain the same because there is no restriction for the other numbers. We can take as many 3s as we want, as many 5s as we want. All we need to do is take at least 1, 2 to make sure that we're counting only the even divisors, right? That means now we knew this product. Even if you calculate 1 plus 3 plus 9 plus 27 or you use the GP formula, you will get the same answer as before, 40, same answer as before, 31. But here instead of 7 you will get 6. So either you take 2 plus 4, 6, or you can take the GP formula again in case there were larger numbers involved. Then first term now is 2, common ratio is again 2, number of terms 2 minus 1 by 2 minus 1. So this comes out to be 2 into 4 minus 1, 3 by 1, 6. So, or you can directly do 2 plus 4, 6. So whichever way you feel comfortable in, you will get the same answer, which is 7440. Now how I can check is, earlier it was 7 into this, now it's 6 into this. So that means one smaller multiple of 1240. So I'll just subtract 1240 from this. That is how you can be smart with your calculations. So 7440. Alright. So this is how we can manipulate the number of divisors, the sum of divisors. Whichever question we have, we can do it logically by first finding out the prime factorization correctly. If you mess that up, the rest of the problem will suffer, right? So first get the prime factorization correctly. Remember, it has to be all distinct prime numbers, and then just whichever condition is applied, make sure you're considering that correctly. For even, there has to be at least 1, 2. For divisibility by 4, there has to be at least 2 2's. So not divisible by 4, there cannot be 2 2's or more 2's, right? Even if we had 3 2's available and we added all 3, it would still be divisible by 4. So we needed to add less than 2 ones. For divisibility by 15, we needed to add 1, 3 and 1, 5. If instead of 15, we had, let's say, divisibility by 45, which is 3 raised to power 2 into 5. Then we needed to add at least 2 3s and at least 1 5. So like that, you can do any kind of conditions. I'm sure if you understood everything, the logic behind everything that we discussed today, you can solve all such problems very easily. Okay. Now, the number of ways in which 12 can be resolved into 2 factors. What is 12? 2 raised to power 2 into 3 raised to power 1. How many total number of divisors? Number of divisors is total number of divisors first, not the answer to the problem. Total number of divisors is 6. Thank you. 2 plus 1 into 1 plus 1. 3 into 2, 6. Even number of divisors, just divided by 2. So 3 possible products, right? Also not a perfect square, which is why we are getting 6. Why? Again, let's just verify. Why are we getting even number of divisors? Because there is 1, 2. Why do we have 1, 2? One even number here. Because here this was odd. This was odd. And because we had an odd power here, that means clearly this is not a perfect square. So we can just divide it by 2. Which ones? 1 into 12, 2 into 6 and 3 into 4. Now for 36 we have, clearly we know it's a perfect square, but let's just forget that for once and we start doing its prime factorization. Now this comes out to be 2 raised to power 2, 3 raised to power 2, all even. So yes, it's a perfect square. Total number of divisors is 2 plus 1, 2 plus 1, 3 into 3, 9. Odd, clearly it will be odd because even plus 1 odd, even plus 1 odd, we are multiplying only odd numbers, so we get a odd total number of divisors. Now we have to divide it by 2, not before adding 1 to that, right? Just like when we were doing it for 100, it was very similar, right? 2 raised to power 2, 5 raised to power 2. So just like that, we will add 1 and then divide it by 2. So 10 plus 2, 5. Which ones? 1, comma 36, 2, comma 18, 3, comma 12, 4, comma 9 and 6, comma 6. So 1, 2, 3, 4, 8 divisors we have here, and the 9th divisor, that was 6, we added one more 6 to complete the pair. Okay, so with this we are done with this category of questions. Even though we just discussed one specific type of problems, but this was very important, this is very crucial to understanding. You will see a lot of applications here and there of this particular type, so we needed to discuss this separately and in great detail. But now I hope after today's class you can solve any such problem. You can use any of this in any problem. Even in our future classes, you will see that we will be using this information, this knowledge in other problems where we have something like this. We are checking how many cases can we make, how many possibilities are there of choosing out of these p identical objects, p plus 1. So like that we can use all of this. So make sure you revise all of this. So in the last class we covered how to select objects when we have to take at least one of them, right? When we have to select at least one of them, then how can we find the number of ways of selecting? Today we are going to select exact number of objects. So before we start, is the audio fine? Is the video fine? Just let me know so that I can start. All right. So without wasting any more time, we are going to see the exact kind of question I'm talking about. So yesterday we had a bunch of fruits and we had to select at least one out of those, right? Today we have to select exactly 4 fruits out of our given fruits. How many fruits do we have? We have 6 apples, 5 mangoes and 4 bananas. Now we have to select exactly 4 fruits out of them. How many ways to do that? Either we can select 0 apples and let's say 1 mango and 3 bananas, or 0 apples, 0 mango, 4 bananas. Like that we can have a lot of different options, right? One way to do this is by finding the combination. We have to find X number of apples, Y number of mangoes and Z number of bananas such that the sum of these 3 numbers comes out to be 4, right? Now, what is the condition for X, Y, Z? It can be 0 or 1 or 2 or 3 up to 4, right? So that means for X, Y and Z, we have either, now without worrying about the order, what are the 3 numbers? Without worrying about the order first, what are the 3 numbers that can sum up to 4? It can either be 0, 0, 4. Remember from the first class, in order to count all the cases, we have to follow a certain order. In this case, I will follow the ascending order. Okay, so that means we first fix the first 0 and then 0, 1 and the remaining will be 3. 0, 2, 2. Now I will not count 0, 3, 1 because I've already counted again, because the order doesn't matter. I'm just checking what 3 numbers can I pick so that their sum is 4. Okay, so we are only following the increasing order. We will not follow 0, 3, 1 because that will increase and then decrease. So it always has to be increasing. We have reached a point when this was decreasing, this was increasing, so they are equal now. The next one will be, this will be more than this, 0, 3, 1. So time to change the first digit. Now it's 1. Now again, it cannot decrease, now it only has to be the same or increase. So 1, 1, 2, or that's it, because if we move on to 1, 2, then the last one will be 1, increase and then decrease. So we're done with 1. Which means now if we do 2 and then 2, the last one will be 0, it will decrease again, so even this will not be counted. But in order to count all the cases without repetition, we have to follow a certain order. So these are all the cases that we can get, right, without order. Now let's order them. How many orders for this? Four can either be in the first position or the second position or the third position. Now we have 0, 0, 4 or 0, 4, 0 or 4, 0, 0. So how many? 3 factorial divided by 2 factorial, because 2 zeros are identical. Similarly 0, 1, 3, this will have 3 factorial. 0, 2, 2, again 3 factorial by 2 factorial, and 1, 1, 2, 3 factorial by 2 factorial. So we get 3, 6, 3 and 3. In total 50. So that is one way you could have done this, right? Just by logically, by counting, by using what we have learned so far. But how else can we look at this? We had to count all the possible cases. What if this number was more than 4? What if this number was much larger? In that case, we would have to count a lot more, right? So let's look at another way. We have so many ways of doing this and we are going to take our sweet time on this question because we want to cover all possible methods. Yes, okay, yes, is this live? This is live. It is live. I just wasn't paying attention to the chat because we cannot break the flow. While I'm explaining a solution, I don't want to break the flow. Once I'm explaining a solution, I will be focused on that, but that is why I will not read the chat in the middle. Anyway, yes, please go ahead. What is the doubt? I don't know what your doubt is, Vijay. Come on. You're studying in 12th. Should I prepare for IOQM? If you're preparing for JEE and if that is your goal, you should focus on that. Anyway, you should not like Olympiad should be lower priority if JEE is your goal, bache. Alright. So this is clear, right? It was a tedious process, but we reached the answer. The answer is 15. Alright. Now let's take a look at another method. Now, if we fix the first one, let's say 0. Now the remaining two have to be equal to the sum of the remaining two has to be 4. If I fix this one, then I know this one, right? It will be 4. If it's 1, I still know this one, 3. So all I need is how many options do I have for the mangoes? If this is 0, then how many options do I have? I have 0, 1, 2, 3, 4. It can go from 0 to 4, right? And I will still know the last one. So for each of these cases, there is exactly one possibility for bananas, for Z. So that means for 0, I get 0 to 4, that is 4 plus 1, 5 options. If I fix this to 1, now the remaining sum needs to be 3. That means now this can go from 0 to 3, and as soon as I fix this number, I know Z. So how many possibilities for this? 4. How did we get 4? 3 plus 1. So similarly for 2, the sum will be 2. So 0 to 2, 3 and so on, right? The next it will be 2, and lastly, once I fix it to be 4, then it will have to be 0, 0. So exactly one case possible. So how many cases in total are possible? 5 plus 4 plus 3 plus 2 plus 1. Because it's a small number, you can add them, we get 15. Or if it were a larger number, then we can use AP or sum of series formula, however you feel comfortable. So for sum of series, we have 5 into 5 plus 1 by 2, right? Number of numbers 5, so n into n plus 1 by 2, again that is 15. So that is another way of looking at it. Also correct, because we're getting the correct answer. We did not miss any case, we did not count any case, repeated any case. So that means this is also correct. So this is the second method of doing this. Now let's take a look at another way. Just a second. Now we need to select 4 fruits, right? So that means we have to partition this such that the sum of these x, y, z is 4, right? Before we understand how to actually do this, we will look at another problem, okay, just to see what kind of questions we are looking at. All right, so we'll come back to that question. We have 2 more methods to discuss for that problem. We will come back to it, but let's first see all of such problems, and then we are going to combine the methods and see how they work for all of them. So now, for example, we have a word mathematics, right? This is mathematics. I've just arranged like letters together. So now that means we have 2 M's, 2 A's, 2 T's, 1 H, 1 E, 1 I, 1 C, 1 S, right? We have to form 4 letter words with or without meaning, right? With or without meaning. So how many 4 letter words can we form? We have total 1, 2, 3, 4, 5, 6, 7, 8. We have 8 letters and 3 are available twice. So what are the options we can have? Either all letters are distinct or 2 letters are same. Now all letters are distinct, that is one case. Another case is 2 letters are the same and then the other 2 are different. We can order them. It can be L2, L1, L3, L1. We will check the ordering, but once we are selecting the letters, in that case we are only checking how many are similar, how many are identical and how many are distinct. Then another case is 2 are same and the other 2 are also same. Now more than 2 letters of the same letter are not available. We cannot have 3 of the same because 3 of any letter is not available, right? Max we have 2 M's, 2 A's, 2 T's. So these are all the cases we are going to have. That means we have, how many options do we have for selecting 4 distinct letters? We had total 8 letters available. 8 distinct letters are available to us. So we have to select 4 out of these. And once we have them, then we have to arrange these, all possible options, all possible arrangements. So multiplied by 4 factorial. In this case, we have to select one such letter which is available twice. So out of 3, we have to select 1. So 3C1 into for the other 2. For the other 2, how many options do we have? We don't just have these 5 options, but we have 7 options. Once we have selected L1, that is gone, but we can still, let's say we chose M. So M is gone, but we can still select A1s to T1s or out of these distinct letters available, right? So for these 2, we don't just have 5 options, we have 7 options, 7 remaining options. So we will select 2 out of those 7. And now we're going to arrange these. How do we arrange these? 4 factorial divided by 2 factorial, because these 2 are identical. Now for the last case, we have to select 2 letters, just 2 letters, one L1, one L2, such that these letters are available twice here. How many letters do we have like that? 3. We have 3 such letters, M or A or T. We cannot select H or E or so on now because we need the same letter twice. So out of these 3, we will select 2. So 3C2, and once we have the 2 letters, we are going to arrange this. So 4 factorial divided by 2 factorial, 2 factorial. And we will just add this up and we will get our answer. Alright. So what's the answer? I think you can calculate, right? Someone says 2, 4, 5, 4. Okay, if you want to check, let's check. But I know you can do that very easily. And that comes out to be, for first case, we have 8 factorial by 4 factorial, that is 8 into 7 into 6 into 5, which is 1680. For second one, we have 3 into 7 into 6 by 2, 21 into 4 factorial by 2 factorial, that is 24 by 2, 12. This comes out to be 63 into 6, 756, right? And for the third case, we have 3 into 4 factorial by 2 factorial, 2 factorial, that is 6. So in total 18. So we get 2, 3, 2, 4, 3, 6 and 2, 4, 5, 4. That is correct. Very good. That's the answer everyone's getting? Yes? Perfect. So this is another way of doing this kind of problem by making sure you're counting all the cases one by one. Either all are distinct or 2 are similar or 2 are similar, 2 are similar. If we had more such options, we are going to count in that order. Okay? We'll come back to the first question, don't worry. But let's take a look at another kind of problem which will happen to be very similar. Now, what is the problem that we have? Earlier we had to select exact number of objects. Now we have to distribute the objects. Okay? So, distinct objects. Right now in this problem we have 5 different ice creams. Okay? We have 5 different ice creams and we have to distribute them among 3 students without any restrictions. That means even if some students do not get any ice cream, that is also one possibility. But we have to finish the 5 ice creams. We have to distribute them. Total should be 5. So now x plus y plus z is 5. The first student gets something, the second student gets some number of ice creams and the third one gets some number of ice creams. Again, we'll order them. Right? We'll start with 0 and then the other one also gets 0 and 5. Or now, if we just count all the possible cases, it might be a lot of work. Why? Because we are not done here. This is not just one case. Okay, this is one case. But the next, let's say, there is 0, 1, 4. Now, this is not just one case, but actually, which one ice cream is this second student getting? We have 5 different ice creams, 5 different flavors, 5 different brands, just 5 distinct ice creams. And now second student has to get one of them. But which one? We also have to see which one, right? So that is why we can't just list all of them. In that case, we'll have to count all the possibilities for each case. So we are going to do the first method. We're going to see how we can find all the possible combinations of numbers, and then we'll see the possibility of finding the ice cream, selecting the ice cream, and then arranging it within these 3 students. Okay, so let's start. First of all, first step is which 3 numbers sum up to 5? Which 3 numbers sum up to 5? 0, 0, 5. Then we go 1 up, 0, 1, 4, 0, 2, 3, and that's it. 0, 3, 2. We're not doing it because it is increasing and then decreasing. We've already counted that. We're going only in one order so that we don't repeat any case. Then we move on to 1, 1 and remaining 3. 1, 2, 2 and that's it. Then no further case will be there because 2, 2 and then 1, we have already counted this. So these are all the possible cases, right? Now we have to find how many ways of selecting the ice creams. So here we have to select first 5C0, then out of the remaining 5 we select 0, out of the remaining 5 we select 5. Here we first select 0, then out of the remaining 5 we select 1, out of the remaining 4 we select 4. I'm just doing the proper way. Of course, logically you will not do all of these steps. You know that this is just one case possible, all 5 are going to this. In this case we just have to select 1, the remaining 4 will go to the third student, or however we arrange it. Then for this we have again same logic, 5C0 into 5C2 into 3C3. Now 5C1, we first select this one ice cream, out of the remaining 4 we select this one ice cream and the remaining 3. So now I don't have to do the last one, right? It will always be one possibility. If we have selected these, then the remaining ice creams will go here. So I'm not going to write this anymore, and now we have 5C1 into 4C2, and that's it. Now for each of these cases we also have to see how many arrangements are possible, right? So okay, we have selected the partition. Now we have the ice creams. We have one set of 0 ice cream, another set of 0 ice cream, and another set of 5 ice creams. Or in this case, one set of 1 ice cream, one set of 1 ice cream, and one set of 3 ice creams. We have this. Now we have to arrange it. We have to see all possible arrangements, right? So we have to arrange all of these within the 3 students. So now here we will do 3 factorial by 2 factorial. Here we have 3 factorial. Here we have again 3 factorial. Here 3 factorial by 2 factorial. And here again 3 factorial by 2 factorial. Alright, so we'll just add these up and we'll have our answer. What's the answer that we're getting? Here we get 1 into 3, so 3. Here we have 1 into 5, 5 into 6, 30. Then we have 1 into 5C2, 10 into 1, 10 into 6, 60. Then 5 into 4, 20 into 3, 60. And then we have 5 into 4C2, that is 6. So 5 into 6, 30 into 3, 90. We'll just add these up and we'll have our answer, right? Is that what everyone is getting? Yes? Is there any doubt? So yes, bache, we have to count a lot of cases sometimes, but if each case is going to be handled separately, then we have to list all the cases, okay? If we can just find how many cases, how many possible partitions can be there. If the ice creams were identical, then it was the same solution as before. We just had to see how many numbers are possible in this case. But now we also, before arranging them, we also had to see how to select the ice cream. So then we had to count all of these. So it's 243 what you're getting, okay. 122, 10243, yes. So the answer is 243. But the method is more important. How we are actually making sure that we're counting all the possible cases in an order. We're not going to do this randomly, okay? So that is the most important thing. If you do it randomly, it is very likely that you will miss some cases, or you might end up wasting some time rechecking if you counted everything, if you missed anything. But if you go in an order, then it is very helpful. You will make sure that you're counting everything. Alright. Now coming back to the like object partition, right? Coming back to this like thing, when there are identical objects, like objects, identical objects, coming back to the original problem, if though they were 5 identical ice creams and we had to do it, such kind of questions, how do we deal with that? Okay, so let's say we are distributing 5 like balls into 2 people. Okay, 5 like balls into 2 people. That means we have 5 identical, say, blue balls, and we have to distribute it among 2 people. Now, that means, let's say the first one gets x, the second one gets y, and we have this. The same kind of equation we keep getting, and now we have to find a solution to this. Okay, so now we are going to discuss how to actually find a solution to this problem. There's a direct formula and there is a long derivation which is going to make sure that you will count all the possible cases whenever we cannot apply the formula directly. So first, let's see the formula. Okay, so in this case, this is very easy. We just counted this. For x plus y equal to 5, x can either be 0, and as soon as we fix the first one, the second one is clear. It has to be 5, right? If we fix it to be 1, then we know why. It has to be 4. If we fix it to 2, we know what y is going to be. So how many options for x are there? 0 to 5, that is 5 plus 1, 6. And for all of these 6 cases, there is exactly one possibility for y. That means in total 6 ways of distributing these 5 balls, 5 identical balls into 2 people. Okay, so in total we have 6 cases, right? So this is one way of solving this that we have already discussed when we are counting in a way all the possibilities. Now another way of looking at this is, let's say I have to put a partition in this, right? If I put the partition here, that means the first student gets 2, the second student gets 3. If I put the partition here, that means the first student gets 3 and the second gets 2. They are different cases, so we have to count them separately, right? Because the students are not identical, the students are obviously different. Now, there's also a possibility that I put the partition here. What does this mean? The first student gets nothing and the second student gets all of it. Or the first student gets all 5 and second student gets nothing, right? So that means as soon as I put a partition here, we have the exact distribution. So we can see it in a way. In one way of looking at this is, we have 6 possibilities of putting the partition, right? 1, 2, 3, 4, 5, 6. We have to select one out of these 6. So 6 possibilities, 61. That is our answer, right? So again we get 6. Another way of looking at it is, now this is the most important one. We have 6 things to arrange. We have 5 balls and 1 partition. So in total we have 6 objects to arrange. As soon as we find one arrangement of these 6, let's say it comes out to be this arrangement, this is a unique arrangement. Like this, we'll have all different unique arrangements, and that will give us a unique distribution between the 2 students, right? So how many ways of arranging these 6 objects are there? 6 factorial divided by 5 factorial, because 5 of these 6 objects are identical. So we get 6. Alright. Now let's take it one step further. We had 5 balls just like before, but now we have to distribute it among 3 people. X plus y plus z is equal to 5. Similar to our previous problem, if the 5 ice creams were identical, or if we change this 5 to 4, then it brings us to our first question, right? Now we can count all the possible cases, but if we just do the partition thing again, how many partitions do we need now? We needed 1 partition for 2 people. We will need 2 partitions for 3 people, right? If we have 2 partitions here, that means the first one gets 2, the second one gets 1, the third one gets 2. Or we can have something like this. Both the partitions are here. What does that mean? The first one gets 4, the second one gets nothing, the third one gets 1. So by arranging 2 partitions, by finding the position of these 2 partitions, we will find the unique distribution. So how many ways of arranging these 2 partitions here? We have 5 plus 2, 7 objects. So we have to arrange these 7 objects, 7 factorial divided by 5 balls are identical, 2 partitions are identical. So 7C2, this is nothing but 7C2. So with this we get a formula that if we have to arrange, we have to find these 3 numbers, x plus y plus z. If we have, in general, if we have x1 plus x2 plus up to xr, we have to distribute this n. We have to distribute this n into r different partitions such that their sum is n, and all these x1, x2, x3 and so on are non-negative integers. Alright, so if just like before, x plus y plus z, they were all 0 or 1 or up to n, because it cannot be negative, so the maximum it can go is up to n. So each of them can go from 0 to n, 0 to n, 0 to n. So we get a direct formula that we put n plus r minus 1 partitions, right? N objects, r minus 1 partitions, and we arrange these divided by the n objects and r minus 1 partitions. So this is nothing but n plus r minus 1 c r minus 1. This is the formula. Okay, so going back to our first question. Now we have n is 4, r is 3, minus 1, c, r minus 1. So we get 4 plus 2, 6, c, 2. That is 6 into 5 by 2. Again we get the same answer, 15. So this is the same as distributing 4 objects into 3 different partitions, right? So this is another method. Now one last method which might be the trickiest, but it is the ideal way of looking at it, because this is how we can solve any given problem like this, where we have to solve an equation. How do we do that? But whoever has a problem, understanding, I'm taking it very slow so that most of you can understand. If you still feel, that's the beauty of a recorded session. You can always go back to it, listen to it again. You're just asking me to repeat, but that's the beauty of technology. Now you can just make me repeat again yourself without me actually having to do that extra effort, right? So if you have any problem, understanding something that I already explained, you can always go back and listen to it. I'm sure you will get it. Okay, just give it some thought, think about it yourself, and you will get it. Now the most important part of today's class: how do we actually solve any such problem? That is called a multinomial theorem. x1 can go from 0 to n. And similarly, x2 can go from 0 to n, xr can go from 0 to n. Right? So, for x1, how many options do we have? X raised to power 0, x raised to power n, and like this we have for x2 as well. We have this for all our variables. And once we multiply this, but we will have a lot of terms in this multiplication, right? We will have x raised to power 0, x raised to power 1. We will have all possible exponents of x with different coefficients. But we need to find the coefficient of x raised to power n in this. Why? Because what will that do? We will get some value from here, some value from here, some value from each of these r, and that will form one case. As soon as we multiply all of them, the exponents will add up, right? Exponents will add up. For example, if we look at our previous problem. X plus y plus z is equal to 5. We are saying we need coefficient of x power 5 in x raised to power 0, x raised to power 1 up to x raised to power 5 raised to power 3. Because we have 3 variables, we will multiply this 3 times. Now let's say we pick this 0 from the first bracket, we pick 1 from the second bracket and 4 from the third bracket. So we get one such term where the coefficient is 1 right now and the power of x is 5. So now in how many ways can we pick such terms such that this x raised to power 5 is what we get? That is what we mean by coefficient of x raised to power 5 in this expression, because the number of such terms, such combinations, that will be, all such terms will be added, right? All such terms will be added. We will also add x raised to power 0, x raised to power 5. This will also give 1 x raised to power 5. We will get 1 x raised to power 5 from here. We will also get 1 x raised to power 5 from here, and like that, right? So that means the total number of combinations, that we can have, the arrangements that we can have, that will be the coefficient of x raised to power 5, because that many times we are adding the same term again and again and again. Okay, so that is why the ideal way of doing such problems is we have to find the coefficient of x raised to power n in this. And how do we make these brackets? We write in power all the possible values that these variables can take. Okay, so like here it can take 0 to n, so we wrote all the possible. If it could not take, let's say, few of these values, then we will skip those values. Alright, even here we took all possible values for x. So now let's just solve this. Once we solve this, one bracket we get, it's another GP, so with common ratio x, so 1 minus x raised to power, how many terms? N plus 1 divided by 1 minus x whole raised to power r, which is equal to 1 minus x raised to power n plus 1 whole raised to power r into 1 minus x raised to power minus r. Now, bache, if you know binomial theorem, then it's easy for you to understand how to find the coefficient of x raised to power n in this. If you don't, then I suggest that you study it up, because today is not the class we get into binomial expansion entirely, which is why I'm just going to tell you how to expand these, how to get the coefficient, but if you are not comfortable with it, you haven't studied that topic yet, then I suggest that you first study that topic and then it will be very easy for you to understand. This becomes very easy problem. So now in the first bracket we get 1 minus r into x raised to power n plus 1, and then we have rc2 x raised to power n plus 1 square and so on. We need the coefficient of x raised to power n. If we multiply x raised to power n plus 1 with any terms, here we are only going to have 1, then x and higher powers of x. If we multiply this with this, any terms in this with this, we will get x raised to power n plus 1 or n plus 2, like higher powers. We need x raised to power n. It is impossible to form x raised to power n from this. That means we will ignore all of these. Why will we ignore? Because it's impossible to form x raised to power n from any of these terms, so we will only consider 1. That means what will be the final coefficient of x raised to power n here? The coefficient of x raised to power n here multiplied by 1. So now our new problem is coefficient of x raised to power n in 1 minus x raised to power minus r. This is our problem, and there is a direct formula for this, that is n plus r minus 1 c r minus 1. So that is how we will get the same answer. Yes, of course we have to get the same answer, this is correct. But why did we do all of this complicated thing then? Because here we are assuming, but very carefully you have to remember the conditions. While memorizing any formula, it's very important to memorize the conditions as well. When can we use the formula? The condition is all of them go from 0 to n. Alright. Now, if that weren't the case, if there were some specific conditions, not every variable could be from 0 to n, in that case we will need this multinomial expansion. We will have to write all the possible cases and we'll have to see the coefficient of x raised to power n in this. So this is how we do it, bache. If this is new to you, if you're having difficulty understanding this, I suggest you go through this after the end of the class again, revise it, understand it in depth. If you don't know binomial yet, then I suggest you at least read some formula, some expansion, some basics of it, and then come back here. It will be very easy for you then. Alright. So now let's take a look at some examples. Okay. Try this. We have using any method, okay? I think you can easily do it using the formula. Just make sure that we can apply the formula. So what is the question? The number of ways of distributing 10 mangoes among 3 students without any restriction. All mangoes are identical. What's the correct answer? Very easy. Come on. Try again, bache. It's not A. See, I know we did a lot of complicated things, but this is very basic. The formula, you can apply the formula directly here. What do we have to do? We have to distribute 10 mangoes among 3 students. That means we need x plus y plus z is equal to 10. Right? Now, we have to distribute this among 3 students. So this is our equation. What is N? 10. What is R? 3. What is the formula? N plus R minus 1, C R minus 1. So the correct answer becomes, thank you, B. So, alright. When can we apply this formula directly? When we are talking about identical objects. Okay. Then it's just solving this equation. Another way of looking at it was, we have to just find the partition for the 3 students. So we will arrange these 10 mangoes and 2 partitions. So we arrange these 12 in total objects divided by 10 factorial for the 10 identical mangoes and 2 factorial for the 2 identical partitions. So this is nothing but 12C2. Whichever way you find more comfortable. Of course, that seems, I think, the most comfortable, the most easiest to understand, right? So, bache, whichever you feel is easiest to understand, but you should be able to apply at least one of these methods, right? So, that is how we can solve this. Okay. Now, find the number of ways of distributing 10 mangoes, 6 apples and 4 bananas among 3 students such that every student gets at least 1 mango. Try this one carefully. Think logically, do not try to rush the answer, okay? Let me get aside so that you can see the options. No, bache, D is not correct. Try again. No, carefully, carefully. Think very logically. C is correct, yes. And Dhairya, are you the one who attended my recent VIP session as well for greatest integer and calculus related thing? Is that? Because I know one Dhairya, but I'm sorry, I don't know your last name. Okay, but hi. I'm glad that you're attending this session. I hope you get to learn something here as well. Now, coming back to the question, C is correct. Okay. So, how do we do this? Now, it's a similar problem. We have to distribute 10 mangoes. We have to distribute 6 apples. We have to distribute 4 bananas. They're not related, they're independent. We first distribute the 10 mangoes and then it doesn't matter who got how many mangoes. We start again and see how many possibilities for distributing these 6 apples. And again, start again. We don't care what any student has got, we'll see how many possibilities for distributing 4 bananas. Alright, so, but the problem here is, first we have to see, okay, step by step. 4 bananas we have to distribute among 3 students. So 4 bananas plus 2 partitions. So 6 objects and 2 partitions. Or we can say x plus y plus z is 4. So 4 plus 3 minus 1, C 3 minus 1. So 6 C2 ways of distributing the bananas. Similarly for 6 apples, there are 8 C2 ways of distributing. Same way, right? X plus y plus z is equal to 6. So 6 plus 3 minus 1, C 3 minus 1. Same formula. Now we have a condition. For mangoes, if there were no condition, we could have directly done 12C2 how we did in the previous question, right? But now what is the condition here? The condition is that at least 1 mango should be given to all of the 3 students, which means x plus y plus z is equal to 10. In this equation, now we have a condition. Earlier, all of them could go from 0 to 10, 0 to 10, 0 to 10, right? But now each of them will go from 1 to 10, 1 to 10, 1 to 10, right? So that means now we cannot apply the formula directly. What we can do is, there are two ways of again looking at it. In combinatorics, there will always be multiple methods to look at it. So in this, how many ways can we do this? First, we give one mango to each of these. Okay, so we had these 3 students and we give them 1, 1, 1. How many do we have left? We have 7 left. Now we have to see the remaining x, the remaining y, the remaining z. Each has at least 1 now. Now the remaining x plus y plus z has to be equal to the remaining 7. Now x, y, z can be 0 as well, because we have made sure that they all get at least 1. So now x, y, z can go from 0 to 7. So that means this will be 7 plus 3 minus 1, C3 minus 1, which is 9C2. So instead of 12C2, we get 9C2. And because they are independent and we have to distribute mangoes and we have to distribute apples and we have to distribute bananas, so we will just multiply the 3 numbers. Why we were not doing this? Because this is excluding just one case out of all of those, right? We multiplied all of them and we're just excluding one case. But we're not just counting one wrong case. We're counting multiple wrong cases because what all cases we need to exclude? We need to exclude the cases where any one student gets a 0, gets 0 mango. Any one student. It can also, it's not just 0, 0, 10. It can be 0, 10, 0, 0, 1, 9. Even this, all of these are being counted. That should not be counted. So instead of checking how many cases are we miscounting, we will directly just give each of the student 1 mango and then distribute the remaining 7 mangoes. Alright. Now another way of solving such problems is x plus y plus z is equal to 10. We have a new condition. X has to be greater than equal to 1, y has to be greater than equal to 1, z has to be greater than equal to 1. Okay, so now we take a new variable which is equal to x minus 1. Now this is greater than equal to 0, right? Y dash, we also take y minus 1, which is also greater than equal to 0, z dash, which is z minus 1, this is also greater than equal to 0. So in order to make these x dash, y dash, z dash, we subtract x minus 1, y minus 1, z minus 1, and because we subtracted 3 minus 1s here, we also have to subtract 3 minus 1s here. So now our new problem becomes x dash plus y dash plus z dash is equal to 7. Now we can apply the formula directly. 7 plus 3 minus 1, C, 3 minus 1, that is 9C2. So in general, if any equation has this kind of conditions, then we can solve it this way. So now let's say if I had x plus y plus z is equal to 10, such that x is greater than equal to 1, y is greater than equal to 1, z is greater than equal to 2. Then what will be the answer? Use the same logic as this and answer in the chat. With practice, bache, with practice you can increase your calculation speed. But first of all, try to answer this question. The solution is literally up there. You just have to understand how we can form a new variable. All the new variable needs to satisfy is, the entire condition is, it should go from 0 to n. See, x minus 1 is greater than 0, y minus 1 is greater than equal to 0, z minus 2 is greater than equal to 0. So our new variables will be x minus 1, y minus 1 and z minus 2. So we'll make this here x minus 1 plus y minus 1 plus z minus 2. What all did we subtract in the LHS? 1, 1, 2, total 4. So we will also subtract 4 here. So this means x dash plus y dash plus z dash is equal to 6. So that means now we can apply the formula, because now x dash is greater than equal to 0, y dash is greater than equal to 0, z dash is greater than equal to 0. All of these variables can go from 0 to 6, 0 to 6, 0 to 6. Okay. So now we'll apply the formula directly. 6 plus 3 minus 1, C3 minus 1, which is 8C2. Good. So now, directly applying the formula and seeing what we did, let's just look at some more problems. So this we just did. Find the number of non-negative integral solutions of the equation. Non-negative, that means 0 or higher, right? Cannot be negative. It can be 0, 1, 2, but integer. Okay, so that means 0 or a natural number. So that is what the formula was for. 0 to 10, 0 to 10, 0 to 10. So we can directly apply the formula. 10 plus 3 minus 1, C3 minus 1, that is 12C2. Exactly the same problem as distributing 10 mangoes into 3 students. Now, positive integral solutions. Positive integral meaning natural numbers has to be greater than equal to 1. Now this is greater than equal to 1, this is greater than equal to 1, this is greater than equal to 1. Same as distributing the mangoes, distributing 10 mangoes into 3 students, but now what is the condition? The condition is that at least 1 mango should go to each student. That is what this condition means, that at least 1 should be given to each student, and then the rest doesn't matter. How do we do it? By taking another variable, x dash plus y dash plus z dash is equal to 10 minus 1 minus 1 minus 1, 7. So 7 plus 3 minus 1, C3 minus 1, that is 9C2. Okay. So this is how, without thinking of any objects, thinking of any partitions, any students, we can directly solve an equation where we can have integral solutions with certain conditions. Alright. Now, find the number of non-negative, so 0 or higher, integral solutions of the inequality x plus y plus z less than equal to 10. How do we solve inequalities? If this were equal to 10, we could have done it. Now, one possibility is that we count all possible things, right? X plus y plus z can be 10, which will give 12C2, 9, which will give 11C2, 8, 10C2, or because they are non-negative, it can go up to 0. So that means 2C2. So like this, and we can add them up. Clearly sounds like a lot of work. There must be another way of looking at it. There is. Now, x plus y plus z. We have 3 non-negative integers and their sum is always less than equal to 10. right? That means if we subtract 10 from x plus y plus z, we subtract x plus y plus z from 10, this will always be greater than equal to 0, because this is either equal to 10 or smaller. If we subtract this from 10, this will always be non-negative. It can either be 0 or a positive number. That means if we take this as w, if we take this variable as w, that means 10 minus x plus y plus z is equal to w, or 10 is equal to x plus y plus z plus w, where w can be greater than equal to 0. W can also go from 0 to 10, right? Because if x plus y plus z is 0, it is still less than equal to 10. In that case, w will be 10. So now each of these will go from 0 to 10. Now we can apply our formula. How do we apply the formula? Now we have n equal to 10, r equal to 4. Because now we have 4 variables. So n plus r minus 1, c r minus 1. So that is 13c3. Alright. So even if you added all of these, you would still get 13c3. But an easier way of doing this is by adding a quantity. If this is smaller or equal to 10, less than or equal to 10, that means if we add another quantity w, then it will be equal to 10. Whatever is missing, that is making it smaller, we just add that quantity. Now it can be 0 or 1 or up to 10. Alright, so like this we will solve such inequalities, and then it becomes our usual problem. This will count all possible cases. So number of non-negative integer solutions of x plus y plus 2z is equal to 20. Now we cannot apply our usual formula, right? Why? Because there is a 2 here. Even if we replace this by another variable, now it's not like it can go from 0 to 20. It will go from 0 to 20, but only even numbers, right? 0, 2, 4, 6 and so on up to 20. Not all possible natural numbers, right? So we cannot apply our formula directly. Even if we split it into 2 z's, even then there is a problem. Why? Because the first z and the second z have to be equal. But if we count all possible cases for these 4 variables, it is possible that this is 7, this is 5 and this will be counted. But that cannot happen. They have to be the same. So how do we do this? We do this using the multinomial expansion. So yes, answer is C. That is correct. That is correct, bache. Let's take a look how we can use multinomial every time and it will always give us the correct solution. Okay. So for the first 2, we have all possible 0 to 20 options, right? So now we have x plus y plus z dash is equal to 20, where z dash for x plus y, we have x raised to power 1, x raised to power 2 up to x raised to power 20. That is the possibility for both x and y. But for z dash, we have 1 plus x raised to power 1, x raised to power 2, 0, 2, then 4, then 6 up to x raised to power 20. And we have to find the coefficient of x raised to power 20 here. This is a GP, this is still a GP. What is this GP? This is simply 1 minus x raised to power 21 square 1 minus x raised to power minus 2. Here we have 1 minus x square. X square is the common ratio. How many total terms? 0 into 2, 1 into 2, 2 into 2, 10 into 2. So 0 to 10, 11. So in total we have 11 terms here, divided by 1 minus x square raised to power minus 1. Alright. Now we need the coefficient of x raised to power 20 here. X raised to power 20 here. Again, from here we will only take 1, because the other x raised to power 21 or x raised to power 42, they are all greater than x raised to power 20. So we will only take 1 from here, and we can ignore the rest of the bracket, rest of the expansion here. Similarly, here 1 minus x raised to power 22, from here as well we will only take 1. So now we have our new problem, x raised to power 20, the coefficient of x raised to power 20 in 1 minus x raised to power minus 2 and 1 minus x square raised to power minus 1. Correct? Is there any discussion? We can put z0 to 10, then solve every time adding them up. Of course, Vichi, that is what you can do. Of course, if you want to count all of the cases, you can. But the problem can be when it's a big number. We don't want to rely on manual counting. We have maths at our disposal. We have to learn how to handle the largest of numbers, right? That is why we learn this method. Of course, that is also correct. If you just put this 0 or directly here 0 then 2, so for x plus y you will have x plus y is equal to 20, so 21 ways. Then for 2 there is x plus y is equal to 18, that means 19 ways, and so on till 1. So this will be equal to 121. The sum of first 11 odd numbers, that is 11 square, that is 121. That is absolutely correct. But it's important to learn this method so that you can apply it in any scenario. Okay, you don't have to count all the possible cases. So now we have to just find x raised to power 20, the coefficient of x raised to power 20 in this expression, right? Here we again have to do some case handling, yes. Just a second, we are so again we have to do some hard work. If there is just one expression, then it becomes easier, but in this case we have 1 minus x raised to power minus 2, 1 minus x raised to power minus 1, 1 plus x raised to power minus 1. So that is 1 minus x raised to power minus 3 and 1 plus x raised to power minus 1. How do we solve such problems? Again, if you're new to binomial, multinomial expansions, you might be getting some confusion, which is why I suggest that don't start here. It will only confuse you more. Study binomial first and then look at these solutions. But coming back, 1 plus x raised to power minus 1 is this. Alright, 1 minus x raised to power minus 3. This is being multiplied and we need x raised to power 20. We need x raised to power 20 as a product, which means if we take 1 from here, then we need x raised to power 20 here. That will be 20 plus 3 minus 1. Right, 20 plus 3 minus 1, see 3 minus 1. Then we take 1 from here, x. Then we need x raised to power 19 from here. So, minus 19 c 21 c 2 plus x square. So, now we have 18. So, 20 c2 minus 19 c2 and so on, right? Now let's take a look at this. 22 c2 minus 21 c2. We have this 22 c2 minus 21 c2. If you know the property, bache, 21 c1 plus 21 c2 is equal to 22 c2. That will always be the case. If we have NCR plus 1, it will always be n plus 1 CR plus 1. If you don't remember the property, we can just expand this 22 factorial by 20 factorial 2 factorial minus 21 factorial 19 factorial 2 factorial. We take 21 factorial by 20 factorial 2 factorial common. What do we get from here? We only have 22 remaining because 22 into 21 factorial, that is 22 factorial. From here, we have to multiply it with 20 to get our 20 factorial in the denominator. So that means this 2 gets cancelled with this 2 factorial and we have 21 factorial by 20 factorial into 1 factorial or directly 21. So 21 C1 or directly 21. So from here we get 21, from here we get 19 and like this from the next 2 we get 17 until 1. So now we have, yes, the same kind of expression now, which is sum of all odd numbers. It's an AP where either you can say we have first 11 odd numbers which directly comes out to be 11 squared, or you can apply the formula of sum of AP, which is 11 terms by 2 into first term plus last term. So that is again 11 square, which is 121. But this is bache how you apply multinomial in any scenario. Okay, just have to keep expanding and checking how we can find x raised to power 20 here. I suggest you revise this after the class. It might be a little complicated for you if you're doing it for the first time, but if you know binomial expansion, then you must be able to follow all of it. All right. Now, last question of the day. This class went longer than usual, right? But it's an important topic. It's a very important topic even when it comes to IOQM or JEE. This is a very important topic, which is why we are taking enough time to understand this. Okay. Now, the last topic In how many ways can a 12-step staircase be climbed, taking 1 step or 2 steps at a time? That means we have a staircase. There are 12 steps. We can either take it 1 step at a time, or we can jump 2 steps directly at any point. At any point, if we are here, we can either go here or we can directly go here, take 2 steps at a time, jump 2 steps up at a time. Okay, so that means we have to count all possible ways of doing this. Now there are 2 ways of looking at this as well. First is, let's say while going, I took X single steps and Y double steps. So now X plus 2Y is equal to 12. But we won't just count how many possibilities of X and Y are there, because if this goes from, let's say 0, then 2, 4, 6 up to 12, right? Now for X, we know there's only one possibility. In each case, there's only one possibility for X. So 0 to 12, that means Y can go from 0 to 6. So total 7 cases. But that's not all the problem. For example, if we take 10 single steps and 1 double steps, that means that is not one case, because we don't know when we took that double step. We either took it at the very beginning, or after 1 single step, or after 2 single steps, or after 3 single steps. So that means we'll have to check each of these cases, right? So now we have to arrange these. So how do we arrange these? For this case, we have, well, one case, but how do we get there? 12 factorial by 12 factorial, 0 factorial. For this, we have 12 factorial, sorry, 11 factorial by 10 factorial, 1 factorial. How did we get this? Because we had 10 single and 1 double. So we had to arrange these. That means we arrange 10 plus 1 divided by 10 single are identical, and then 1. Similarly here we have 8 plus 2, 10 factorial by 8 factorial, 2 factorial. So what is this? This is 12C0, this is 11C1, 10C2, and like this we'll keep adding. So what is the sum? 12C0 plus 11C1 plus 10C2, 9C3, 8C4 plus 7C5 plus 6C6, and that will be the last case, right? Last case we have 0. That means we selected 6 double. Out of those 6, we have to arrange 6 factorial by 0 factorial, 6 factorial. So 6C6, and that is our last case. All 7 we have listed here. We just have to add them up. So we add them. 1 plus 11 plus 10 into 9 by 2, that is 45. 9 into 8 into 7 by 6, that is 84. Plus 8C4. 8 into 7 into 6 into 5 by 24. So that is, okay, now I have to write down. 8 into 7 into 6 into 5 by 24. So that is 70. Plus 7C5, that is also 7C2. So 21 plus 1. And we add these up. A lot of calculations, yes. We are checking ma'am's math calculations. So 12 then 57, 141, 211, 232, 233. Right? So this is one way of doing it, okay? One step at a time. Let me just go through it again, the entire solution. What did we do? We first checked how many single steps are there, how many double steps are there, and then we have to arrange them. So how many single steps and double steps? We first fix the double steps. So that means double step is 0 or 1 or 2 or 3 up to 6. And the remaining will be single steps. So 12 minus 0, 10, 12 minus 2, 12 minus 4 and so on. And then we have to arrange these x and y steps. So x plus y factorial, cy or cx. Okay. So this is one way of looking at it. Another way of looking at it, a very important thing to learn, bache, if you're preparing for the Olympiad, is a way of writing such cases. Now we don't know how many possible cases are going to be there up to 12, but we know that if we had these 12 steps, then for any point, let's say this is the 12th step, to reach here I could have taken either, this is 11th, this is 10th. I could have taken either a direct jump from 10th or a direct jump from 11th. So let's say there are T12 ways of reaching the 12th step. We can say that this is equal to either we take one step from 11th. So in how many ways could we reach 11th step? T11. Okay, so there were T11 ways of reaching the 11th step. We can, if we have reached here, then we can just take one step and 10, 11 into 1. Or we can come from T10. From 10 steps, so that means once we have taken T10 ways of reaching 10th step, then we just have to jump once. So there's exactly one way of reaching 12th step from 10th to 12 directly, or we can go 11 and then we can come from 11. Okay, so that will be true for any step. For nth step, it can either come from n minus 1 or it can come from n minus 2, and we will add all the possible ways of reaching this or this, and then this will be the total number of ways of reaching nth step. So for example, what is T1? We started from 0th. How many ways to reach the first step? We have to take a single step. How many ways of reaching second step? We can either jump from first step, we can go from 0th to second, or we can go from 0th to first, then first to second. So there are two ways of reaching the second step, right? Either we go directly, we are on the 0th step. So we either jump directly to second or we take it one step at a time, right? Exactly two ways of reaching second step. Now that means for T3, how many ways are there? We are saying it has to be T1 plus T2. But let's confirm where we are getting this from. Let's say we were at 0th step, and then this is first, this is second, this is third, right? We can either go this way one step at a time. This is one way, right? This is exactly one way. We go from 0 to 1, 1 to 2, 1, 2 to 3. This is one way. Another way is we go to 0 to 1 and then directly from 1 to 3, or we go directly to 2 and then to 3. That means once we have reached the second step, either the yellow route or the green route, once we have reached the second step, there is exactly one way of reaching the third step. And how many ways of reaching the second step were there? Either the yellow route or the green route, which were the two ways. If you forget about the third step, there were two ways of reaching the second step. Right? There were two ways of reaching the second step. That means after we have reached, there's only one way of reaching the third step. Or if we are not going to second step, we are coming directly from first, then how many ways were there of reaching the first step? There was only one way. So either we take the orange route or we take yellow or green. Now, bache, you might say that once we have reached the first step, there are still two ways of going to the third step, right? We can either go to second and then to third, or we can go directly to third. But if we are counting that step again, if we are going to second again, then we are counting it twice. We don't want to repeat any case, right? So that is why once we are checking the last two steps, we are either checking that you take a single step to reach here, or you take a double step to reach here. So if you take a single step to reach the nth step, that means there are Tn minus 1 ways of doing it. If you take a double step to reach to Tn, that means to nth step, that means there are Tn minus 2 ways of reaching the nth step. Okay, so this is called a recurring relation. So like this we can find all Tn's, and finally we need to find T12. So T1 is 1, T2 is 2, T3 is 3, T4 is, we just have to add the last two and we get the next one. So 2 plus 3, 5, T5, 3 plus 5, 8, T6, 5 plus 8, 13, T7, 8 plus 13, 21, T8, 13 plus 21, 34, T9, we add these, then T10, we add these two, so 89, and T11, 144, T12, 233, which is what we were counting. How many ways of reaching 12 step are there, which is what we found in our previous method as well. So both methods are correct, both methods are giving the right answer, but it's important to know both the methods, understand both the methods, so that you can apply any of these in your problems. Sometimes this might be helpful, more helpful, sometimes the other one might be more helpful, so you have to know everything to score the best you can. Okay, if you study half of the syllabus, if you study half of the methods, then you are only aiming for half of the solutions, half of the correct answers. But if you study everything there is to study, then your chances, your probability of scoring maximum marks increases. Okay, so we learned a lot of new things today, I'm sure, for a lot of you. So I will suggest that you go through everything again so that you understand it for life. Even if you understood everything in this class, I'm very happy. If you understood everything, you're on the right track. But this is my one tip forever. For every class you attend, not just with me, but with any teacher of any subject, it's very important to revise. That makes sure that you remember everything. Even if you think you remember right now, even if you think you will remember it for a few days, but their chances of forgetting increases if you don't revise. So as soon as you revise, it's just the human brain, that's how it works. As soon as you revise, it retains better. So take it from me, it is always better to revise. That makes sure that you will never forget this even after years. So today we are going to be covering 3 small topics, fairly easy. Just again, like always, we have to understand everything very logically, nothing to memorize. Yes, it helps to memorize the formulas, but it definitely helps more when you understand how you're getting the formulas, because there might be exceptions to that formulas, and the only way to actually get the right answer is by knowing where the formulas are coming from, right? How to derive those formulas, how did we come up with the formula. So just like that, we are going to be covering 3 topics today. The first is sum of all possible numbers using given digits. Then we will see exponent of prime in any big number. How do we calculate that? And finally, we are going to see, as the title says, select non-consecutive objects. So earlier we learned how to arrange the objects in such a way that certain objects are never adjacent to each other. We were arranging. Today we are going to learn how to select non-consecutive objects. We cannot select any 2 adjacent objects. So alright, let's begin. Yes, this is entirely in English. Okay, so let's start. The first topic is sum of all possible numbers. In one of the first classes, we saw how to calculate the total possible numbers using the given digits, right? For example, this simple problem, find the, let's forget the sum for a bit, all the 3-digit numbers that can be formed using 1, 2 and 3 without repetition. So how many options, how many possible numbers do we have? 3 factorial, so 6, right? 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. These are all the possible numbers we can get using 1, 2 and 3 without repetition, all the 3-digit numbers, right? Now we have to add these. Now we have to add all of these. So if you look at this, there are in each column 2 1s, 2 2s and 2 3s, right? In each column we have exactly 2 1s, 2 2s, 2 3s. That means total 6 possibilities for each column, right? So what does this sum up to? 2 into 1 plus 2 into 2 plus 2 into 3. That is 12. If you take 2 common, this becomes 2 into 1 plus 2 plus 3. So we get 12, right, for each column. That means if we add this, we get 12 and 1 is carried over, then 12 plus 1 13 plus 1, then 12 plus 1 13. So this is our final answer. Of course, like always, we cannot list all the possible numbers directly. We need to be smart about it. So let's break it down. How did we reach 1332? We had 12. We just had to multiply it by 111, right? 12 into 1 plus 12 into 10 plus 12 into 100. For each column, for each digit, we had to do this, right? Now where did we get this 12 from? We got it from 2 into 1 plus 2 plus 3 into 1 plus 10 plus 100. So we know 1 plus 10 plus 100 is because we have a 3-digit number. So we went from 1's digit to 100's digit. We have 1 plus 2 plus 3 because these are the 3 digits that are given to us. What is this 2? 2 is for each digit. How many possibilities are there? If we fix this 1 digit for this 1, how many possible numbers can we make? 3 minus 1, 2 factorial, right? For each digit we can have 2 factorial numbers, right? We fix 1 digit anywhere and we get n minus 1 factorial numbers for that digit. So that means this becomes n minus 1 factorial into sum of all digits into 1 plus 10 plus 100 up to 10 raised to power n minus 1, right? Because we're starting from 10 raised to power 0, then 10 raised to power 1, 10 raised to power 2 up to 10 raised to power n minus 1. And this is the formula that we get. So if it is a straightforward question where we have all distinct digits, right? And we can form n factorial numbers here, then we will just calculate this way. N minus 1 factorial, because for each digit we have n minus 1 factorial options. You can also look at it this way, that the total numbers are n factorial. How many digits are there? N digits. So for each digit we get n factorial divided by n, right? Which is n minus 1 factorial. So you can look at it any way, it's the same thing. N minus 1 factorial for each digit multiplied by sum of digits multiplied by 1 plus 10 plus 100 up to 10 raised to power n minus 1, right? Depending on how many digits we have in the number. Clear? Now, find the sum of all 4-digit numbers that can be formed using the digits 1, 2, 3 and 4 without repetition. Same as before, we can directly apply the formula here because the digits are distinct, the number of digits is 4 and we can have 4 factorial numbers here. So, 4 minus 1 factorial into sum of all digits into 1 plus 10 plus 100 plus 1000, or you can directly write 1111 for each digit. Alright, so this is 3 factorial into 10 into 1111, that is 60 into this, which is this. Okay, but what if now there's a slight variation? Now we have to form 3-digit numbers using 1, 2, 3 and 4. How many such possibilities are there? We first select which 3 digits to take, 4C3, and then we arrange them. So 4 into 3 factorial 24, or you can look at it this way, that we have to fill these 3 spaces, 4 options for this, 3 options for this, 2 options for this. So 4 into 3 into 2, 24. Right, simple. Now, but now we have to find the sum of all digits, right? So let's assume we have the 3 digits. We have selected which 3 we are going to take and which one we are going to leave, right? We can leave 1, we can leave 2, we can leave 3, or we can leave 4. We have 4 options. We will either skip 1, or we can skip 2, or we can skip 3, or we can skip 4 and take the remaining 3. Now, let's say for example, right now I have chosen which 3 digits I am going to take. Let's say it is 1, 2 and 4. Now for this case, I will take the entire sum as number of digits. So it's my previous question, right? The 3-digit numbers using these 3 digits. 3 minus 1 factorial into 1 plus 2 plus 4 into 111, right? Now let's call this S3 because we left 3, right? So this becomes 2 into S3 into 111. S3 because we skipped 3. Just like that, we are going to have 4 sums 2 into S1 into 111, 2 into S2 and 2 into S4 111. Right? Now what is the sum of S1 plus S2 plus S3 plus S4? S, if S is the total sum, alright? If S is 1 plus 2 plus 3 plus 4, then S1 is S minus 1, S2 is S minus 2 and so on. So S1 plus S2 plus S3 plus S4 becomes 4 times S minus 1 minus 2 minus 3 minus 4, which is again S. Right? S1 is S minus 1, S2 is S minus 2. So we'll add all of these. 4S minus so finally that is 3S. So taking 2 and 111 common out of this, we get 2 into 3 into sum of digits into 111. So 60 into 111, that is 6660. Okay? But if you, no, it is not recording. If you think that these are very easy questions for you, that's amazing. I'm very happy for you. I'm very proud of you that you have such a great prep already. You find this very easy. But whenever we are studying, whenever we are learning a new topic, then we have to start from the basics, because that is where we get the best understanding. Okay? So do not worry, this course is going to cover all the questions. In the end, we are going to have as many sessions as it takes to just practice difficult questions. Trust me, we are going to get there. And then I know you all will be complaining, ma'am, this is too hard, ma'am, this is too confusing. We will do it. Okay? We will understand everything there as well. But in order to do that, we have to understand every formula, where it's coming from, how we can get to the answer every single time. Okay? Yes. So if you see, this is similar to the previous question, 60 into, except the number that we were multiplying it was 1111, because it was a 4-digit number, and in this case it's a 3-digit number, so 111. Do not memorize, just understand logically how we can do it. Now what if one of the digits was 0? We have to form 4-digit numbers, so 0, 1, 2, 3. Now how many numbers can we make? Forget about the sum for a second. And how many 4-digit numbers can we make? Come on, quick, quick, quick. No, not 7. Come on, you can do this. Especially the students who were complaining that this was an easy question. Come on, what is the total number of numbers that we can make? Three into 3 into 2 into 1. Thank you. So we have 3 options for this, 3 options for this, 2 options for this, 1 option for this. So this is 3 into 3 into 2 into 1, 18. Or we can look at it that we have 4 factorial, we arrange all of them and we exclude the numbers where 0 was in the leftmost place. So how many such numbers? We fix 0 and then we have 3 factorial. So 4 factorial minus 3 factorial, that is 18 again. Of course, we will get the right answer if the method is correct. So you can take a look at both the methods. You should understand both the methods, because in this question we are going to use this one. Why? Let's see. We need to find the sum of all 4-digit numbers that can be formed using 0, 1, 2 and 3. The only condition is, in order for this to be a 4-digit number, 0 cannot be here. So let's first find the sum the old way. Let's assume 0 can be here. Okay, so the total will be 4 minus 1 factorial into sum of all digits 0 plus 1 plus 2 plus 3 into 1 1 1. This is the total. Now this is also including which numbers where 0 is in the leftmost position. Let's subtract the sum of all such numbers. So once we fix 0 here, what do we get? We have all the 3-digit numbers using 1, 2 and 3. Right, that's the sum of all such numbers. So that will be 3 minus 1 factorial into 1 plus 2 plus 3 into 1 1 1. And here you go. That's your final answer. If you want to calculate 3 factorial, that is 6 into 6 into 1 1 1 1 minus 2 into 6 into 1 1 1. So we take 12 common. From here we are left with 3 3 3 3 minus 1 1 1. That is 12 into 3 2 2 2. So whatever you get here. Okay, so this is how you can approach the problem very easily. These are just two simple problems, and then we take all possible cases and we remove the cases that we do not want. Just make sure that you're removing the sum and not just the cases. Just focus on your studies, bache. It's okay. You will have some students who are not here to study. That's okay. Just understand what is going on here. Reply with the answer in the chat. I'll look at your answer. Okay. So clear? This is how we can take care of such cases. Let's see another case. Find the sum of all 4-digit numbers that can be formed using 1, 1, 2 and 3. Let's go back to our how many numbers can we make using these 4 digits. We arrange all of these and we divide it by the repetition number. So this comes out to be 24 by 2, 12. Right? We have to find the sum of all these 12 numbers. So we are going to use the similar approach. I suggest you look at this in general. If you are struggling to find the sum, if you can't think in the beginning, you know, how to find the sum of all such numbers, then take this approach. Find the number of numbers that can be there, see how we were calculating, and then find an idea on how we can use the same thing to calculate the sum. For example, here we take the entire sum. The entire sum is 4 minus 1 factorial into 1 plus 1 plus 2 plus 3 into 1 1 1 1. This is the entire sum. But we are counting each case 2 factorial times. That is why we divided the entire thing by 2 factorial, right? Because we were counting every number 2 factorial times or 2 times or twice. So that means even the sum will be double what we wanted. So we will just divide it by 2 factorial. And finally we have 3 factorial 6, 1 plus 1 plus 2 plus 3, 7 into 1 1 1 1 by 2. So this comes out to be 21 into 1 1 1 1, that is this. Perfect. Right? Easy? So this is how we can apply the same thing in various situations. Just understand how we were calculating the total number of numbers, how it's going to affect the sum What were the repetitions here? Remove those. What were the cases that we were excluding? What were the cases that we were supposed to remove? Just do the same thing here and you'll have your answer. Now, the next type of questions that we're going to cover today is exponent of prime. Okay, exponent of prime, that means in a large number we need to find what is going to be the power of a given prime number in the prime factorization of that big number. So, for example, let's say we have n factorial. Okay, we have n factorial, a given number n, it can be anything, and we need to find for a given prime number p, what is going to be the power of this prime number p when we write the entire prime factorization of n factorial, not n factorial. So, bache, let's understand this using an example first. We have 10 factorial. Okay, so here we have 10 into 9 into 8 into 7 up to 1. We need to find the power of 2. Okay, so we write the prime factorization. What all prime numbers will be here? There will be 2, 3, 5 and 7, right? Because 1 to 10 all the numbers are here, so all the prime numbers up to 10 will be here. 11 won't be here because 11 is not smaller than 10, so 11 is not included here. All prime numbers up to 10 will be here. Now, let's say we need to find this alpha. We write the prime factorization like this and we need to find what this alpha is, or this beta, or the gamma, or the delta. So, let's first take a look at 2. Okay. How many 2's will be here? Where are we getting these 2's from? We are getting 1, 2 from here. We are actually going to get 1, 2 from all the even numbers, right? Every even number will at least give 1, 2. I have 1, 2. Every even number has a 2. I will give my 2 to you. So, every even number is giving 1, 2. So, we will write, but I hope you know what this symbol is. This is greatest integer. This means if we are writing 10 by 2, greatest integer, that means the greatest integer, the largest integer, that is either equal to this quantity between the brackets or just smaller. Okay, the largest integer possible, which is either equal to or smaller than this. For example, if we have greatest integer 7.7, that is 7. Greatest integer 9, that is 9. Either equal to or just less than that quantity. Coming back here, so that means however, like the total number of even numbers here. What is the total number of even numbers? We divide this by 2 and take the greatest integer, because it will be an integer, right? It will be a natural number. How many even numbers are here? That will not be a fraction. There will be a fixed integral answer to this question. So, that means we have here 1, 2, 3, 4, 5. Where did we get this 5 from? Because 10 divided by 2 is 5. Now, that's not all the 2's that we are going to get. We are also getting another 2 from all the multiples of 4, right? All multiples of 4 will have one extra 2 to give. When this 2 gave its 2, now only 1 was remaining. When 6 gave away its 2, only 3 was remaining. But when 4 gave away its 2, there was still an even number remaining. It was still 2. It could still give one more 2. So, every multiple of 4 will give its 2. So, now how many multiples of 4 are here? 10 divided by 4, which is 2.5. Now, of course, there are not 2.5 multiples. The greatest integer, the integer just smaller than 2.5, 2, 4 and 8. So, 10 divided by 2 square, 4, and its greatest integer, so 2. Now, is that all? No, because even though when it gave away its second 2, now there was only 1 remaining. But when 8 gave away 2 of its 2's, there's still 1 2 remaining. It can still give 1 2. So now there will be, that means there will be 1 additional 2 in the prime factorization. Where is this 1 coming from? How many multiples of 8 are here? Same as before, 10 divided by 8 or 2 cube and its greatest integer. 10 divided by 8 is 1.25 and we just take its greatest integer. Only 1 is the answer. So 5 plus 2 plus 1, that is 8. Okay, so that is how we can calculate any prime numbers exponent in any numbers factorial. We just keep looking at this until the prime number raised to power 4 became greater than 10. We are not checking 2 raised to power 4. Why we are not checking 2 raised to power 4? Because 2 raised to power 4 is greater than 10. That means anything after this will be 0, right? 10 divided by 16 is 0 point something, greatest integer 0. 10 divided by 32, 0 point something, greatest integer 0. So we are not counting any further. Everything else after this will be 0. So we will stop here. Alright. So the general formula becomes n by p, greatest integer, then n by p square, greatest integer, n by p cube, greatest integer, n by pk, until it is non-zero. As soon as you get a 0, you stop there. Okay. So as soon as the p raised to power k becomes greater than n, you stop there. Alright. So a quick application. What will be the exponent of 3 in 10 factorial? Very good. So E3 in 10 factorial will be 10 by 3 plus 10 by 3 square. Now the next 27 is greater than 10. So we'll stop here. So 3 plus 1, that is 4. Right? Clear? Now try this one. Exponent of 7 in 100C50. There's no factorial here, so we can directly not use that formula, but maybe we can use this application. Carefully, logically think about it. I'm still not seeing a correct answer in the options. Still keep trying, bache. Yes, 0 is the correct answer. Very good. So let's take a look. What was the formula? N by p square, n by p cube for n factorial, right? So E7 in 100 factorial is 100 by 7 greatest integer plus 100 by 7 square greatest integer, and then 7 cube is 343, which is greater than 100, so we stop right here. Okay, so 100 by 7, that is 14 point something, because 7 into 14 is 98, so we get 14 here, and 49 into 2 is 98, so 2 here. So 16 in 100 factorial. Now what is 100C50? 100C50 is 100 factorial divided by 50 factorial. 50 factorial. The exponent of 7 in 100 factorial is 16. That means 100 factorial is equal to some k1 into 7 raised to power 16. Correct? Similarly, we'll count for 50 factorial because we also need that here. So 50 factorial by same logic, 50 by 7 plus 50 by 7 square, and we stop here. So 50 by 7, 7 plus 50 by 49, 1, so 8. That means 50 factorial is k2 times 7 raised to power 8. This k1 and k2 does not have any 7. It's some other prime numbers and some other prime factorization, but 7's exponent, because we only care about 7's exponent, so it is 7 raised to power 16 and 7 raised to power 8. Now coming back here, that means this becomes 100C50 becomes k1 into 7 raised to power 16 divided by k2 into 7 raised to power 8 whole square. So we are going to ignore k1 by k2 square. These do not have any 7's. This becomes 7 raised to power 16 minus this. Just using exponent rules. So 16 minus 16, 0. That means there will be no 7 in the prime factorization of 100C50. So k1 by k2 square into 7 raised to power 0. So there is no 7 in this part, there is no remaining 7 in the other part. So the correct answer is 0. Okay. So very logically we have to use the formula. Now, how many zeros are here at the end of 108 factorial? That means, how many zeros? What does that mean? Exponent of 10. Okay, exponent of 10. But 10 is not a prime number. Remember, the formula was for prime number. That method only worked for prime numbers. So what is 10? 10 is 2 into 5. That means there will be some 2's and some 5's. We are going to take same number of 2's and 5's out of those, and we are going to get a 10 from each pair of 2 and 5. Now how many pairs can we make? How many pairs can we make? The minimum number out of those two, the smaller number, we will have clearly, because 2 is smaller, we'll have more 2's, 5 is larger, so we'll have less 5's. So that means, remember, that is very important. We'll have more 5's and less 2's, so we have to only check exponent of 5. Exponent of 2 will always be greater than 5's exponent, because 2 is smaller, there will be more 2's there, right? But exponent of 5 will be smaller, so that is the maximum pairs we can get. More than that, it's impossible to make, right? We can only make those many pairs of 2 and 5. So that is our problem. Now we know the answer. 108 by 5 plus 108 by 5 square, and then 5 cube is 125, that is larger than 108, so we stop here. So this is 21, this is 4, so the answer is 25. Okay, so whenever we have to find exponent of a composite number, we are going to split it into the prime factors, and we'll see how many pairs, how many combinations we can make depending on what the larger number there is. Okay. Now, the last category for today. I think the first two were fairly easy. Even this is easy as soon as you understand how to approach such problems. So, the third category for today, the third type of questions, the last type of questions that we are going to understand today, they seem to be very tricky, but it is actually very easy once you learn how to actually solve them. So what is the type of question? What are the questions that we are looking at? We're looking at selecting non-adjacent, non-consecutive objects. We are given some objects, they are placed in a certain order. We have to pick some out of them. Okay, we are given n objects, we have to take r out of them, NCR. That was the original thing. Now there's a condition there that we cannot pick a consecutive, any two adjacent objects. If we have picked the second number, that means we cannot pick the object on the first number or on the third number, right? That is our problem. So the simplest way to do it is by assigning them 0 or 1. Okay, if we take them, we give them a 0, we don't take them, we give them a 1, something like this. Just any order, you can give 0 to one kind and 1 to other. So we call it binary equivalent, right? In binary we have zeros and ones and that's it, right? If it is true, we give it 1. If it is false, we give it 0. That is what binary is. The same way we are going to look at the problem here. So for example, let's look at an example. It will be very clear in just a minute. The question is, how many ways can 4 trees be cut from 10 trees in a row such that no 2 trees cut are consecutive? Okay, it is not possible that we cut this and this. These are consecutive, we cannot do this. So that means we have to select 4 trees out of these 10 such that no 2 out of those 4 are adjacent to each other. Another problem, another way of looking at this problem is, we are assigning 0 to the tree which is being cut and 1 to the tree that is still going to be there. Okay, so that means we are going to have 6 ones and 4 zeros. Right? For example, let's take a look at this arrangement of ones and zeros. We have this 0, this 0, this 0, this 0. We can see that no 2 zeros are adjacent to each other. We have 4 zeros and 6 ones. So we will cut these 4 trees. Or if we take a look at this one, we again have 4 zeros, no 2 zeros are adjacent to each other, and we cut this, this, this and this. So every unique arrangement of ones and zeros will give us a unique answer for our problem, unique selection. Okay, so now it's a very simple problem. It's just the gap method, right? We first arrange the ones. How many arrangements? In this case, because they are identical, there is only one arrangement, right? We have 6 ones, we just arrange them 1, 2, 3, 4, 5, 6. We place these 6 ones. There's only one possibility of doing this. Now we have to insert zeros between these gaps. How many gaps do we have? 6, 1, so 7 gaps. 6 plus 1, 7 gaps, and we have to select 4 gaps out of these 7. So 7C, 4, and that is your final answer. So instead of selecting 4 out of 10 and looking at the cases where they could be adjacent, we can simply do it in the opposite way. We make arrangements of ones and zeros. Okay, let's take a look at another application of the same thing. An engineer has to visit a factory for exactly 4 days during a period of 15 days. Okay, every month within the first 15 days, the engineer has to visit 4 times on 4 days, and it is mandatory that no 2 visits take place on consecutive days. Basically, out of those 15 days, the engineer has to select 4 days, and such that no 2 out of those 4 days are consecutive, are adjacent to each other in that arrangement. Number of all possible ways that they can do it is, we place all the ones first. How many ones? 4 zeros and the remaining 11 ones, right? We place all the 11 ones first, only one possible arrangement to do that, and then 12 gaps, 11 plus 1, 12 gaps. Out of those 12 gaps, we have to select 4, and that is your final answer. Alright? So, very easily you can do it. Just you have to transform the problem. You have to take a look at the problem from another angle, and then it becomes super easy. Okay? Clear to everyone? Alright. Now let's take a look at this problem where it's a circular arrangement. Now instead of a linear arrangement, we have 10 people sitting around a circle, and they are people, they're not identical, they are 10 different people sitting around a table. We don't have to find the arrangements, right? They're already sitting here. There are 10 people around here, they're already sitting. We just have to pick 3 out of these such that no 2 out of those 3 are sitting adjacent to each other. If we pick P1, then we cannot pick P2 or P10. Okay? So, just try it once and then we'll discuss the solution. Yes, 50 is the correct answer. Yes. So, 50 is the correct answer, bache. 35, I know. If you, let's see. What if, again, we have the same thing, right? We have to arrange zeros and ones. How many zeros, how many ones? Let's say we are giving 0 to the people who are not going to be here anymore. The 3 people that we have to select. Okay? So, 3 zeros and 7 ones. If we just arrange these 7 ones and 3 zeros around a circle, then you might say that we first place all the ones, and then out of the remaining gaps, 7 gaps, because it's a circular arrangement, so out of the remaining 7 gaps, we will select 3. And this is 35. But this is wrong. Why is this wrong? If we placed 1, 1, 1, 1, 1, 1. We arranged in a certain order 1. Now once there was only one order for the 7 ones, right? Now you're inserting zeros here. Let's say I want to insert a 0 here. How can I do it? I already placed the 1. Or if you're saying, ma'am, just shift it by 1, then there are a lot of cases for each of them, right? If you're shifting, you will have to consider, can we shift it? How do we shift it? So that is why we're not counting all the cases. So bache, the student who got the answer as 35, that is why it is not correct, because we have to see the placement here is not identical because they are different, distinct 10 people. So how do we actually calculate? One way of looking at this is we fix one person, okay? This one, the one sitting in the, we number all the people, and the first person, we take 2 cases for this first person. Case 1 is, P1 is not selected. Okay, that means we are giving this P1 a 1. Now it's a linear problem. right? Whichever arrangement we have of the remaining 6 ones and 3 zeros, the linear arrangement, we just place it here, right? As soon as we fix the answer for this one, now we just arrange the remaining 6 ones and 3 zeros, and we will have a unique arrangement for this particular case. So what will be the arrangement? We arrange the 6 ones, that's only one possibility, and then 7C3. So that is now 35. Now let's take a look at case 2. When P1 is not selected. Okay, that is P1 gets a 0. Now it's not the same as arranging 7 ones and 2 zeros. If we arrange 7 ones and 2 zeros, it is possible that we get a 0 here. That is not possible. So that means we have to impose the condition that adjacent to this P1, P2 and P10 cannot be selected, which means P10 will be a 1, P2 will also be a 1. Because these two cannot be selected. As soon as we selected P1, we made sure that P2 and P10 cannot be selected. Now, for the remaining P3 to P9, this is a linear arrangement. Now we arrange these in any way we want and we will get a unique answer. So now how many ones and zeros do we have? We took 2 ones, so we have 5 ones remaining. We took 1 zero, so we have 2 zeros remaining. So we place the 5 ones. Out of the 6 gaps, we place 2 zeros. So 6C2, that is 6 into 5 by 2, that is 15. And now only these two cases are possible. Either P1 is selected or P1 is not selected, right? And for each of these cases, we counted the total number of possibilities. So 35 plus 15, the answer is 50. Okay? Yes, Vichit, this is very helpful for JEE as well. Okay, so that is how we can actually apply all the same things in different scenarios. Just be very careful. Can we apply this? Are we sure we are counting all the possible cases? Are we sure we're not missing any case? Are we sure we're not counting any case? Again, I keep repeating this in every class, but that is all what this chapter is about. You just have to make sure you're counting all the cases, and that's it. It's just different ways, different methods of making sure that you're counting all the cases. Okay? So, today we are going to just stop the class here. Yes, we ended the class earlier today, but we did learn a lot of new things today, a bunch of different methods of solving these things. In the next class, we are going to do inclusion-exclusion principle. We are going to start with inclusion-exclusion, and then we're going to look at one of its applications, derangements, where none of the objects can be in their original place. So we're going to see all of that. Again, very logical, just have to understand. So we will actually look at this problem again from a different angle, and we're going to reach the same answer. Of course, if the method is correct, you're going to get the same answer. So without wasting any further time, let's start. So this was the last question that we did in the previous class, right? Find the number of ways of selecting 3 people out of 10 people sitting on a round table such that no 2 people selected are consecutive. Alright, so how did we solve this? We assigned, there were 1, 2, 3, 4 like this, 10 people sitting around a table, and we assigned them ones or zeros. If we assigned this person 0, that meant that we are not going to select this person, or we are going to select this person. And if we gave this person a 1, that meant that we are not selecting this person stays here, right? This was how we did it. We divided it into 2 cases. One case that we select this person, one case we do not select this person, and based on that we got our final answer. Correct? Now, let's take a look at this from another way, a familiar way. Whenever we had to, let's say, solve a problem where no two A's are adjacent, we can either fill these two A's between the gaps, or we can check how many cases do we have when these two A's are adjacent and remove those cases from the entire total cases, right? So basically what we do not want here, what do we not want? We do not want to select consecutive people. So we are going to check how many ways are there to select consecutive people, and then that's it. We can just remove those cases from the entire set. What are the total number of ways of selecting 3 people out of 10 people sitting around a round table? Without any condition, we know the answer is 10C3, right? 10C3 ways of selecting 3 people out of 10 given people. Now, how do we find the cases that we do not want to include? We want to exclude. So that is where inclusion exclusion is coming from. What do you want to include? What do you want to exclude? So here I want to exclude the cases where any two adjacent people are selected. Okay, so again, number of ways of counting that. I will do it in this way, that I first check number of ways of selecting 3 adjacent people, and case 2 will be 2 adjacent, 1 non-adjacent, right? If we cover both of these cases, then we are counting all the possible cases where 2 adjacent people are selected. So now, how many ways are there of selecting 3 adjacent people? Let's say I start from this person and go in a clockwise direction. This is my first person, second and third. This is one case. If I start from, let's say here, and go in the clockwise direction, then 1 person, 2 and 3. So as soon as we fix the first person, and another way of looking at this is, let's say I'm choosing this, this and this. These 3 persons that are marked with blue, these are the 3 adjacent. I want to see, how do I make sure that I include this? I only count the first person and then go clockwise. So as soon as I fix the first person and go in the clockwise direction, I know which 3 adjacent people to choose, right? So that means all I need to count is how many ways can I fix this first person. And how many ways can I fix this first person? 10. Because out of all these 10 people, I can fix any one of them, and as soon as I fix them, I get 3 adjacent people. So that means case 1 has 10 possibilities. There are 10 ways of selecting 3 adjacent people, because as soon as you fix one person, you get a unique possibility, a unique arrangement, because you're only going in one direction. If you were counting both the directions, then you would see repetitions. Okay, so that's something we have discussed in previous classes. In case of a circular arrangement, fix the direction to avoid repetitions. So I fixed the direction, clockwise, anti-clockwise, whatever you want it to be, and then I have unique arrangements. Coming to the second case. In the second case, I want 2 adjacent and 1 non-adjacent. Just like before, I can have 2 adjacent in the same ways, right? I'll draw the circle again. So now, as soon as I fix the first person, I know which 2 adjacent I'm talking about. right? I go in the clockwise direction and I know which two adjacent people I'm talking about. If I fix this person, then I'm talking about these two. If I fix this person, then I'm talking about these two. So as soon as I fix one person, I know which two adjacent people I'm talking about. Now comes the third person. So that means I can select this in 10 ways, right? Now for each of such pairs, we need one non-adjacent, right? So that means this person cannot be included, this person cannot be included, because that will be adjacent to this, that will be adjacent to this, and that is something we have already counted. It's not like that is allowed. That is also not allowed, but we have already counted 3 adjacent. Now we are talking about 2 adjacent and 1 non-adjacent. So that means this person cannot be counted, this person cannot be counted out of the remaining 6, right? 1, 2, 3, 4. These 4 are just removed from the selection pool. Out of the remaining 6, we can select anyone, right? We can select any one of them and we will get a unique case of 2 adjacent and 1 non-adjacent. Okay, so that means for each pair we get 6 C1 options. So in total 60. Now our original total number of cases, the total number of cases that we had was 10C3. 10C3 is equal to 10 into 9 into 8 divided by 3 into 2 into 1. So this comes out to be 120. Out of these 120, we have to remove 10 plus 60, that is 70. So the final answer is 120 minus 70 equals 50. Same answer, of course, the same answer. That's the whole point, right? If your method is correct, you are going to reach the same answer. There is only one correct answer, but there can be multiple correct methods. So, of course, you can choose any of those methods and they are fine. But all I want you to understand is if your mind started thinking of this, because I know right now we're studying topic by topic, you're looking at questions one by one, you're looking at a topic, some theory, and then you're looking at a question. Then you know how to apply it, which method to apply, how to solve that question, right? But what if you see this question out of nowhere? You don't know in that case which method to apply. You can think of multiple methods. You don't know which one to apply, but the first method you think of, you want to see, can I get the correct answer through this method? So for example, if you saw this question and you're thinking, I want to select 3 people such that no 2 people selected are consecutive. Let me just count. It makes sense that I can just count how many consecutive people I can select. I can use the bundle method, right? And then I can probably just exclude those cases and I'll have my answer. So I wanted to tell you how you can actually use this method. This will take just as much time. I took more time to explain this because this is the first question today, and this might be new theory for a lot of you students here, but this is very important, very simple sometimes. But sometimes it can happen that only one method gives you the right answer, the other method, not because the method was wrong, but because you missed something, it became harder to make sure that you're counting only the unique cases. So that is why it's very important to understand all the methods, how to count the number of adjacent, 3 adjacent people, the number of 2 adjacent, 1 non-adjacent. All of these will be very useful. So I hope this was very clear. I took my sweet time explaining this problem so that you can apply this knowledge anywhere in any problem. Okay, now coming to the generic inclusion exclusion. What is inclusion? What is exclusion? If you have studied sets, if you have studied Venn diagrams, then this is very easy. But if you haven't, I'll give you a little bit of intro. So inclusion exclusion for 2 sets. We have A and B. These are 2 sets. This is a Venn diagram for the 2 sets where this blue circle represents the set A, B circle represents the set B. This overlap is what is common between A and B, which we represent by A intersection B. Okay, now we want to count the number of elements, the number of members in these two sets combined. We count these and these, we write all of them together, and we want to count what is the total. That either it's in A or in B or in both, but at least one of them. So we want to count the number of elements in these two sets combined. So we write that as union. That means A or B, both is also allowed, but at least in one of them. It should be there in at least one of them. So we want to count the number of elements in A union B, which is either A or B or both. That is counted as, we first take all the elements that are in A and all the elements that are in B, but we counted the elements that are there in both of them twice, right? We first counted the entire elements in blue circle, then we counted all the elements in orange circle, but this common area, we counted this twice, we only needed to count them once, so we will subtract this once. So n of A plus n of B minus n of A intersection B. That is how we calculate the total number of elements in either A or B or both, at least in one of them. This outside, the rectangle outside this is called universal set. Universal set is all the elements that could have been there, that we are talking about all the elements that could have been there. For example, if A is, let's say, all the maths teachers in your school, B is all the chemistry teachers in your school, and let's say there are some teachers who are teaching both maths and chemistry. Universal could have been all the teachers in your school, or all the science teachers in your school, all the science and maths teachers in your school. It can be anything, but all the elements of A and B are there in universal set. So what is this area outside both these circles, which is neither in A nor in B? It is A union B complement. A union B complement, that means neither in A nor in B. Complement is not in this. So not in A union B, that means it's not in any of these circles. So if we want to count the number of elements in this, that is neither A nor B. This is neither A nor B. Then we will just simply do n of u, all the teachers, all the elements that were there in the universal set, all the total teachers that we were talking about, all the total elements we were talking about, and subtract the ones that were there in A union B. Okay, so we'll see how we can apply this formula directly here. Find the number of positive integers from 1 to 100 which are divisible by at least one of 3 or 5. That means in our Venn diagram, u is 1 to 100. All positive integers from 1 to 100. We are talking about all these natural numbers. A is multiples of 3. B is multiples of 5. What is this common area? This A intersection B, what does this represent? What does this represent? Yes, bacha, I see the answer, but that is not the answer what I'm asking. Very good if you've already solved it, but it's very important to answer what the teacher is asking and not just look at the question and solve it. Very good if you were able to solve this. But what is A intersection B? What did you calculate when you were trying to solve this problem? What is A intersection B? That is there in both these sets. It is a multiple of 5 and multiple of 3. It's multiple of 3 and a multiple of 5. So that means it is multiples of 50, right? So it is a multiple of 3 and it is a multiple of 5. That means it has to be a multiple of 50. Good. So now what do we need to calculate? We need to calculate the number of positive integers. We don't want to see which integers are there. We need to count the number of integers, the number of elements in either A or B or both, at least one of them. That means we need to calculate this. That is equal to n of A plus n of B minus n of A intersection B. Correct? Now, what is n of A? N of A is how many multiples of 3 are there from 1 to 100. Right? From 1 to 100, how many multiples of 3 are there? That is nothing but greatest integer of 100 by 3. We used this in the last class. Very similar concept, right? When we were counting the exponent, we were calculating the exponent of a prime number. In the same way, how many 3's are there? How many multiples of 3 are there? 100 divided by 3, greatest integer of that, which is 33. What is n of B? By the same logic, 100 by 5. There will be these many multiples of 5 in 1 to 100. So, plus 20 minus n of A intersection B. A intersection B is multiples of 15. So, how many multiples of 15 are here? 100 by 15, greatest integer. So, that is 100 by 15, greatest integer, 6. So, finally, we get our answer. So, yes, bache, you were getting the right answer. Very good. So, this is how we can use this simple formula to calculate all the multiples of 3 or 5. We don't actually have to see how many are there. But if you were going logically, if you did not know this formula, even then you could have calculated, right? You counting, okay, all the multiples of 3. There's 3, 6, 9 up to 99. So, that is 33. Okay. And there, how many multiples of 5 are there? There's 5, 10, 15, 20, up to 100. Okay, so 20. But I counted 15 twice, then 30 again twice. So, which means I'm counting multiples of 15 2 times. I only needed to calculate 1 time, right? So, I will remove all the multiples of 15 because they were counted twice. So, I can subtract the number of multiples of 15, which is 15, 20, 30, 45 up to 90. So, that is 6. So, I would get 33 plus 20 minus 6. Very logical, right? Okay. So, now this was when we only had 2 sets, multiples of 3 and multiples of 5. What if we have more than one set? What if, let's say, we have 3 sets? The Venn diagram is very similar. Now, you have, the rectangle is still a universal set. We have 3, let's say, physics teachers, maths teachers, chemistry teachers, right? So, we have these 3 circles. Now, there could be that there are some teachers who teach physics as well as maths. So, let's say if this was P, this was M and this was C, chemistry, then this entire overlap between P and M are the teachers who are teaching both physics and maths. P and C, these are all the teachers that are teaching both physics and chemistry. And similarly, maths and chemistry, these are the teachers that are teaching both maths and chemistry. Now, if you look in the center, this triangular area, we can see yellow, orange, green, all 3 colors. That means they are teaching physics, they are teaching maths and they are teaching chemistry. It's there in all the 3 circles. That means this is A intersection B intersection C. They are there in all of them. A and B and C, like that. Okay, so this is how you understand the Venn diagram. Now coming back to our problem, we need to calculate an A union B union C. That in at least one of them, it should be there in at least one of them. How many such elements do we have that are there in at least one of them? Now, just like before, we count all the elements of A, all the elements of B, all the elements of C. Okay, now just like before, I counted this A intersection B twice, so I'll remove that. I counted B intersection C twice, I'll also include that. And I counted A intersection C twice, I will also include that. But this central area, A intersection B intersection C, first I counted it 3 times, right? Once in A, once in B, once in C. I counted it 3 times. Now, when I was removing A intersection B, I removed one. When I was removing B intersection C, I removed another one. And when I was removing C intersection A, I removed another one. Now it's completely gone. So we need to at least include it once. So we will add an A intersection B intersection C. And like that, we get the formula for 3 sets. So bache, this kind of a formula where we first take 1 at a time and add them, then subtract 2 at a time, then add 3 at a time. So this is the generic formula that you're going to get for any number of sets. Okay, so for example, if you have, let's say, 4 sets, so we need to calculate an A union B union C union D. What are we going to do? We're going to first add all the number of elements taken 1 at a time, in sets taken 1 at a time. Okay, now we have to subtract 2 at a time. So minus A intersection B. Now how many such will be there? We have to select 2 out of 4. 4C2, 6. So these are all the 2 pairs that we could have got from these 4. So we subtracted. Now we have to add 3 taken at a time. So plus 3 taken at a time, 4C3, there will be 4 such triplets. So A intersection B intersection C, B intersection C intersection D, C intersection D intersection A, and A intersection C intersection D. Basically, we're leaving out 1. If we're taking 3, we're skipping 1. So we either skip A, or we skip B, or we skip we either skip A or B or C or D. So we have 4. Now we added this. Now this was 3 at a time. Now we come to 4 at a time, and what was the order? Plus, minus, plus, next will be minus. 4 at a time, that means we're taking all 4. And like this, we get the formula for any number of sets. Okay, so the same formula, the same pattern will be followed for any number of sets. That is what inclusion exclusion is. We included, then excluded, then included, then excluded. Okay, so we cannot go further after this because we've taken all 4. We cannot go to 5 at a time because there are only 4 sets. So if you want to verify, we were taking 1 at a time, then subtracted 2 at a time, and that's it. We only had 2. For 3, we took 1 at a time, subtracted 2 at a time, added 3 at a time, and that's it. We stopped here. So like this, we can do inclusion exclusion for any number of sets. Okay. Now find the number of positive integers from 1 to 100 which are neither divisible by 3 nor by 5. That means if A was multiples of 3, B was multiples of 5, and we want neither divisible by 3 nor by 5. That means this outside region. What was this? A union B complement. And if we needed to calculate the number of elements in this, all we had to do was n of u minus n of A union B. What is n of u? All the numbers. 100. Right? That's what we're talking about. Positive integers from 1 to 100. So our universal set is all natural numbers from 1 to 100. Then neither divisible by 3 nor by 5. So that becomes n of u minus n of A union B, that is 100 minus, what did we calculate? If let's say we were going from scratch, we did not just calculate this, then n of A plus n of B minus n of A intersection B. So like this we get 100 minus 47, which is 53. Alright, so like this we can calculate either in 3 or in 5 or in 3 but not in 5, like that. For example, if we want to calculate from 1 to 100 only divisible by 3 not by 5, in that case what does our Venn diagram look like? This is u, this is still 1 to 100, this is A multiples of 3, B multiples of 5. Now what area are we talking about? We are talking about divisible by 3. That means it's in set A but not by 5. So not in B. In set A but not in set B. In that case we just want this area, right? Because it has to be in A, so it has to be in this circle but not in the B circle. So that means we will remove the common parts. So what will be the answer? The answer will be n of A minus, what did we subtract? We did not subtract the entire set B. We only subtracted the ones that we had included but we did not want to include, which is A intersection B. So that comes out to be n of A was 33, n of A intersection B, that is multiples of 15, was 6. So we get our answer 27. Alright, so that way using Venn diagrams you can very easily, very simply solve any such problems. As soon as you have your set, you know which sets to assume and what is the common area, then you just have to follow the inclusion exclusion principle. Alright, now let's say we want number of positive integers from 1 to 100 which are neither divisible by 2 nor by 3 nor by 5. That means we have 3 sets: A that are divisible by 2, B that are divisible by 3 and C that are divisible by 5, right? Something like this. U is again 1 to 100. Now what are we doing? We are just using our formula. So to use the formula, that is n, what do we need to find? N of u minus n of A union B union C, right? That is what we need to calculate, that are neither divisible by 2 nor by 3 nor by 5. That means we will exclude all of those cases that are divisible by either 2 or 3 or 5, at least one of them, right? We'll remove all of them. So that is what we have to calculate. Number of elements in U, 100. Number of elements in A union B union C. We first take one at a time, right? One at a time. N of A is 100 by 2, 50. Then n of B is 100 by 33, greatest integer 33. N of C, 20. We'll subtract taken 2 at a time. Now what is 2 at a time? Just like before, A intersection B, divisible by 2 and divisible by 3. That means divisible by 6. Like that, B intersection C, 15. C intersection A, divisible by 10. So we will subtract those. So divisible by 6, 100 by 6, we'll do that. So that gives us 16. Divisible by 15, 6. And divisible by 10, 10. Then taken 3 at a time, now we have to add. So taken 3 at a time, that is divisible by 2 and 3 and 5. So that means that divisible by the product of 2 and 3 and 5, that is 30. So how many such numbers? 100 by 30, 3. 30, 60 and 90. So we will add those 3. And that is how you can calculate this. So 50 plus 33, 83 plus 20, 103 minus 16, that is 87, minus 6, 81, minus 10, 71, plus 3, 74. So we're subtracting 100 minus 74, that is 26. Is that what everyone's getting? Yeah. Very good. So this is how you can use the formula and not have to write all of it, just do it mentally. But if you think that can make you just do some mistakes, cause some mistakes, then just simply write everything and make sure you don't make a mistake. Okay? But an important thing here is to understand the meaning of sentences and how to transform that into the language of sets. Union, intersection, complement, that is the most important thing. Once you know, then you know the formula. That becomes very easy. Alright. Now a very important application of derangement, of inclusion-exclusion principle is derangements. What is derangement? Derangement is such that, let's say, we have n objects. Let's say we have n students. And each of them, we have 6 students and each of them is assigned 1 seat. Okay, each of them is assigned 1 seat. Now I want to see how many ways of arranging these 6 students are there such that none of them is sitting in their original seat. Okay, for example, let's say maybe they can hide something in their own seat for an exam, and I don't want that. I don't want that any of the students can cheat using something they had written on the desk for their help. So I want to make sure that none of them can do something like that, so none of them will be sitting in their original seat. Now how many ways of arranging these 6 students like that are there? So that is called derangement, where none of the students are sitting in their original seat. If we had letters and envelopes, each letter was supposed to go in its corresponding envelope, but I want to see how many ways are there when none of the letters go in their respective envelope. So like that, that is what derangement is. Very important, you will see it from time to time in a lot of questions. So how do we calculate that? That is nothing but inclusion exclusion. How many ways of arranging n distinct objects in n places are there? Without any condition, there are n factorial ways of arranging n objects in n places. Now we are obviously choosing those ways as well where some of the students are sitting in their original spots, maybe all of them, maybe some of them, maybe one of them, 2 of them. Let's see. So let's say I want to now remove those cases, right? So how do I remove those? I will check. I want to remove those cases where one of them is sitting in their original spot. So I will choose which one is sitting in their original spot, and then now I know this one person is sitting in their original seat, in its original place. The remaining n minus 1 can be anywhere. But this also includes when two of them are sitting together, two of them are sitting in their original place. We are counting those, right? We are basically repeating certain cases that we're counting. So now we excluded those. Which ones did we exclude? We excluded where these two students were sitting in their original spot. So we will add that NC2 because we excluded it more than once. We had two excluded, but we did not exclude it exactly once. So we will have to add that. Right? And just like that, you will keep going until you reach that situation where all of them were sitting in their original spot. And that is how you get the formula. Okay, this is what inclusion exclusion is. Now, if you look at it, what will be the sign of this? It's alternating between plus minus, so depending on if n is even or odd, it could be plus or minus, right? So we write that as, if it's odd it's minus, if it's even then it's plus. So we will write this as plus minus 1 raised to power n into NCN 0 factorial. Now this might be a bit complicated. How do we actually check? How do we actually calculate? Because these are a lot of calculations, right? So we will simplify each of these terms. N into n minus 1 factorial, that is n factorial, plus n factorial divided by n minus 2 factorial into 2 factorial into n minus 2 factorial. So n minus 2 factorial gets cancelled and we're left with n factorial divided by 2 factorial. Similarly here, n factorial by n minus 3 factorial, 3 factorial into n minus 3 factorial, even this gets cancelled. So like that we will have n factorial by 1 factorial, 2 factorial, 3 factorial, 4 factorial up to n factorial, right? We will be doing, we'll just cover the entire syllabus in a few classes, and then we will go through all the PYQs, all the relevant questions for this chapter after that. But first we need to cover, because if we are doing the question simultaneously, then you know which method to apply, how to solve that question. But if you see a new question randomly, then how will you solve it? So that is why we will solve all the questions at the very end. Do not worry, we will have a lot of such sessions just for problem solving. But for now, let's understand where we're getting the formula. Okay, so like that we have n factorial minus n factorial by 1 factorial, n factorial by 2 factorial, and so on, and this is actually minus 1 raised to power n factorial by n factorial. So if we take n factorial common out of all of these, then we have this formula, n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial up to minus 1 raised to power n 1 by n factorial. So like that we have our formula. So that means we write this as dn So that means d1 will be calculated like 1 factorial 1 minus 1 by 1 factorial, and that's it. We stop here. We won't go to 2 because n is 1. So that means our answer is 0. Does that make sense? Of course it makes sense, right? Because we had one student and one place. We want to see how many ways of arranging this one student in this one place is there such that it's not sitting in its original position. There is no such possibility. So D1 is correctly 0. Now D2. D2 is, there's S1 in place P1, there's S2 in place P2. We want such an arrangement such that these two are not sitting in their original spots, which means S1 has to sit here and S2 has to sit here, right? Only one possibility. Let's verify, is that what we are getting? 2 factorial by 1 minus 1 by 1 factorial plus 1 by 2 factorial. So yes, this comes out to be 1. Correct? Similarly, let's see D3. D3, in that case we have P1, P2, P3. Now S1 cannot sit here. S1 can sit here or here. Right? Only two possibilities for S1. For S2, let's see in the first possibility. Now S2 can go anywhere. But if S2 goes here, let's say S2 goes here, then S3 will have to go here. That means it will be in its original spot. That is not allowed. So that means S2 has to go here so that S3 can go here. Similarly here, S2 cannot go here, S2 has to go here, which means S3 will go here. So only two possibilities are there for 3 objects. Let's verify. 3 factorial by 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial. So this is 0. We'll multiply this entirely. So this becomes 0. So that means 3 factorial by 2 factorial, 3 minus 1, that is 2. Correct? So like this, you can verify this for any number. But an interesting way of looking at this is, let's say we want to derange n objects, right? Now, we want to derange n objects. How many ways are there if I know n minus 1? I know dn minus 1. Okay, so that means I know if I have P1, P2 up to Pn, and similarly I have Sn objects. I have n objects. I have S1, S2 up to Sn. Now S1 can go. Where can S1 go? S1 cannot go here, but S1 can go anywhere from P2 to Pn, right? So that means I have S1 I have n minus 1 options. Once I have placed S1 in one of these positions, then let's say I chose Pk out of 2 to n. So k can be anything from 2 to n. Let's say I picked Pk. How many options were there? N minus 1. I chose kth position for S1. Now, where will Sk go? Sk anyway could not go anywhere in. Now, where will Sk go? Sk can either go to P1, right? Or not at P1. Only these two possibilities, either it goes to P1 or it doesn't go to P1, both are allowed. Now, if Sk goes to P1, that means I removed two of the elements, two of the objects, and the remaining problem remains the same. Now I have n minus 2 objects that cannot sit in their original positions, and their original positions are available, right? So that means I have dn minus 2 ways of arranging the remaining objects, right? Now in this case, when Sk does not go sit at P1, that means I have n minus 1 positions and n minus 1 objects, and Sk cannot go to P1 and the remaining cannot go to their original. Let's say if P1 was its original position, then it's very similar to our n minus 1 derangement, that Sk cannot go to a specific position, the remaining cannot go to their specific positions. It is the same as n minus 1 objects cannot go, being able to go to their respective positions. So that means this is dn minus 2 ways, this is dn minus 1 ways, right? So that means for S1, I had n minus 1 options, and once I had n minus 1 options, once I selected that, then it was dn minus 1 plus dn minus 2, right? So this is how we can understand derangement, that it is not just placing Sk cannot go to Pk, Sk cannot go to a specific position. So let's look at an application, an example, and it will be more clear, and then we're going to come back to this. So first of all, find the number of placing 5 letters in 5 envelopes such that no letter goes in the correct envelope, right? No correct envelope, that means it's D5. So you simply calculate 5 factorial by 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial, like this. So that becomes, this is always 0, 1 minus 1. So 5 factorial by 2 factorial, that is 120, 1 by 2 minus 1 by 6 plus 1 by 24 minus 1 by 120. So we multiply 60 minus 20 plus 5 minus 1, that is 44. Okay, so because these are very simple and you might use them again and again, so you can memorize these, you might actually end up remembering these because you will be using these simple numbers derangements, but again, up to you. If you don't memorize it, that's also fine. You can just simply calculate using the formula that we had. So D1 was 0, D2 was 1, D3 was 2, D4 is 9, D5 is 44, D6 is 265. Like that, you can maybe remember some of these. Now, let's say we have a similar problem now, 6 cards, 6 envelopes. The card, each envelope contains exactly 1 card and no card is placed in the envelope bearing the same number. Derangement. Now there's a condition. The card numbered 1 is always placed in envelope number 2. Card 1 goes to envelope 2. Total number of ways of doing this. We did this very similar thing just now. Now K is 2. So now C2 can either go to E1 or it cannot go to E1. For C2 going to E1, now this is D4, Dn minus 2. If it cannot go to E1, then it is n minus 1. So D4 plus D5, that is 9 plus 44, that is 53. Right? Another way of looking at this is when we had these 6 envelopes. Card 1. Where could card 1 go? Card 1 could have gone here, or here, or here, or here, or here. 5 options. There is no difference between them, right? There are exactly 5 options for card 1, and it could have taken any one of them. So, for each of them, it's an identical situation. For any k, we get d4 plus d5, right? It doesn't matter where it goes. These are just numbers. It can be in any order. It could have gone in any one of those. That meant there are total 265 ways, right? d6 is 265. That is equal to 5 times c1 going to ek. It doesn't matter what k we chose. If it is k2, then we will get the same number of possibilities. If k is 3, we get the same number of possibilities. So there were 5 options. For each of them, same number of possibilities. This is what we are trying to calculate for E2. So we just divide 265 by 5. So 265 by 5 is equal to 53. Right? Both are correct. Both are important to understand. If you understand this, then we can go back to our formula. So that means D6 can go for, we take any one of them. We take any card. First card, we took first card, and we see that C1 could have gone to any of these 5 envelopes. And for each of them, it would be identical. There's not much difference, right? Once it's gone there, then there will be same number of possibilities. So that number of possibilities is into 5 is 265. So 265 divided by 553, that is the number of possibilities of derangement once we know that C1 is going to E2. So coming back to our this thing, that means once we took any one of them, we took S1, any one of them, and we saw there were n-1 options for that one object. It just cannot go to P1, and then it has n-1 options, and for each of those options there are dn-2 plus dn-1 options. So this is nothing but equal to dn. The total number of derangements is, we are trying to find a recursive formula for this. So once we have one object, we take any one, and we find either S1 can go to P2, or it can go to P3, or it can go to like that Pn. And for each of them there are dn-2 plus dn-1 options of arrangements, possibilities, and we multiply that with n-1 and we get all possible derangements. So if you want to verify, you can verify. Dn by n-1 is equal to dn-1 plus dn-2. If you want, you can verify, you will get the same value on either side. Okay, so that is how we can even get the recursive thing. So for example, now we know if we just need to calculate D7, we just do 6 times D5 plus D6, right? So D5 plus D6, that is 44 plus 265, 309. So 6 into 309. If you want to verify, you can verify. D1 is 0, D2 is 1, D3 will be 2 times d1 plus d2. 0 plus 1 into 2. This is 3 times d2 plus d3. d2 plus d3, 3 into 3, 9. 4 times d3 plus d4. d3 plus d4, 11 into 4, 44. 5 times d4 plus d5, that is 53 into 5, 265. So like this you can calculate any derangement either using the formula, or if you know these values then it becomes even easier. You're ready for some advanced topics. So of course multinomial theorem is something we've already done, which means if you have revised it properly all the previous lessons, then you are going to find this very easy because I have already covered it, but I just thought that we should cover it properly one more time, and then we are going to understand pigeonhole principle. It's a very simple principle, bache, but that is something I learned in IIT. Yes, so that is something that they teach at IIT. You are going to be learning here. Of course, we are not going to the most advanced level today, but we are going to understand and see how we can apply this very simple, very basic principle in some of the most twisted problems. So let's start. Good evening, good evening. Ready? So let's first quickly go through multinomial theorem and then we're going to move on to pigeonhole. Alright. So multinomial theorem, if you remember, we solved this problem. We had 10 mangoes and we had to distribute those 10 mangoes among 3 students, right? So what did we do? We had to divide 10 mangoes among 3 students. That means we needed to partition these 10 mangoes into 3 parts such that the sum is 10. Now any one of them could also get 0 mangoes, which meant if I made the partition in this manner, then the first student gets 0, the second student gets 2 and the third student gets 8. So basically we had to arrange these 2 partitions that will divide it into 3 parts and we will have our solution. So how many ways we can arrange this? We have 10 mangoes and 2 partitions. So 10 plus 2 factorial divided by 2 for the 2 identical partitions and 10 for the 10 identical mangoes, which meant 12C2. Correct? This is what we did. Another way to solve this same thing was using multinomial theorem. So let's see what multinomial theorem is. Multinomial theorem is a theorem which we use to solve something like this problem, right? We have R variables. These variables can take certain values, certain integral values, and their sum has to be equal to n. So what did we do? Let's say we go back to our mangoes problem. That meant we had number of mangoes that we give to the first student, number of mangoes that we give to the second student, and number of mangoes we give to the third student. The sum should be 10. Now all of these can go from 0 to 10, right? This is what we can do. Each of them can get 0, 1, 2 or up to 10. That is the only possible values of x1, x2, x3. So how did we solve this? Using multinomial theorem, which was we have to find the coefficient of x raised to power 10 in, we multiply all the possible values x0. For this, we write the bracket with now this is the bracket for x1 because it can go from 0 to 10, so it can take 0 value or 1 value or 2 value up to 10 values. Similarly for x2 and for x3. So we multiply it 3 times, right? I hope all of you remember how we actually derived this. For example, we take the value 2 from for x1, the first bracket, we take 3 from the second bracket, and we take 5 from the third bracket. Now they will multiply, each of them will multiply with each other and give one unique term. This is x raised to power 10. This is adding 1 to the term x raised to power 10. We are counting how many such x raised to power 10 terms will be there once we multiply all of these 3, right? We are counting the number of x raised to power 10 terms in this expansion. Now, this is one such term. When we take 2 from here, 3 from here, 5 from the third bracket. Or we can take x raised to power 9 from the first one, let's say x raised to power 0 from the second one, and then if we took x raised to power 2, this will give x raised to power 11, which is not what we are counting. We are counting x raised to power 10. These will also give x raised to power 10. So this is also counted as another one. So what are we doing? We are basically counting how many combinations of such integers can be there. Now we can also order these. We can take x raised to power 3 from the first one, x raised to power 2 from the second one, x raised to power 5 from the third one. That will also give us another term. So we are basically counting how many such terms we can get so that we get all possible values for these 3 variables such that their sum is equal to 10. So this is multinomial theorem where we give all the possible values. In this case, it was 0 to 10. In one of the cases, if you remember from our previous class, some of the variables could only be even. So in that case, we only count the even powers. So we basically put all those numbers, all the possible values, possible integral values in the powers, and we write them down as a sum for each of these variables, and then we multiply them, and we have to find the coefficient of x raised to power 10, that is x raised to power n. So in our original problem, we have to find coefficient of x raised to power n, right? Now a very important thing that we need here is, what is x raised to power 0 plus x raised to power 1 up to x raised to power 10? This is equal to, this is a GP. So first term, this power 3 I will write as it is. Now the first term is 1. The common ratio is x. The number of terms is 11. So this is the sum of the GP, right? First term 1 minus common ratio raised to the power total number of terms divided by 1 minus common ratio, which is equal to 1 minus x raised to power 11 cube and 1 minus x raised to power minus 3. We need coefficient of x raised to power 10 in this, which means we will have 4 terms here, right? We get 1 minus x raised to power 33 minus 3x raised to power 11 plus 3x raised to power 22. We know a minus b whole cube, but let's say even if we did not know, let's say it was a minus b whole raised to power something, we will only get higher powers of x raised to power 11, right? It can only, the least power available other than 1 is x raised to power 11, which is already greater than x raised to power 10, and this will only give positive powers of x. So that means we can only, after multiplying, get even higher powers of x. What did we need? We needed x raised to power 10. We cannot get 1 by x in this. So that is why we will ignore all of these and only take 1. So from the first term, we only take 1. So that means now we multiply 1 with this, and whatever the coefficient of x raised to power 10 is there in this term will be the coefficient of x raised to power 10 in our entire expansion, right? So that means our new problem becomes coefficient of x raised to power 10 in 1 minus x raised to power minus 3. How do we calculate that? We have to remember this. In 1 minus x raised to power minus n, the coefficient of x raised to power r is n plus r minus 1 CR, which means here in this case, now do not get confused between n and r. Here we have switched the n and r. Earlier n was 10, r was 3. Here n is 3, r is 10. So do not get confused. Always remember that you have to add these two, 10 plus 3 minus 1, see this number, 10. Okay, so we add these two, 10 plus 3 minus 1, see this number. Of course, it's very important that you also memorize this in general, but do not get confused between the n and r. If you think you will get confused, then it's better to write it as x raised to power n in 1 minus x raised to power minus r is r plus n minus 1 c n. Alright, so that means we have to, the general formula, this is the general formula when it can go from 0 to n, it can take any values from 0 to n, then this is what we are going to get. Okay, so n plus r minus 1 cn or c r minus 1. So here what do we get? 10 plus 3 minus 1, that is 12 c10, which is the same as 12 c2, which is the same as the answer we got earlier. The correct answer is B, 12C2. Now you might think, ma'am, this was much easier. Why did we go through that complicated thing? But say yes, in this case, this is easy, of course. You should use this method. You should not even go to multinomials. But in a lot of questions, it is not possible to do it in any other way. It becomes very tedious, but using multinomial, it becomes much, much easier. So, this is the last lecture that we are going to do for the theory. After that, we are going to solve all the PYQs. So, in 2 to 3 lectures after this, depending on how fast we go, we will take problem solving. So, that means it's going to get trickier. This is the last theory lecture. So, we're going to cover this, and if there's any topic you think that we haven't covered yet because it's listed in the syllabus, but yes, there are a lot of topics that are listed in the syllabus that we are not covering because they are not asked that often. Maybe a very small topic might be asked, so we will cover those topics while solving the problem. So whenever we see a problem from which is not a part of these questions, these topics, then we will discuss that small topic right then and there. All right. So both the methods should be super clear, how to actually do the simple problem using partitions and how to solve it using multinomial and this formula as well. So if you have something like x1 plus x2 plus x3 up to x raised to power r is equal to n, where all of these can be all values from 0 to n, all integers from 0 to n. Then the formula is n plus r minus 1 cn. Okay. Now, is rolled 3 times. Then find the number of ways of getting sum equal to 10. We roll a dice once and we get a number. Let's say we get 2. We roll a dice again and let's say we get 6. So now the sum is 8. We roll a dice and if we get a 2, we get the sum equal to 10. So that is one option, 2, 6, 2, right? Like that we can have a lot of options. So an easy way to look at it is we have x1 plus x2 plus x3 is equal to 10. The first number we roll is x1. The second number we roll is x2. The third number we roll is x3. But now these are not going from 0 to 10. When you roll a dice, it will only go from 1 to 6, right? So now we need the coefficient of x raised to power 10 in x raised to power 1 plus x raised to power 2 up to x raised to power 6 whole raised to power 3. Let's simplify this. So we have first term into 1 minus common ratio raised to power number of terms divided by 1 minus common ratio whole raised to power 3, which is equal to x cube 1 minus x raised to power 6 cube 1 minus x raised to power minus 3. Now we are looking for coefficient of x raised to power 10 in this. That means we are looking for, we get x cube definitely from here. So we have to look for x raised to power 7 in the remaining expansion. So we need x raised to power 7 from here such that the product is x raised to power 10. So our new problem is x raised to power 7 in 1 minus x raised to power 6 cube 1 minus x minus 3. Now we get an x raised to power 6 which is smaller than 7. Now we're not going to ignore all of the remaining terms. Now we have to consider x raised to power 6 as well. We won't consider the other ones, right? We will consider 1 and minus 3x raised to power 6. We will not consider x raised to power 12 or x raised to power 18 because that's greater than 7. But this 3 into x raised to power 6, that is something we have to consider. And then we have 1 minus x raised to power minus 3. Now, what is our problem? We need coefficient of x raised to power 7, 1 multiplied by coefficient of x raised to power 7 in this 1 minus x raised to power minus 3 plus, or rather minus, so plus minus 3 multiplied by coefficient of x raised to power, we are getting x raised to power 6 here. So what is remaining? X raised to power 1. We need x raised to power 1 from 1 minus x raised to power minus 3. So that will be our final coefficient of x raised to power minus 7. Okay. So what is coefficient of x raised to power 7 in this? That is equal to 7 plus 3 minus 1, 9, C 7 minus 3 into 1. 1 plus 3, 4 minus 1, 3, C 1. So let's simplify this. 9 into 8 by 2 minus 3 into 3. So 9 into 4 minus 9 is equal to 9 into 3, which is 27. Yes, bache, this is for IOQM. This is something you have to know. This is very important. This is heavily used in combinatorics problems, so we have to know this. Okay. So as I mentioned in the previous class, if you are not sure about binomial expansion, you haven't studied binomial expansions, then I suggest you revise that topic. You at least go through the basics of that topic, and if you want, I can bring a separate lecture for binomial theorem, but here, or you can find it on the channel already, but Here we are directly applying the concepts of binomial, and the main concept that you need is this one. This is something that you have to remember. So we use that formula twice here, once here and once here. 9C7, 3C1, and that is our final answer. Okay, so this is why multinomial is very important, because directly memorizing a formula will not work in this case. You could have seen this and said 12C2, but that would have been wrong, because now it's not from 0 to 10, it's only from 1 to 6. So we have to expand, we have to see the expansion. Let's take a look here. The number of ways of selecting 8 fruits from unlimited supply of mangoes, apples, bananas and oranges. It can go from 0 to infinity. That means we have x raised to x1 plus x2, number of mangoes, number of apples, number of bananas, number of oranges is equal to 8. How will we do this? Now what are the values? We have an unlimited supply of mangoes, apples, bananas and oranges, and we have to select 8 total fruits. That means if we select, let's say 0 from here, 0 from here, 0 from here, then we have to select 8 oranges. Like that we have to find combinations. Maximum, the minimum value can be 0, maximum value can be 8. It cannot be more than 8, otherwise we would have selected more than 8. So this looks like our previous problem, right? What does that give? 8 plus 4 minus 1, C, 8. So that is 11C. 8, which is 11 into 10 into 9 divided by 3 factorial, which is 6. So 5, 3, 15 into 11, 1, 6, 5. So you have to know how to identify when we can use the formula directly and when we cannot. When we can use all values from 0 to 8, then we can directly apply the formula. If you want, if you don't want to memorize a formula, if you like me and you prefer doing it the entire solution and not using a direct formula, because maybe you remember the formula wrong, maybe you are not sure that can we apply the formula, will it give the right answer, let me quickly derive. So you can also do that. It's up to you. So you get x raised to power 0 plus x raised to power 1 up to x raised to power 8 and whole raised to power 4. So using the same derivation as we did before, you will reach the same answer. Alright. Now, the number of terms in the expansion of x plus t plus 2z whole raised to power 8. That means if we add the like terms, we expand it entirely and then we add the like terms. If we get x squared t raised to power 6, z raised to power 0, then we will add all of these terms and we will get one single term in the end, which means the like terms will be counted once. So how many ways we can form such terms? We know that the entire power is 8. Right? That means we are multiplying x plus t plus 2z, x plus t plus 2z 8 times. Right? We're multiplying them 8 times. That means if we get x from here, we will get one term. No matter what. If it's x, if it's t, if it's z, it doesn't matter, but it will give us one term. Each bracket will give us one term, right? One x or one t or one z. And we will get one term from each bracket, and that will give us a unique term. Now we have to count how many unique terms will be there such that the power of x, the power of t and the power of z is the same in those, is different in those terms. Basically what I'm saying is, you will get one term from here, one term from here, one term from here. In total there will be 8 terms. 2x, 6t and then remaining 0z. The sum of powers here will be 8 because we got 2x from somewhere, we got 6t from the remaining brackets and then no z because we have taken one term from each of the 8 brackets. Or we could have taken x raised to power 2, t raised to power 4, z raised to power 2. So from 2 of the brackets we are taking x, from 4 of the brackets we are taking t, and from the 2 remaining brackets we are taking z. Now they can be any of these and we have to count all of these. But right now we have to see how many unique terms will be there. The coefficient will be counted based on how many x raised to power 2, t raised to power 4, z square will be there. But we have to see how many unique such terms will be there, which means if power of x is x1, power of t is x2, power of z is x3, we know the condition that x1 plus x2 plus x3 has to be 8. Right? It has to be 8 because we're taking x1 from, we're taking x from x1 brackets, we're taking x2 brackets, we're taking t from x2 brackets and we're taking z from the remaining x3 brackets such that this is the total. So now this is our previous problem. Why? Because each of these can be 0 to 8. We can take x from all 8 brackets or we can take 0x. We cannot take any x and we'll do the multiplication from only t's and z's. Right? So 0 to 8 is possible for all of these 3, which means we can use our formula 8 plus 3 minus 1 C8. That is 10 C8, which is 45. So this is how we have to simplify. Again, bachche, right now we know which chapter, which topic we are studying, but whenever we see a new problem, we have to identify how to actually solve a question. But very often you will see a statement like this. We are thinking, forget about the topic we are doing and we look at this problem and we know, okay, this is also possible, this is also possible. That means the entire sum has to be 8. The values can be anything, but the entire sum of all the 3 powers has to be 8, which means it will follow something like this. And looking at this equation, it should be immediately clear to you that this is a problem from multinomial theorem. So this is how you identify, how you apply this topic, and trust me, you will see this topic, this kind of equation so often in combinatorics problems that it's very important. This topic is very important, which is why we are covering this another time. Now, try this one. The number of distinct terms in the expansion of x plus 2y minus 3z plus 5w minus 7u raised to power n. Same as before, right? We will have x raised to power x1, y raised to power x2, z raised to power x3, w raised to power x4 and u raised to power x5. We have 5 variables. They will have their individual powers. All such values are possible. But the only condition is this has to be equal to n. The number of the total sum of all these powers has to be n. So, again, x1 can take values from 0 to n, x2 can take values from 0 to n. So, now this is the same problem, n plus 5 minus 1 Cn, which is n plus 4 Cn or n plus 4 C4. Okay, so carefully 1, 2, 3, 4, 5 terms. That means R is 5, n plus R minus 1 Cn or Cr minus 1. So with that, we are done with multinomial. We have seen more applications earlier. That's why I did not repeat all those problems. You can just go back to that lecture and go through those problems again. But now we are going to understand a very simple theory, a very simple principle, and then we are going to see how that very simple, very obvious principle can be used to calculate or to prove a lot of complicated problems. Okay, so let's start. What is pigeonhole principle? Pigeonhole, the name says there are pigeons and there are certain holes. The very basic principle behind this is, let's say we have n holes. In trees, we have one hole. Like this, we have n holes. Okay? And we have n plus 1 pigeons. Now, every pigeon wants to sit in at least one hole. I mean, they want to sit somewhere. They don't want to keep flying. Every pigeon wants to sit, take rest. Okay, so now n plus 1 pigeons are sitting in these holes. It's possible that some of these trees are empty, there are no pigeons sitting there, or there are multiple pigeons sitting in one hole. That is allowed. But it is never possible that there is exactly one pigeon in one hole, or there is at most one pigeon in one hole. Why? Because there are n plus 1 pigeons. So, at least 2 of them have to share a tree, right? It is not possible that every pigeon gets a unique tree to themselves. They have to share because we have more pigeons and less number of trees, less number of holes. So that is the entire concept. Yes, that is it. If we have more objects to place and less places for them, then some of the objects have to share the place. Easy, simple. If n plus 1 objects are put into n boxes, then at least one box contains 2 or more objects. That is possible. Let's say I had 5 objects and 4 boxes. That means 1, 2, 3, 4. Even if I place object 1, object 2, object 3, object 4, the 5th object will go somewhere, right? Object 5 may go here. In that case, this box is occupied by 2 or more objects. It is also possible that the last box was empty and we placed object 4 here or object 5 here. like that. In that case, 2 boxes are occupied by 2 or more objects, but at least one box will always be containing 2 or more objects. We could have also done something like O1, O2, O3 go here, and then O4 and O5 both go here. So in this case, this box contains more than 2 objects, but it is never possible that none of the boxes contains less than 2. That means 0 or 1 objects. Why? Because there are more objects. Very simple. Clear? You have to remember this, bache, because if you don't, you might think it's easy, but still just keep that in your mind. Otherwise, you will have a hard time understanding the problems that we are going to solve. Okay, so if we have more objects, less number of places, less number of options for them, then definitely some objects will go in the same place. They will have, for example, let's see a very simple example. Let's say I have picked 13 people. I have 13 people in front of me, and I ask each of them, what's your birth month? January, June, May. Okay, everyone gives me their birth month, but it is not possible that all of them will have a different birth month, right? I will get at least 2 which have the same birth month. It's possible that a lot more are sharing the birth months, but at least 2 will be there who will definitely share the birth month. All 13 cannot have their unique birth month because there are only 12 months. So that means if we have 13 people, there are at least 2 who have birthdays in the same month. Right? Again, very simple, very logical. So now answer this for me. There are 7 married couples at a party. How many of, so at a party, there are 7 married couples. Okay, only 14 people are there at the party, these 7 into 2. Out of these 14 people, we have to select certain number of people. Let's say n. I selected n people out of these 14. Now, how many minimum I need to select in order to guarantee how many I have to select? I can select more, but minimum. In order to guarantee that at least 1 married couple is selected. Eight. Very good. Because if we select, how do we actually think of this? Let's say I select n and there is no married couple. How many such people can I find? That means I have to select 1 person from 1 couple. Right? I cannot select 2. That means at max 7 can be selected such that no couple is selected. 1 from the first couple, 1 from the second couple. It can be any of the 2, but 1 from each. So at max 7 I can select in that way such that no married couple is selected. Now I have to select at least 1. That means I add, as soon as I add more than 1, I had 7 couples and 8 people to choose. That means at least 2 will go into that couple, right? I have 8 objects and 7 boxes. What are these boxes? I am arranging which couple they are going to. Let's say first person was from couple 3. These are couple 1, couple 2, couple 3, couple 7. Let's say first person was from couple 3, second person was from couple 7, and so on. Now I arrange all the 8 persons this way, then at least 2 of them will go into the same box. That means 2 of them will have to go to the same couple, will belong to the same couple, will be a couple. Okay? Simple again. Now, here comes something tricky. We are given 1 to 200 natural numbers, the first 200 natural numbers. If we select any 101 integers, out of them, any 101, then there are at least two integers such that one of them is divisible by the other. I'm not saying that they will have a common factor. No, one of them will be a multiple of the other, at least. It is not possible to have such 101 integers such that no two integers are divisible by each other. Basically, we have 6 and 3. Now, 6 is divisible by 3, okay, or 12 and 8. Now, in this case, we are not saying that this is also counted. No, we will have at least one such number whose factor is also present. If we have 12, if that number is 12, then either 4 is there or 6 is there. At least one such pair will be there such that if A comma B is the pair, that is A is divisible by B or B is divisible by A. Now, it's a bit tricky, it might be a bit complicated. You have to listen very carefully. I will explain in detail and extremely slowly. So, try to follow every line, every step I mentioned. Okay? I have 101 integers. A1, A2, A3 up to A101. Right? I have 101 integers with me and I name them, I give them a variable. Now, let's say I write each one of them in this way, 2 raised to power L1 into B raised to power B1. I write this as this. What does that mean? I take as many 2's as I can take out of A1. For example, if A1 was, let's say, 72. How many 2's can I take out of this? 3. 2 raised to power 3. What is remaining? An odd number. If I have an even number remaining, then I will still take out that 2 until I have only odd number present with me. So, we will write this as 2 raised to power 3 into 9. Okay? If we have 15, then we will write this as 2 raised to power 0 into 15. We will split them into powers of 2 and then an odd number. Okay? So, we write this as 2 raised to power L1. We write this as 2 raised to power L2 into B2. And like this, 2 raised to power L101 into B101. Such that B1, B2, B101 are odd numbers. Right? We took as many 2's out as we could and until we were left with only odd numbers. How many odd numbers do we have between 1 to 200? We have 100 even numbers here and 100 odd numbers here. Right? So that means we have to select 101 out of 100 possible odd numbers. That means at least 2 of them will be the same, right? If we are selecting 101, that means at least 2 of them will be same. We cannot have all different odd numbers. There will be at least 2 which are the same. Let's say B, K and B, L are same. Okay? It can be anything with K less than L. Or if you want, you can just do, L is confusing you, BP, BQ, B subscript P, B subscript Q are the same such that P is less than Q. Okay, that means it can be, let's say B3 and B37 are the same. At least two of them will be the same, and I take any two of them which are same, which means BP is equal to BQ. Now we go back to the original numbers. We have A, AP is equal to 2 raised to power LP into BP. AQ is equal to 2 raised to power LQ into BQ. Right? That is how we can write AP and AQ. Now these are the same. Let's say this is equal to B. Okay? So that means this is equal to 2 raised to power LP into B, 2 raised to power LQ into B. For example, let's say BP is equal to BQ is equal to some odd number which is the same. Let's say that is 17. One number is 2 raised to power something into 17. Another number is 2 raised to power something into 17. Let's say that something is, it can be anything, 3 and 7. Can be any two numbers, right? We took some, although this might have gone above 200, but okay. Let's say this was 0 and this was 2. Okay. Now we have whichever one is larger. Okay. Let's say the second one was larger. That means LQ is bigger than LP. So if we divide, if LQ is greater than LP, then we divide AQ by AP. Then we get 2 raised to power LQ minus LP, which will be an integer because LQ is greater than LP. LQ minus LP will be positive, 2 raised to power positive or non-negative. Actually, they will have to be different, so it will be positive, which means 2 raised to power something positive. It will be an integer. Okay, I know it's a bit complicated, but if you understand, if you really try to understand, which I think you should, otherwise you will have a hard time understanding maths. So if we, again I will repeat the entire solution very quickly now. We took all 101 integers and we took all the 2's out of them until we only had odd numbers remaining. We had 100 odd numbers with us. We had to select 101 out of them, which meant at least 2 of them will be the same. Let's say that was BP and BQ. That means AP is equal to, let's say BP and BQ are equal to B. AP is equal to 2 raised to power LP into B. AQ is equal to 2 raised to power LQ into B. If, let's say second one is larger, if the first one were larger, we would divide AP by AQ. So whichever one is larger, we divide that by the smaller one and we will always get an integer, which will be equal to 2 raised to power difference of LP and LQ. Okay, so this is how we actually apply such a simple principle. Very simple. What was the principle? Where did we use it? We used it here. That if we have more variables to choose out of and less number of options for them, then at least 2 will have the same values. That is all we needed to use, and then we applied that information to prove that one will divide the other. So now the tricky part was taking the 2's out, right? That is what we have to practice. With practice, we start seeing how we can actually solve this problem. Now, a relatively easier one and the last problem for today. A basket of fruits is being arranged out of apples, bananas and oranges. We have apples, we have bananas, we have oranges, and we are making a basket. Now, what is the smallest number? Smallest number of fruits. Pieces of fruits, that means one apple, one banana, that is one piece of fruit. So how many, the minimum number of fruits we need to put in the basket such that either there are at least 8 apples or at least 6 bananas or at least 9 oranges. I know, bache, this is a tricky topic. If you're having a hard time understanding this, I suggest that you watch this video again because I've already repeated it a lot of times. So just go back to the video, go back to the previous question, listen to the solution, pause it, think about it. That is how you're going to understand. It's a very difficult level topic for sure, but if you're able to understand it, it's amazing if you can follow, because in the end it is very simple, right? More objects, less boxes, of course, at least 2 will go to the same box. Simple concept. How to apply is tricky. Yes, for that you have to understand. I cannot make you understand after a while. I can only explain, but understanding part is your responsibility. You have to think. I cannot make you think. Okay? It's an English course, bache. That's why I cannot speak in Hindi. I will definitely bring a Hindi course as well. But this is purely in English, as you can see. You should have been able to see in the title, but yeah, it's an English course. Alright. Anyone? Even if you're confused by the previous question, that's okay. But a basket of fruits is being put together such that there are at least 8 apples or at least 6 bananas or at least 9 oranges. What is the minimum number of fruits we need to put in the basket? Think about it. What is the minimum number of fruits we need to put in the basket such that there are at least either 8 apples or at least 6 bananas or at least 9 oranges? At least one of them has to be true. Let's say none of them is true. Let's say the opposite. Let's look at that. Okay? So this is how we solve it. We look at the opposite. What will be the opposite of this? At max, at most, 7 apples and at most 6 bananas, 5 bananas. Because if we have 6 bananas, then our condition is satisfied. We want the opposite. At most 5 bananas. We have maximum 7 apples. That is the maximum we are taking apples. Because as soon as we took 8 apples, our condition is satisfied, and looking at the opposite of it when this condition is not satisfied. So, at most 7 apples, at most 5 bananas, and at most 8 oranges. That means 7 plus 5, 12 plus 8, 20. We have 20 fruits. That means if we had to select 20 fruits, we could have assembled it in such a way that this condition would not be satisfied. Right? If let's say this number, I needed to put together a basket of 20 fruits, then I can form it, I can put it together in such a way that it has 7 apples, exactly 7 apples, exactly 5 bananas and exactly 8 oranges. In which case, this condition is not true. So, at least 8 apples need to be there, or at least 6 bananas need to be there, or at least 9 oranges have to be there. Which means, as soon as I add 1 to this, I need to put together now a basket of 21 fruits. Let's say I did not make this true. I put 7 apples. I put 5 bananas. This is also not true. Now, how many oranges will I have to put? 21 minus 12, 9 oranges. And then this is satisfied, then our condition is satisfied. Or if we did not put 9 oranges, I put, let's say, 6 oranges and 4 bananas, then I have selected 10 fruits. The remaining 11 will come from the apples. So at least 8 apples are selected. That means we will check the opposite of it, the maximum we can do without making this true. The maximum number of fruits we can put while keeping this condition false. So when will this condition be false? When there are less than 8 apples and less than 6 bananas and less than 9 oranges. So this is the condition. The maximum we can do is this, which is 20 fruits. So as soon as you add one fruit to it, as soon as you add one more fruit to put in the basket, then one of these will be true and our condition will be true. Very logical, right? This is not something you have to memorize, bache. If you have been memorizing maths, if you have been memorizing formulas, then you will have a hard time understanding advanced topics. So I will repeat again and again, never memorize maths. That is not what you're supposed to do. Yes, of course, it helps to memorize certain formulas, but it will definitely help if you understand the derivations. We have to understand where every formula is coming from, every logic behind problems. So again, this is very easy, bache. Just have to think. Once you start thinking, this should be simple to understand. Yeah, it makes sense, right? If we have to select 21 fruits, one of them will have to be true. So this is how you have to look at such problems. We look at the opposite when this condition is not true and we add 1 to that. So yeah, I think this was easier to understand than the previous one. I know. As soon as we add variables instead of fixed numbers, I know it gets tricky for a lot of students, but if you think about it, maybe use examples to think, you will get a better understanding. Okay, so definitely revise today's class. It's for sure a new thing for all of you, right? Pigeonhole is not something trivial. I did not learn it until I was in college, until I was, I think, in my second year of college. So can you imagine? You are already learning something that I learned, that most of the students learn in advanced degrees. So it's okay if you're having a hard time, but the reason why we think, the reason why it's been added to IOQM, it's been added to RMO, the reason why the teachers are teaching you is because we definitely know you can understand it if you just try to think of it very logically. Okay, hope by now you all are ready to actually solve some questions. Now we have completed all the syllabus that you will need to solve almost every one of these PYQs. So are you ready? You will solve it first. You will try each one of them. I will give you around 1 minute to solve it on your own, and then I'm going to share the solution. You can check your answer, you can check the way you solved it, and if you solved it in a way which was more efficient, then required less number of calculations or something like that, then what I showed, then definitely message in the chat so that I can learn something from all of you brilliant students. So are you ready? Alright, so the flow of PYQs, I have divided the PYQs into 2 parts so that we can do it in 2 separate sessions and not all of them at once. And of course, we're not going through all of the PYQs, right? Because they are repetitive, they might be too easy for you, something that we have already covered in previous lectures. So that is why I have selected the questions that will be helpful for you, that might help you learn how to actually apply whatever we learned so far. And before anyone comments, ma'am, please Hindi. But this is an English only course, so we will bring a Hindi English course, however you feel comfortable later. But as of now, this is a purely English course for the students who are not that comfortable with Hindi. Alright, so we start with KVPY PYQs. A lot of letters there, KVPY PYQs. But yes, we start with KVPY questions related to combinatorics that I feel have been very good, have been very difficult, and then we move on to pre-RMO, before IOQM even started, because the questions, the syllabus is pretty much the same. right? The level of questions is pretty much the same. So we're going to go through pre-RMO, and then in the next session we are going to cover more pre-RMO questions as well as IOQM PYQs, the ones that have been asked ever since IOQM started. Okay, so we'll try to cover as many questions as we can in these 2 sessions, so that all kinds of questions have been visited, all kinds of approaches have been learned. You can attempt a new problem on your own if you are able to solve all of these questions. Okay, so keep your minds sharp and open. Do not be lazy. Try to think of the solution from any direction and every direction, and get the right answer as quickly as you can. Now, so a woman has 10 keys, out of which only one opens a lock. She tries the keys one after the other, keeping aside the failed ones. She takes one and tries to open a key, and if it doesn't work, then she puts it aside. What is the probability that she succeeds at the 7th key? She's trying 10 keys one at a time, and if it doesn't work, she just discards it. So what is the probability that the 7th one that she tries is the right one? Only one of them is going to be right. D. Very good. So the answer is D. This one does not require any calculations. This is just using your brain, just thinking of it logically. So there are 10 keys. It doesn't matter in what order. If you have key 1, key 2 up to key 10, what is the probability that this one, key 7, is the right key? Same as the other one. There's nothing special about the 7th one, right? So that means it's 1 by 10, 1 by 10 for each of them. So the correct answer is D, 1 by 10. Okay. Yes, to answer the question in the chat, will IOQM 2023 PYQs be also there? Yes, but all the recent PYQs will be covered. I will select the questions that I feel have not been covered yet. It will help you learn something unique. So those are the questions I will handpick. I will not cover the entire IOQM papers, maybe in another session, but in these 2 sessions, I will select the PYQs that I feel are different, are unique, that are going to help you learn a new approach. Okay. Now, next question. S is a set of first 40 natural numbers 1 to 40. Let A be a subset of S such that no 2 elements in A have their sum divisible by 5. What is the maximum number of elements possible in A? For example, if I have 1, 4, 7. If A is this, then that is not allowed. Why? Because no 2 elements in A should have their sum divisible by 5. And in this case, 1 plus 4 is 5, which is of course divisible by 5. So this is not allowed. Think carefully. Yes, 17 is the right answer. C, yes, very good. So how do we approach such a problem? That is more important than what is the right answer, right? So yes, the correct answer is 17, but how do we get that? We have 40 numbers. Out of 40, 8 of them are divisible by 5. 8 of them will leave a remainder 1. 8 of them will leave a remainder 2. 8 will leave 3. 8 will leave 4. And divisible by 5 means 0. So in terms of remainder, we are going to check if we take any of these numbers and check its mod with respect to 5, what will be the remainder? It can be 0, 1, 2, 3, 4. And because there are 40 numbers, there are exactly 8 of each of these. 8 numbers which will leave remainder 0, 8, that will leave 1, 8, that will leave 2, 8, that will leave 3, 8, that will leave 4. Now, if I take any 2 of them, any 2 out of these 8, any 2, then their sum will be divisible by 5, right? Because one of them is divisible by 5, the other one is also divisible by 5, then their sum is also divisible by 5. For example, if I take 15 and 25, then the sum 40 will also be divisible by 5. So at max, I have to check the maximum number of elements. So at max I can take 1, right? Because if I take 1 out of these, then I do not have to worry about the sum being divisible by 5. Now coming to these 4 categories, if I take 1 from here, 1 from here, then this leaves a remainder 1, for example 11. This leaves a remainder 4, for example 19. 11 plus 19, 30. That will leave a remainder 0. The sum will be divisible by 5. So I can not take 1 from here and 1 from here. Even if I take, let's say 8 from this second category where remainder is 1 and just 1 from the last category, even then I will find 2 elements whose sum is divisible by 5, which means either I can take the elements from here or I can take the elements from here. But out of these 16, at max I can take 8 either from here or from here, but can't be from both. So out of this I will get 8. Similarly, but the same logic from these 2 as well, I can take either all 8 from here or 8 from here. Of course I can take less than 8, but I am checking the maximum number of elements possible. So 8 from here, 8 from here, 1 from there. So 16 plus 1, answer is 17. Okay, so this is how we will actually calculate. Now, how many ways are there to arrange the letters of the word education so that the following 3 conditions hold? There are 5 vowels. All of them should occur in the same exact order. We cannot have A before U or anything like that. We can have something in between these, but when we just take the vowels, this order has to be maintained. The consonants also occur in the same order. The 4 consonants, there are 5 vowels and 4 consonants. These 4 also have to maintain their order. And no 2 consonants are next to each other. Gap method. So, what's the answer? Carefully. The vowels have to occur in the same order. The consonants have to occur in the same order. And the most important, the thing that we know how to solve this, right? That no 2 consonants are next to each other. What do we do in that case? Come on, come on, come on. Yes, we'll be covering all sorts of problems in these 2 sessions, in IOQM, in pre-RMO, in KVPY, all the combinatorics problems, because they are all relevant for you when you're preparing for IOQM and other related exams. So we are going to cover all of such unique problems, not the easy ones, of course. I know you can do that, but yes, we'll be covering all categories of problems. Okay, no, D is not the right answer, but you try again. Think carefully. Maybe you're missing one of the conditions. I'll give you 10 more seconds and then don't guess. Yes, A is the right answer, but I hope you're not guessing. So how do we actually do this? We have, so the answer is A, by the way. So The one student who got it right, yes, it is correct, but I hope you were not guessing and you were actually thinking of it logically. So this is a very easy problem, bache. This is using all the concepts that we have done already. Very easy. Let's see how. So the third condition, no two consonants are next to each other. What does that mean? That means that, how do we do that? We first place the vowels and between those gaps we place the consonants to make sure that no two consonants can be together, right? This is what we did. So first we have to place the vowels. Ideally we would have done 5 factorial, but now we know the order. So there's only one option, I, U, A, I, O, and my vowels are placed, my vowels are ordered because there's only one order allowed. Then we have to place the consonants, right? So first what did we do? We picked 4 places out of these 6 for the consonants. So 6C4, and then we arranged the consonants. But here again the order is fixed. So once, let's say we pick this one, this one, this one and this one. Let's say we pick these 4. Once I picked it, I have my word, I have my arrangement, because the order is fixed. It has to be D, C, T and N, and that is my arrangement. So in total, how many ways to arrange? Just 6C4 or 15. Okay, think carefully, very logically, do not have to memorize any of it. Just learn how to approach all sorts of problems correctly. Okay. Now, let A1, A2 up to AM be non-empty subsets of this given set which has the first 100 natural numbers. They satisfy the following conditions. These M subsets are satisfying these conditions. What are these conditions? This number of elements, this is number of elements in A1, number of elements in A2, number of elements in AM. They're all distinct. It's not possible to have 2 subsets which have the same number of elements. And another condition, they are pairwise disjoint. They don't have anything in common. Any two, take any 2 of these subsets and they will have nothing in common. That means we have to essentially partition this 100 into different. Why partition? We can, of course, it doesn't say that we have to use all of the natural numbers, all of the 100 numbers, right? Of course, we don't have to, but we have to find the maximum possible value of M. So we have to have the maximum number of subsets. So in a way, yes, we are trying to partition it, or we're trying to partition this so that we get maximum subsets which are unique, which don't have anything in common. If one of these elements, one of these natural numbers, let's say 7, is going into one of the subsets, then we cannot put 7 into any other subset. Okay? And the number of elements in each of them will have to be different. So what is the answer? 13, 14, 15, 16. Which option is correct? A, B, C or D? Try again. So yes, A is correct. 13 is the right answer. Very good. Yeah. So for all those students who are getting another answer, just recheck your solution. Think of it. What are you missing? What are you counting? What are you missing? What are you skipping? What are you recounting? In combinatorics, that is what you have to learn. Don't just check the solution what ma'am shares, but actually go through your solution. Where did you make the mistake? That is how you learn. That is how you get better. Trust me, if you're not doing that step, if you're not analyzing your own solution and checking what went wrong, or whatever you thought of, will that give the right answer or the wrong answer? And why is it giving the wrong answer if it is? All of these analysis, all of these questions really help you expand your mind, really help you just be better at maths. Trust me, that is how you're supposed to learn maths. Now coming back to this, so answer is A. Let's see how. We have all of these are distinct numbers, right? The number of elements in A1, the number of elements in A2, and so on. Let's assume this is an increasing order. We can take it in any order. So let's assume, without any loss of generality, that A1, A2, Am, they are all, the number of elements in each of them is distinct and increasing. Now we have to maximize the number of subsets, which means we have to minimize the number of elements. If I take 10 and then 40 and then 70, then I will get very few. But if I take 1, 2, 3 smaller elements in each subset, then I will get more number of subsets, right? So we start with 1. Now this cannot have one element, so we will have the next smallest number 2, then the next one will have the next smallest number 3, and so on. So that means the minimum way of doing it would be something like this, right? Now the total number of elements in this will be 1 plus 2 plus 3 up to m, or m plus 1 by 2. This total elements has to be less than equal to 100, right? Because we're taking some here and then some here and then some here and then some here and so on. So the entire sum cannot be more than 100 because we're not repeating any number. We cannot repeat any number. So the total has to be less than 100. Now we will just solve this. M plus 1 is less than equal to 200. Now this is an increasing value, right? As m increases, this sum will increase. So we have to find the largest m for which this is true. Of course, even for m equal to 1, this is true. 1 into 2, 2 is of course less than equal to 200. But we have to find the largest m for which this is true. So let's check 13. 13 into 14, what is that? 13 into 14 is 2, 13 plus 5, 182. So this satisfies. We move on to the next one. 14 into 15. What is this? 14 into 15, 7210. This does not satisfy, which means the largest m that is satisfying this condition would be 13. We cannot have 14 or higher. After that, this will not hold true. This inequality will not hold true. So 13 is the highest number for which this inequality is holding true. Okay? So this is how you do it. This is how we can maximize the number of elements, the number of subsets. We have to minimize the number of elements in each of them so that we get as many subsets as we can. Okay? Next one. If a 3-digit number is randomly chosen, what is the probability that either the number itself or some permutation of the number, which is again a 3-digit number? Why is it saying which is a 3-digit number? Because, for example, if we have something like 970, then one of its permutation can be 079, but now this is a 2-digit number. So we are not going to consider this permutation. We are only going to consider the permutations which remain a 3-digit number. Okay? So that at least one of the permutation of it should be divisible by 4 and should be divisible by 5. Both. It should be divisible by 4 and by 5. So what is the probability? How many, first of all, how many such numbers are there that either that number or its permutation is divisible by 4 and 5. You check that and then divide it by total number of 3-digit numbers that we have, and you will have your probability. So try this one. Yes, B is correct. I hope again you're not guessing, but yes, B is correct. Very good. That's amazing. Let's see how. First of all, let's see how do we approach such a problem. That is what we're here to learn, right? We're not just here to solve some problems. I know you are having fun solving these problems. I am also having a lot of fun, but it's very important to learn how do we check which method should we use here. So let's understand the question. The question says that the divisibility by 4 and 5. The number should be divisible by 4 and by 5. That means it should be divisible by 20. Only in that case is it possible that the number is divisible by 4 as well as by 5. Right? We have to find the LCM of the two numbers, and that is how we check the divisibility. So first of all, that should be clear. Then we are saying that such numbers which have a permutation which is divisible by 20. So let's do it in the opposite order. We first find all the numbers that are divisible by 20 and then check all their permutations, as long as they remain a 3-digit number, right? So first we check how many numbers are there that are divisible by 20. Then we check their permutations, all possible permutations, and that is how we'll find the total number of numbers that have some permutation, either themselves or some rearrangement, as long as it remains a 3-digit number, that are divisible by 20. So let's start. Now what is the first? Okay, first of all, how many 3-digit numbers do we have? It starts from, what's the smallest 3-digit number? 100. What's the largest 3-digit number? 999. So total is 999 minus the one before this, 99. Out of the first 999 numbers, we are removing the first 99 numbers. So total 900. That is the total. So in order to calculate the probability, this will be our denominator. That we are done with. Now, out of these 900 numbers, first of all, let's check what are the numbers that are divisible by 20. What's the smallest number that is divisible by 20? 100. Then 120 and up to the last one will be 980. Because after that we get 1000, which is a 4-digit number. So like this we have our numbers that are divisible by 20. But now we have to calculate how many permutations we can have. We can't just say 3 factorial or 2 factorial or anything like that, because it can have a repeated digit or it can have all distinct digits. So we have to check. Okay. So let's first of all be very clear about one thing. What is that one thing? That the last digit of all of these numbers is going to be 0. Because 20 is able to divide all of these numbers. They are all multiples of 20, which means the last digit has to be 0. So we have at least 1 0 here. Right? Now, let's say we divide it into different categories. First is all 3 distinct digits. Right? Like 120, 980, all 3 are distinct. Last one will be 0, but the other 2 are non-zero and different from each other. Then we have something like 100, where we have 2 zeros, right? So some non-zero digit followed by zeros. That will be one category. All 3 digits cannot be same. We have 3 distinct and then 2 can be same, but all 3 cannot be same because last one is 0 and the first one cannot be 0. Now another category is there where these two are the same and this is a 0. So whatever non-zero digit we have, it's repeated and the other one is 0, right? Let's look at it one by one. How many such numbers are there and how many permutations are possible for each of them. Okay, so let's look at it one by one. First of all, we have 3 distinct, or rather let's see how many permutations will be there for each of them. Okay, so for 3 distinct, we have something like, let's say 1, 2 and 0. Then for the first position, we will have 2 options out of the 2 non-zero numbers. Then for the second one, we'll have 2 remaining because now 0 can also be here. And then the last one will be 1, right? If we have to find the number of arrangements of such a number 120, then how do we calculate? There are 2 options for the first one, either 1 or 2. And then once we have placed the non-zero, then either here there will be 1 non-zero or 0 and whatever is remaining will be here. We are counting the number of permutations possible of such a number. So here we have 4. Here we cannot have any other arrangement. Why? Because this has to be non-zero, so 0 cannot come here. So only one arrangement is possible of such a number like 100. Now here when we have both of these same, now let's say for example for easier understanding, we have a number like 220. This is divisible by 20, right? So 220 is such a number. How do we find all the permutations? For the first place, only 2 is possible, right? 0 cannot be here. So for here we have one option. Now once we have placed 2 here, now here either it can be 20 or 02, right? So we have 2 options for this and 1 option for this. So total 2 permutations are possible, either 220 or 202. So we'll count both of them. So this is how we will calculate the number of permutations possible for each category. These are all the categories. All we need to do now is count the number of all such numbers. Okay. Again, very logically, we have, let's first check the second category. This is the easiest. We have 100, 200, 300, all of them will be divisible by 20. So we will go from 100 to maximum 900. So total 9 possibilities for this digit. So total we have 9. So from this category we get 9. From this category, in order for this to be divisible by 20, this digit here, this tens digit has to be divisible by 2. It has to be an even number. If it's not, let's say 130, then it's not divisible by 20. So that means we need to have an even digit here, and these two are the same. So that means either this can be 220 or 440 or 660 or 880, right? That's all that is possible. 110, 330, they won't be divisible by 20. We need these 2 digits to be the same. So either 2, 4, 6 or 8. Non-zero even numbers are 2, 4, 6 and 8, non-zero even digits. So 4 options for this, total 8. So now, how many total numbers were there that were divisible by 20? 20 into 5, 20 into 6 up to 20 into 49. So from 5th multiple to 49th multiple, total 49 minus 4, 45. So total we had 45 multiples. Out of them 9 and 4 have been considered, 13 have been considered. So remaining 32 will have all distinct digits, right? So this becomes 1 to 8. So what are the total numbers that are divisible by by 20 or the permutation is divisible by 20. 128 plus 9, 137 plus 8, 145. So the probability will be 145 by 900 or 29 by 180. So this is how you calculate all the permutations, whatever has been asked in the question. Okay. Another way of calculating how many such multiples of 20 are there such that this is, all of these are distinct. We can do that. How can we do that? We have to find number of multiples of 20 which have all distinct digits. So first of all, this has to be 0. Now this has to be an even number but not 0. Otherwise it won't be distinct. So it can be 2, 4, 6 or 8. 4 options. Now out of 10 digits, 0 has been taken and anyway this had to be non-zero. So out of the 9 non-zero digits, 1 has been chosen here. Now out of the remaining 8 we can take any, but we cannot take this one again because otherwise it won't be all distinct. So out of the remaining 8 we can take any one. So for this we have 8 options. So total 8 into 4, 32 options. So you can either count all of them and subtract these two, or you can check how many multiples of 20 are there that will have all distinct digits. Okay. Try this one now. We have a set A which has all the first 30 natural numbers. Number of ways in which one can choose 3 distinct numbers from A such that the product of the chosen numbers is divisible by 9. Why was it 2 into 2 into 1 in the previous question? Because if we have to calculate the number of arrangements of, let's say, a number like 980, how many 3-digit numbers can we make using 9, 8 and 0? That's the question. I know you can solve it. The number of 3-digit numbers we can form using 9, 8 and 0. The first one, the hundreds digit, will have 2 options, either 9 or 8. Then once we fix that, the tens digit will have 2 options, 0 and a non-zero number, and the remaining third digit will go in the ones place. So total 2 into 2 into 1, 4 options, 4 ways of arranging. Okay, C1110. Try again. It's a tricky one. Yes, this problem is not trivial. Just give it a try. 1590, that is perfect, very good. Let's see how. So first of all, we need to find 3 numbers. There is no order, we just need to select 3 distinct numbers from this set such that their product is divisible by 9. In order for this to be divisible by 9, we need to have at least 2 3's in the product. Right? Either we can have something like 9 into 2 into 7, we get 9 from here, or 18 into 2 into 7, something like that, that we have at least one multiple of 9 here. Or we can have something like 3 into 6 into 5. Now we get 1 3 from here, 1 3 from here, and the product will have 2 3's or will be divisible by 9. But something like 3 into 7 into 1. This doesn't have 2 3's. This only has 1 3, so it won't be divisible by 9. Or let's say we have 3 into 27 into 6. This has all the 3's, right? We get 1 3 from here, 3 3's from here and 1 3 from here. This will be divisible by 9. Why? Because we only needed 2. We can have more and that's fine, but we need at least 2 3s for this to be divisible by 9. Or if there is no 3 here, no 3 here, no 3 here, no 3 here, again won't be divisible by 9. So that means it can have as many 3s as it can in the product. The power of 3 can be anything, but we need at least 2. So, and one way to approach this is you check total selections and exclude the one that we don't want. What do we exclude? Either there was 0 3 in the product, or there was 1 3 in the product. As long as there is 2 3s or more, then it will be divisible by 9. So the remaining are good to go. These two categories are something that we don't want. So this is how we are going to go. Let's see one by one what are these numbers. Total selections, out of 30 we are selecting 3. So 30C3. 0 3s. Now we need to check how many multiples of 3 are there, how many multiples of 9 are there, and so on. So multiples of 3, 3, 6, 8, 3, 6, 9, 12 and so on, right? So from first multiple till the 10th multiple, basically 3 is computation table, right? 3 into 1, 3 into 2, 3 into 10. So first 10 multiples are here. So we have 10 multiples of 3. But we cannot just say, so okay, first of all, till here for this category we have 10 multiples of 3. That means the remaining 20 have 0 3s, right? For example, 5, 11, if it's not divisible by 3, then it won't give any 3. So the remaining 20, we have to select 3 out of these remaining 20 and we'll have 0 3s. Now in the last category, we need exactly 1 3 in our product. If I select any one of them, any one of these 10, then I can also select 9, and in that case I will have 2 3s, or I can select 27, I'll have 3 3s. That is not allowed. So basically we have to choose the numbers which are not divisible by 9 out of these 10. So what are the numbers that are divisible by 9? 9, 18 and 27. Other than these 3, if I take any of these remaining 7, so there are 3, so we are left with 7 multiples that give 1 3, right? So if it's 3, 6, 12, all of the remaining multiples will give exactly 1 3. So in this category we have to select exactly 1 out of these 7, and for the remaining 2 numbers we have to select out of those 20, right? Because we need exactly 1 3. So 1 from these 7 and 2 from the remaining 20, and that will give you the final answer. You can calculate 30C3, that is 30, 29, 28 by 6, 20, 19, 18 by 6, and this is 7 into 20, 19 by 2, 10. So we can calculate this way. 30C3, that is 5 into 29 into 28. Okay, a lot of calculations there. 140 into 29. So 14 into 9, that is 126. And 28 plus 12, that's 4060, right? And then we have 57 into 20, so that is 1140, and we have 7 into 19, that's 133, so 1330. So 2470, 4060 minus 2470, that is 1590. Yes. So option A is correct. Okay. Alright, so this is how we approach such a problem. We check. Again, if you remember from one of our lectures, we saw we can also calculate that we have 2 3s or more 3s like that, right? We have 2 3s from different multiples, or we have 2 3s from the same number. Like that, we can also calculate it using that method. That is also fine. You should try. If you thought of that method, you should definitely try and you should get the same answer. But you have to just see whichever you think is easier, less complicated, you should go with that. Alright. Now, let M respectively and N. So, M and N are the number of 5-digit integers that are obtained by using the digits 1, 2, 3, 4, 5. Okay. So, we have 5 digits 1, 2, 3, 4, 5. M is the number of 5-digit integers we get with repetition, and N is the number of integers we get without repetition. The condition for both of them is sum of any two adjacent digits is odd. Then M by N is equal to, try it once. Check your answer again, bache. Yes, 15 is correct. Very good. Let's see how. This is an easier question. I think all you need to remember, all you need to understand is sum of any two adjacent is odd. When is the sum of two digits odd? When one of them is even and the other one is odd. If both are odd, the sum is even. If both are even, the sum is even. So one of them has to be odd, the other one has to be even. Which means it always, any two adjacent. So that means it always has to be alternate. Let's first check what N is. For N, we need to rearrange these because repetition is not allowed. We need to form a 5-digit number. So that means we have to rearrange these 5 digits here such that it alternates between even, odd, even, odd. We have 3 odd, 2 even. So the only possible way is we get odd here and even here, right? So that means we have how many options for odd? 1, 2, 3. 3 options for odd here, then 2 here and 1 here. Or you can say we find an order of odd digits, we find an order of even digits, and that is 3 factorial into 2 factorial. So the answer is 6 into 2, 12. Or you can do it this way, that we arrange the odd ones. Now for the even ones, we have 2 options here and the remaining 1 option here. So 3 into 2 into 2 into 1 into 1, 12. So N is 12. We have our N, which is 12. Now we need to find M. For M, repetitions are allowed. So now, same as before, now there are 2 options. Either odd goes first. So odd, even, odd, odd, or we have this, it starts with an even digit and then we have even, odd, even, odd, even. Now repetitions are allowed, so we have as many options as we can. So now we're not limited that, oh, we have less even, so even cannot start first. But here repetitions are allowed, so even can also start the number or odd can also start the number. Now for odd case, we have 3 options. So 3 options, then 2 options, then again 3 options, because repetitions are allowed. Then 2 options, then 3 options. So we have 3 cube into 2 square, and here we have 2, 3, 2, 3, 2. So total 2 cube into 3 square. We add these two, so m comes out to be, if we take 2 square, 3 square common, we have 3 plus 2. So 4 into 9, 36 into 5, that is 180. So m comes out to be 180. 180 divided by 12, 50. Okay. Let x1, x2 up to x11 be 11 distinct positive integers. Okay, we have 11 distinct positive integers. Now we replace the largest of these integers by the median of the other 10 integers. Then what happens to the median? What happens to the mean? Does the mean increase? Does the mean remain the same? Does the median remain the same? Does the median decrease? Which of them is correct? It's very logical, very based on understanding. Yes, it's fun, right? These questions are super fun. Just very easy. You don't have to memorize anything. You just have to think. That's all. So, which of them would be correct? B. Try again. See, median decreases. That is amazing. Perfect. So, let's see how. Without loss of any generality, I am going to say that the first 10 are smaller and this is the largest. Basically what I am doing is I am arranging them, right? If you want, you can arrange them and then number them A1, A2. If you have a little bit of confusion, then let's say I arrange them, these 11 distinct numbers, such that they are in an increasing order. It's distinct, so they cannot even be the same. A1, A2, A3, A10, A11. Like this, I have them in increasing order. So that means A11 is the largest. What did we do? We replaced A11 by median of other 10. Median. Now they are arranged in an ascending order. So median of 10 numbers, median of even number of numbers will be the mean of middle number. So mean of two middle numbers, A5 and A6. So median of these numbers, A5 plus A6 divided by 2. Now I replace A11 with this. And now I will arrange them again. So what will be the new arrangement? A1, A2, A3, A4, A5 and then this number A5 plus A6 by 2 and then A6, because it's the mean, it will be between these two, and up to A10. We again have 11 numbers, right? Now the total sum of the numbers will definitely decrease, right? The total sum, earlier we had A11, now instead of that we have a smaller number. This is much smaller than A11 because this is somewhere here. So that means the total sum of all numbers decreased. Number of numbers remained the same. So mean will decrease. So mean remains the same or mean increases? No, mean decreases. What about the median? What was the original median? The original median of 11 numbers was A6. For all of these, the median was A6. because it's odd number of numbers, so there was a middle term a6. Here again we have a middle term which is a5 plus a6 by 2. So earlier it was a6, now it is smaller than a6. So that means median decreased. And that is your final answer. Now, this is the last problem from KVPY PYQs, but it's a bit tricky again. So it is kind of like the one we did for 20, but a more difficult version of that problem. So do try this one. If you were able to understand that solution, then I think you can solve this one as well. Just make sure you're not missing any case. So let's go through the question. A denotes the set of all 4-digit natural numbers with no digit being 0. That means all are non-zero digits. B is a subset of A, which consists of all numbers such that no permutation of its digits gives a number that is divisible by 4. Just like before when we were considering multiples of 20, here it's just 4. Then the probability of drawing a number from B with all even digits. So we need the total number of numbers in B and the number of numbers with all even digits. Says answer is C, but I also showed you the answer, so I hope you were able to solve the question and not just sharing the correct answer. But yes, the answer is C. Is anyone else also getting the option C? Yes? Okay, let's see how it actually is C. So we need to understand how we can actually consider multiples of 4. This is very important. This theory can be used in various combinatorics questions. So we have to understand which numbers are divisible by 4. Of course, we know the last 2 digits have to be divisible by 4. That is something, the divisibility rule we all know, right? That means the first 2 digits can be anything. As long as the last 2 digits, this number is divisible by 4. Also, if it's divisible by 4, clearly it has to be an even number, right? The last digit cannot be odd because the number cannot be odd. So, this can be, in this case, non-zero. So, 2, 4, 6 or 8. Now, bache, whenever it's either 2 or 6, this number has to be odd. Whether it's 12, 32, 36, 56, all the numbers such that this tens digit is odd, the ones digit is 2 or 6. Then it's divisible by 4. But if it's even, for example 42, 46, they are not divisible by 4. So with 2 and 6 it has to be odd. With 4 and 8 it has to be even. 24, 44, 68, all of these are divisible by 4. So as long as this is even and this is 4 and 8, or this is odd and this is 2 or 6, then we will have a number that is divisible by 4. So I hope this is clear to everyone how to actually check divisibility, right? Now, we need to check how many numbers are there in the set B. How many numbers or their permutations are there which have divisibility, by 4, right? Now, how we will proceed this is, we are checking odd and even, right? So let's see if all even digits are there, which is what the probability, which is what we have to calculate, right? So all even digits. Now if we have 4 and any other even digit, whether it's 2 or 4 or 6 or 8, we can form a number which is divisible by 4, right? Because with 4 or 8, as soon as we get one even digit in the number, we will have a number that is divisible by 4. So for example, if we have 2, 2, 2, 4, then this is divisible by 4. And even if it is something like 2, 4, 2, 2, now 22 is not divisible by 4, but its permutation of the digits of this number will give a number which will be divisible by 4. So what does that tell us? That tells us that we cannot have 4 or 8. When we are considering all even digits, as soon as we have even one of these, we do not have a number that is not divisible by 4, right? So we need either 2 or 6 in all of the 4 positions. So all even digits, we have 1, 2, 3, 4 digits, 2 or 6 here, 2 or 6 here. Of course, repetition is allowed. 2 or 6 here, 2 or 6 here. So 2 raised to power 4, 16. So these are all the numbers whose permutation is not going to give us a number that is divisible by 4, and it will have all even digits. Now let's say it has all odd digits. Even then we won't have any number that is divisible by 4, right? No matter which permutation we take, we will not have a number which is divisible by 4 because it has all odd digits, right? So how many odd digits do we have? 1, 3, 5, 7, 9, 5 odd digits. So 5 can come here and then 5 can come here. Repetition is allowed. So total 5 raised to power 4, 625. Now let's consider the case when we have one even digit and 3 odd digits. Now let's think about it very carefully. If we have 2 or 6, okay, if that one even digit is either 2 or 6, then we can form a permutation where the last digit is that even digit and any odd number, any odd digit before that, and that will be divisible by 4, right? Because 2 and 6 need odd digits before them. So with 2 and 6 we have to have all even options so that no permutation is divisible by 4. So in that case only 4 or 8 are possible, and then 3 odd digits, that can be 5 cube. We have 5 options for them, right? So 5 cube into 2 options for the the even digit, and then we also have to find the arrangement, right? Where is this odd digit? Where is this odd digit? We find a place for that. Out of these 4, one place has been selected for the even digit and the remaining 3 are odd. Okay, so this comes out to be 8 into 125,000. Now what are the cases that are left? We can have 2 even digits, 2 odd digits. Now again, just like the previous logic, if we have 2 odd digits, then 2 or 6 cannot be there, because with one of the 2 or 6 and one of the odd digits, we will form a number which is divisible by 4. So 2 or 6 cannot be there. How about 4 and 8? 4 and 8 can also be there by this logic. If 4 and 8 gets another even digit, which it has because there are 2 even digits, if we place 4 or 8 here and then any other even digit here, then we get a number which is divisible by 4. So this case is not possible. Similarly, 3 even digits are not possible by the same logic. Even if we have 1 odd digit, 2 or 6 cannot be there. And if we have 3 even digits, even if we have 2 even digits which are, and one of them is 4 or 8, then it will be divisible by 4. So these cases are not possible. So the total is 16 plus 625 plus 1000 and numerator will have 16. So 16 divided by 16 plus 625 plus 1000. That will be your answer, which is 16 by 1641. Yes, bache, class 10 students can totally understand this, but you have to go through the lectures. If you haven't studied the theory, then I recommend that you go through the 10 lectures that we have done before this, and this is using all of the concepts altogether. Okay, so this is how we count the total number of permutations, where we can find one of the permutations which is divisible by 4 or not divisible by 4, right? So this is a very important question. This is a very good question to help you understand all possible arrangements, all such questions. This is, I think, a very good question. So you should definitely revise this. You should have this in your notes whenever you revise your theory. This question is a good one. It will help you understand a lot of concepts at one place. Okay. Now, let's do an easy one. We have done a few tricky ones. Let's take a break from the difficult ones and let's do an easy one right now. So find the number of ordered triplets A, B and C of positive integers such that their product is equal to 108. Yes, what's the answer? Quick. Yes, beggar coin, but what's the answer? Yes, there will be another lecture like this. We won't be able to cover all the PYQs, all the important PYQs in just one session. So yes, there will be another one very soon. I will announce it on the channel when I will be taking the next one. 60, that is correct. Very good. So let's see how we get this. We have, first of all, let's find the prime factorization of 108. It is 2 raised to power 2 and 3 raised to power 3, right? 4 into 27, that is 108. Now we have to find A, B, C, 3 numbers such that A is 2 raised to power x1, 3 raised to power y1. If we have any other prime number here, then the product will not be equal to 108, right? Now these numbers can be 0. It is possible that it only has 3, it only has 2 or none of them. 1 is also allowed, but it has to be only powers of 2 and 3. Similarly, 2 raised to power x2, 3 raised to power y2 for B, and C is equal to 2 raised to power x3, 3 raised to power y3. When we multiply these, we get 2 raised to power x1 plus x2 plus x3, 3 raised to power y1 plus y2 plus y3. This has to be equal to 2 raised to power 2, 3 raised to power 3. Which means this is our multinomial problem, where x1 plus x2 plus x3 is equal to 2 and y1 plus y2 plus y3 is equal to 3. x1, x2, x3 can be 0, 1, 2. y1, y2, y3 can be 0, 1, 2, 3. Standard problem, we can use the formula directly. N plus r minus 1 Cn multiplied by n plus r minus 1 Cn. So 5 minus 1 4 C2, 6 minus 1 5 C3, 6 into 10 60. That is your answer. Yes, bache, it is possible that some of the questions are very easy. Yes, so I have only picked the hard ones mostly But yes, this is an easy one just to show it to you that it is not always very difficult. Not every problem is going to be very difficult, especially if you have practiced all such questions. Then you will find more and more problems easy, right? The more you practice, the more you will be familiar with such questions, and you'll be like, yeah, this is something I have done, this is something I know, this is so easy, this is so basic, I know how to approach this. So with practice you will find more and more questions super easy. Okay, now let's try another one. A postman has to deliver 5 letters to 5 different houses. Mischievously, he posts one letter through each door without looking to see if it is the correct address. He just randomly posts a letter anywhere. There are 5 letters, 5 houses. He knows, okay, these were 5 houses. I have to send my letters to these houses, but he doesn't care where the letter is going, and he's just posting them randomly. Now delivering them randomly. And how many different ways could he do this? What is the condition? Such that exactly 2 of the 5 houses receive the correct letters. Derangement, yes. What's the answer? 5C2 into D3, perfect. Very good. So, we have to first find which 2 houses get the right one, right? There are 5C2 ways of selecting the 2 houses which get the correct letters, right? So, we have to find which 2 houses get the correct letters. Now, out of the remaining 3 houses, we need to make sure that they don't get the letter they were supposed to get. Anything else is allowed, but the letter that was supposed to go in these 3 houses, that is not happening, which is nothing but derangement. So D3. So 5C2 into D3, which is 10 into 2, 20. If you don't memorize D3's value, that is also okay, bache. D3 is 3 factorial 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial. So this is 6, 1 minus 1 plus half minus 1 by 6. This is 0. 6 into half 3 minus 6 into 1 by 6 1, 2. So 10 into 2, 20. That is your answer. Easy again. So just have to understand these questions. They are not very difficult in a lot of these cases. This is very trivial. Just have to think how to actually count all possible cases. There are n. This one is also easy. We are going to do more difficult ones by the end of this class. Yes, there are some tricky ones in pre-RMO, PYQs as well, don't worry. And we will be doing a lot more trickier ones in the next class from pre-RMO as well as from IOQM. Okay? Now, let's take a look at this one. There are n minus 1 red balls, n green balls, n plus 1 blue ones in a bag. The number of ways of choosing 2 balls from the bag that have different colors is 299. What is the value of n? Quick. I'm waiting for your answer, बच्चे. This one's an easy one. Come on. Perfect. Easy, right? So we have to select 2 balls out of these 3n. Total n minus 1 plus n plus n plus 1. We have 3n different balls and we have to select 2 balls such that they have different colors. So either it can be RG or GB or RB. Right? These are the 3 options for 2 different colors. Now for RG, we have to select one from these n minus 1 and one from these n. Or translates to plus. If it's an or, then we have to add. GB n into blue n plus 1 plus R into B, that is n minus 1 n plus 1. This is equal to 299. That's it. Now it's easy. We take n common out of these 2 and n minus 1 plus n plus 1 becomes 2n plus this is n square minus 1 is equal to 299. This comes out to be 2n square plus n square, 3n square minus 1. So plus 1 is 300, n comes out to be 10. Now, to each element of the set S, so S has first 1000 natural numbers now. We are assigning a color to all of these 1000 numbers. Okay, we have to assign some color to each of them. Now, what is the condition? Condition is that if for 2 numbers A and B, if 15 divides A plus B, that means A plus B is a multiple of 15. 0 is also a multiple of 15, even though 0 is not possible. 15 is also a multiple of 15 and so on. So, if 15 divides A plus B, then they are both assigned the same color. If A and B, the sum of A and B is a multiple of 15, then they have to have the same color. There is no other condition. Now we have to see the maximum possible number of distinct colors that we need to use. Seven or 8? Decide. 8? 8 is the right answer. Very good. So, just like before, we have to check the remainders, right? When we were checking the sum is divisible by 5 or not, it's the same way. For the numbers, what are the possibilities for remainders? Remainder can be 0, 1, 2 up to 14. Now, each of these numbers which are divisible by 15 themselves, right? 15, 30, 45, all of those numbers will have the same color. Why? Because you take any 2 of them and their sum will also be divisible by 15. So, they have to have the same color. So, there will be one color for this category. Now, whichever color this category gets, any number in this category will have the same color as this category because their sum will be divisible by 15, right? So, for example, leaving a remainder 1, that is something like, let's say 1, and leaving a remainder 14, let's say 29. So, 1 plus 29, that is 30. So, their sum will be divisible by 15. So, we have to give the same color to these two. So, a maximum one color can be used for both of these categories. Take any number from here, any number from here, and they have to have the same color. So, that means all of these numbers will get the same color. Similarly, all of these will get the same color and so on. So, these are 14 categories. How many pairs can we make? 14 by 2, 7. So 7 into 1 plus 1 for this one. So 7 plus 1, 8 is the right answer. What is the number of ordered pairs A and B where A and B are subsets of 1, 2, 3, 4, 5 such that neither A is a subset of B nor B is a subset of A? We have to remember ordered pairs. So order matters. It's not just that we are selecting two subsets. We are checking which subset is first and which subset is second. $570, yes, that is the right answer. Good. So let's see one of the ways to do this. Number of ordered pairs A and B where A and B are subsets. Okay. So what do we have to check? We are checking let's say A has 0 elements. That means A is 5. Then out of any of these we can have a subset, right? So out of any of the remaining ones, see, there are two ways of doing this again. Either using the direct approach or the exclusion approach. What we can do is we can check the total number of subsets that are the total number of ordered pairs that are possible. How many total subsets can we have for this? 2 raised to power 5, that is 32. So 32 options for this, 32 options for this, total 1024 options are there. We are going to exclude the cases where A is a subset of B or B is a subset of A. One of them is a subset of each other, right? So if A has 0 elements, we took some 0 elements. Of course, there's only one way of forming such a subset. Now B has to come from its subset, right? B has to, let's say if B is a subset of A, then out of these 0 elements, A has to be one of the B has to be one of the subsets of A. Similarly, if A has 1 element, then 5C1 to find A, and then for B we have 2 raised to power 1. Out of these 1 elements, out of these 1 elements in A, we have to find a subset of B. So like this, we will have 5C2 into 2 raised to power 2 up to 5C5 into 2 raised to power 5. Like this. Now, if we add this, their sum is 1 plus 2 raised to power 5, right? Using binomial expansion, if we replace 1 plus x raised to power n, where x is 2, then we will get our expansion. So this is nothing but 3 raised to power 5. But you might say, ma'am, this is only counting this case. What about the opposite case? Because they are ordered pairs, what if A is a subset of B now, not B is a subset of A? Then we just flip the order, right? So into 2. So that means we do this. 2 into 3 raised to power 5. But are we sure we are not counting any case again? What about when A is equal to B? Then we don't have to count them again because we have already counted this ordered pair. We multiplied this entire thing by 2, but which cases did we count more than once? This case, when A was equal to B, then A comma A was the ordered pair we had already selected, and now we are saying we have to select it again. We don't have to do that, right? So what will we do? We will subtract out of 2 into 3 raised to power 5. We will subtract the cases where A was equal to B, which means as soon as we got A, we knew what B was. So when A had 0 element, we've selected A and that's it. Then we know what B is. We don't have to find the subset of B. We don't have to find the subset of A to find B. We know what B is. So 5C0, 5C1 up to 5C5. As soon as we know what A is, we know what B is, and these are the cases that we counted twice. So we have to exclude it once, which means 2 into 3 raised to power 5 is 243 minus, what is this? 2 raised to power 5. So what does it come out to be? 486 minus 32, that is 454. These are the cases where A and B are subsets of each other. Out of the total ones, we have to subtract this. So finally we get 1024 minus 454, that is 570. Clear? So this is one of the ways you can do this. Of course, you can also check it directly. If A is a subset of B or A is not a subset of B, once we fix A, we have to find B from the remaining elements. So like that as well, you can do that and you will get the answer. Just make sure that none of the cases are being repeated. You have to make sure that the ordered pair is considered. Not just that we have to select 2 subsets, but we are actually selecting the order of the 2 as well. Okay? Now, let's take a look at another problem. A subset B of the set of first 100 positive integers has the property that no 2 elements of B sum up to 125. What is the maximum possible number of elements in B? Quick. The first 100 positive integers, we have a big set. And now we are taking a subset of this set such that no 2 elements of B sum up to 125. What will be the answer? No. Let's see. Which two numbers are giving the sum 125? Let's first think of that. You know, whenever you're stuck, just think of some examples. Which numbers do we have to take? Which numbers we cannot take together? Like that. So, which 2 elements? Any 2 elements cannot have the sum 125. Which 2 numbers have the sum 125? 25 plus 100. Or if we increase this by 1 and decrease this by 1, like this, we will have until 62 plus 63. Then again it starts from 63 plus 62, 64 plus 61, that we have already considered, right? So these are the pairs, order doesn't matter, right? These are the pairs which have the sum 125. How many such pairs are there? From 25 to 62, that is 62 minus 24, 38. So out of these 38 pairs, we have to take max 1. As soon as we take more than 1 from any of these, as soon as we have, this is again pigeonhole principle, right? If we have taken 39 numbers out of these, then two of them will come from the same pair, and in that case the sum will be 125. So we have to take 38 numbers at max. We can take 38 out of these 38 pairs. Any of them is fine. You can take any one of them. It's either this or this or this, but maximum one number from each pair. So 38 from here. And the first 24, 1, 2 up to 24, you take any of them, they cannot have the sum 125. Even the largest of this with the largest number present, 24 plus 100 is still less than 125. So you can take all of these, they will never form a sum 125 with any number present. So you can take all of them, which means maximum you can take 24, maximum 38 from here. So 24 plus 38, 62. Very good. And let's do the last question for the day. Alright, there are 5 cities A, B, C, D, E on a certain island. Each city is connected to every other city by road. There is one road that goes from A to B and B to A. There is not a different road that goes from A to B and then you have to take another road from B to A. There is one road connecting A and B. And like this, it is connected to every city and every other city is also connected like this. It's a fully connected graph. Okay. Some roads might be missing in my diagram, but you get the picture, right? Every city is connected to every city. You have a way of directly going from one city to another without having to go anywhere else. Now, what is our problem? Our problem is we have to start from A and come back to A after visiting some cities without visiting a city more than once and without taking the same road more than once. If we have been to B, let's say we took this route A to B. Now I cannot come back to A because B to A, this road has already been taken. I cannot go back on this road. I have to go somewhere and then go back. Let's say I go to C and then C to A. Now this is one such way of starting from A and then returning back to A, which means at least 2 cities need to be visited. If you start from A, go somewhere and then come back, you cannot just visit one city because you've already used this road. You cannot use this road. You have to go through another city. So at least 2 cities will be used. Now the order also matters. It's not just that which 2 cities are you taking, B and C, but in what order? Did you go to B and then C and then A, or did you go to C and then B and then A? They are different. So how many such routes are possible? Answer is 60. Very good. Let's see how. So what do we have to, what is our problem now? Our problem now becomes that we go from A, go to some cities and come back. And we have to tell which order we are going in. So now either we can have 2 cities, we cannot have 1 cities, right? We can have 2 cities between A and A, or we can have 3 or 4 and that's it. Total 5. So that means we only have maximum 4 available between A and A, right? So now we have to check which 2 cities out of these 4. We take 2, we take 3, we take 4. Which 2 cities are we going to? And then which order we are going in. So into 2 factorial, into 3 factorial, into 4 factorial. So this comes out to be 6 into 2, 12, 4 into 6, 24, 1 into 24, 24. You add these up and you get 60. Okay, so this is a basic problem You just have a complicated question, a complicated language in the question, but in the end the problem is very simple. You just have to calculate how many ways we can have our problem. Now it's a linear problem. Instead of a graph, instead of a complicated graph, it's just a linear problem. We have to find the cities, unique cities. You cannot go back to a city. If you visited it once, it is done. So you have to find a unique city to go to, and you have to find an order, and that's it. We will start with some more pre-RMO questions, and then we'll move on to IOQM questions since 2021, right? Good afternoon, good afternoon. Yes, so we have 2023, we even have 2024 questions. So yes, this includes all PYQs, but not all of them. But yes, PYQs from all the years. I have handpicked the questions that I feel will be really helpful for you. So let's start. Okay. Try this one. There's a set. So just to let you know, guys, the questions that I have selected for today are not going to be as easy as the previous sessions. This is the last session that we are having in this series, which means we have to finish it with a bang, right? We are going to solve some very tricky, some very difficult questions, to say the least. So keep your minds open, just think from every angle, and once you're done with the question, once you're done with the solution, and write your answer in the comments or in the chat section. Okay, so we have a set 5, 6, 7, 8, 9 for any partition A, B of E. That means we are partitioning this set maybe like this, or like this, or maybe 5, 6, 9 and 7, 8. So like this we can partition our set into two sets such that A and B are non-empty. Now consider the number obtained by adding the product of all elements of A to the product of all elements of B. We're taking A and B and we're multiplying the numbers in A, we're multiplying the numbers in B, and we're adding the two products. Let n be the largest prime number among these numbers. Find the sum of digits of n. 17. Yes, 17 is the correct answer. Good job. Let's see how. So, what do we want? Largest prime, right? So, let's say A has elements A1, A2, A3 or A4. It can be either 4 elements or 3 elements. See, first of all, what do we have to understand? We have to understand that it doesn't matter which numbers go to A and which numbers go to B, as long as there's a partition, because the order doesn't matter here, right? So let's say A has more elements than B. They cannot have equal number of elements because there are 5 in total. Now what are the options? Either A has 4 elements and B has 1 element, or A has 3 elements, B has 2 elements. That is the only possible partition that we can have, such that both are non-empty, right? Now assuming that A has more, right? Because it doesn't matter which one we're taking first. Even if B had more, it didn't matter, right? We need the largest prime number. It doesn't matter how many ways we can partition this. Now, an important thing here is we need a prime number, right? That means if 6 and 8 are in different sets, right? Let's say A has A1, A2, A3, A4 and B has 1, so the product will be B1. And in this case, the product will be A1, A2, A3 plus B1, B2, right? Now, if 6 and 8 are in different partitions, that means 6 will be here, 8 will be here, or 8 is here, 6 is here. But in that case, we can take 2 common out of both of these products and the resulting number will be an even number. Even in this case, if 6 and 8 are in different partitions, then we can take 2 common out of those and That is why the resulting number will not be a prime number. Now, similarly, 6 and 9. If they are in different partitions, we can take 3 common out of those. So again, it won't be a prime number, which means 6, 8 and 9, all 3 of them have to be in the same partition, because 6 has to be in the same partition as 8 and 6 has to be in the same partition as 9. So we know, and it cannot be in B because B has less number of elements. So we know 6, 8, 9 are fixed here. Now here it's 5 and 7. Here we have two options, either 5 or 7, and likewise B1 will be 7 or 5. Now we need the largest numbers, right? So we will start checking in the descending order. What is the largest product, the largest prime possible, right? So the largest will be not when we are just multiplying these three numbers. If we are multiplying 6 into 8 into 9, then it will give a smaller number as compared to when we further multiply it with 5 or 7, right? So this will give the larger number. So the largest will be 6 into 8 into 9 into 7 plus 5. What is this value? I'm going to use a calculator because otherwise the entire session will take a lot of time. But if you have calculated, so this comes out to be 3029. Now we check if it's a prime number. You start checking, it's not divisible by 2, it's not divisible by 3, it's not divisible by 5, it's not divisible by 7, but 11, no, not even 11, 13. If we divide it by 13, what do we get? 2, 42, that is 3, 39, 3. So this is not a prime number. We move on to the next one. 6 into 8 into 9 into 5 plus 7. And this is 2167. This is clearly divisible by 11 because 7 plus 1, 8, 6 plus 2, 8. So this is divisible by 11. I don't even need to check what will be the quotient, what will we get when we divide it by 11, because we can clearly see that it's divisible by 11. So these two are not possible. The only possibility we have remaining is this one, which is 6 into 8 into 9 plus 5 into 7, which comes out to be 432 plus 35, 467. And now you can check that it is a prime number. So the sum of digits of n will be 4 plus 6 plus 7, that is 17. Okay. Now, how many 4-digit numbers A, B, C, D are there such that A is less than B, less than C, less than D, and B minus A is less than C minus B is less than D minus C? So how many such 4-digit numbers can we have? If you're not here to study, please do not disturb the students who are sincerely studying, because we are preparing for the Olympiad. We do not have much time left. So if you're not here to study, you can leave this session, bache, that's totally okay. But I would request that the chat remains clean and the students can actually answer, and I can see the answers here. Okay. 21. Is the answer 21? No, the answer is not 21. So the answer is 7. Let's see how. See, first of all, we have a number A, B, C, D. These are our 4 digits. Now, they are in increasing order, strictly increasing, no repetition allowed, right? And what can be the smallest number? The smallest digit is 0, but because it's a 4-digit number, A cannot be 0. So, A can start from 1 and it can go till 6, right? And the minimum value of A is 1, maximum value of D is 9, right? Now, we are checking the difference between the digits. We know they are increasing. Let this difference be X, this difference be Y, this difference be Z, right? So, X is less than Y, less than Z. And if we add these differences, basically if we add these differences, A plus X plus Y plus Z, we get D, which means X plus Y plus Z is D minus A. And the maximum value of D minus A is 9 minus 1, 8. So, this has to be less than equal to 8. And minimum value of the difference will be when it's 1, 2 and 3, because X has to be less than Y less than Z. So, minimum value will be 6. So, it has to be between 6 and 8, which means X plus Y plus Z can be 6, in which case this is 1, 2, 3. X plus Y plus Z can be 7. In that case, it will be 1, 2 and 4. No other possibility is there, because it has to be in an increasing order. X plus Y plus Z is 8. What are the possibilities here? Either it can be 1, 2, 5 or 1, 3, 4. And these are the possibilities for the difference, right? Now, let's check each case one by one. For 1, 2, 3. D minus A is 6, right? Which means D is A plus 6. Now, D has to be less than equal to 9, which means A has to be less than equal to 3. So, it can be 1, 2 or 3. In total, we get 3 possibilities for A, and accordingly, we will have B, C and D. Once we fix A, we get B, C, D. Similarly, we will do for the others. 1, 2, 4, D is equal to A plus 7, which is less than equal to 9. So, A is less than equal to 2. So, 2 possibilities. Then, for both 1, 3, 4 and 1, 2, 5, D is equal to A plus 8. So, A has to be 1. So, we get 1 for this, 1 for this. So, 3 plus 2, 5 plus 1, 6 plus 1, 7. So, 7 possibilities are there. So, like this, you can calculate for even a larger number, but this will make sure that you do not miss any case. Alright. Now, IOQM problem. This one is, I think, relatively easy. What do you think? 3 couples sit for a photograph in 2 rows of 3 people each. We have row 1 and row 2. Now, what are the conditions? No couple is sitting in the same row next to each other. They can sit away from each other, but no couple is sitting in the row next to each other, and no couple is sitting in the same column. If husband 1 is here, then wife 1 cannot be here. So, like this, we have such possibilities. Now, we have this condition. Now, how many arrangements are possible? think even JEE students should try these questions. These are very good questions. These are some of the questions that you should practice for JEE Advanced. So I think combinatorics is a topic that is, that is something that you can easily solve even if you're preparing for JEE and not for the Olympiad, because the curriculum is quite overlapping. It's mainly logical, and JEE Advanced does tend to have very tricky problems just like the Olympiads. Anyway, but yeah, I think Olympiads are harder. What? 96. 96 is 96 the answer? Yes, 96 is the correct answer. Good job. Let's see how. Now, let's say the couples are H1, W1, H2, W2, H3, W3. Right? Let's say the couples are one wife, one husband, one wife, one husband, one wife, one husband. Now, let's take it case by case. Case 1 is all men in same row. That is, let's say it's in row 1. So, all men are in same row. Now, what is the possibility? First, let's arrange these men. We have to first pick the row. So, 2C1 into arrange the men 3 factorial. Now, we have to arrange the women such that woman 1 cannot be here, woman 2 cannot be here, woman 3 cannot be here. Right? So, that is nothing but derangement, which is 2 into 6 into 2. So, 24. Right? Now, case 2. Two men, one woman in one row, and correspondingly there will be 2 women and 1 man in the other one. So first let's select which row will have 2 men. So we selected the row. So let's say it was first row, and now we have to select which woman can be here. Let's say this case has, this woman is from the third couple. Right? So that means this is W3. We'll check if it's W1 or W2 in the other case. Okay? But now, for now, let's say there are 2 men and 1 woman in this row. So we first selected which row, and now we have to select the seat for the woman. Right? It can either be here or here or here. So 3C1. Now we have to arrange the remaining H3, W1, W2. Now it's the same as derangement. H3 cannot be here, W1 cannot be here, W2 cannot be here. Right? So this is again D3 and no, actually we don't even have to do 3C1. We will just do 3 factorial. Why? Because these 3 can be arranged in any way. It's not like H1 and H2 order is fixed, right? So it can be H1, W3, H2, just like before. We have to just arrange these 3 people. So it's 3 factorial, which is the same as that expression. So this again is 24. Right? Am I missing something? Right? Now, what are the cases are there? We have a case where When H1, H2 and let's say W1 are in the same row, right? Let's say we have these three in the same row. In that case, what was the condition? That they cannot sit next to each other. So that means H1 and W1 have to be in the corner. It can either be H1, H2, W1 or the reverse order, right? That is fine. But now we have H3, W3 and W2 remaining for this. Again, these two cannot sit next to each other, so they have to go in the either side, right? It can either be H3, W3 or W3, H3. But W2 will have to go in the middle. And in that case, this couple is sitting in the same column, which is not allowed, right? So this case will have 0 possibilities. Similarly, if we have W2 sitting here, again by the same logic, that means the same couple can never sit in the same row. So that next to each other was irrelevant. Basically, the question just had that the couple cannot sit in the same row. Even if they are not sitting next to each other, it's not possible that the other couple is not in the same column. Is that clear to everyone? Yes? Yeah. Let's see just for a second what we're missing. All men in same row. Yeah. In this case, we have 2 men and 1 woman in the same row. But which one woman is sitting with the other 2 men? We have to select that woman as well, right? Which couple are we which woman are we taking and making her sit with 2 men in the same row, right? So in addition, we will have to select which couple this woman belongs to. So that means this is 3 is equal to 72, and now 72 plus 24, that is 96. Okay, complicated, yes, but this is how we have to consider it case by case, making sure that we're not missing any case. Okay, another 4 married couples that we have to arrange. They are sitting in a merry-go-round with identical seats such that men and women occupy alternate seats. Okay, so there's a merry-go-round with 4 married couples, so 8 seats. So we have 8 seats, 8 identical seats. That means these seats are not numbered. We are not saying that one has to sit here to one seat is different, second seat is different. They are just 8 identical seats, so circular arrangement, right? Now, what is the condition? The condition is that men and women occupy alternate seats, okay? And no husband is seated next to his wife. Strike one. $57 is the answer. 57. No. Is it 96? I don't think it's 96. Let me check. 96 is not the correct answer. The answer there is wrong. The answer there actually hasn't been changed since the previous slide. So let's solve it. But I know what the answer is. Yes, 12. 12 is the correct answer. Let's see how. It's very easy. Just you have to think very logically. Okay. So let us, because they are identical seats, we will follow the circular arrangement problem. How did we do that? We fixed one person and then we arranged everyone else around that person, right? N minus 1 factorial. So let's first arrange the men. So let's say we have husband 1 sitting here, because it's identical, it doesn't matter. So we fix the seat of first husband. Now one husband goes here, one here and one here, because they have to sit on alternate seats, right? Now we have to arrange these 3, so 3 factorial. Now let's say this is our arrangement. We name these as husband 2, husband 3, husband 4. Now we have, what are the options here? W3 or W4, because wife 1 and wife 2 cannot be here. Similarly, wife 1 or wife 4, wife 1, wife 2 and W2, W3. Now, as soon as we fix any one of them, let's say I picked W3 to sit here, then W3 cannot sit here because she's already sitting there, so W2 will have to occupy this seat. W2 has occupied this seat, which means W1 has to occupy this seat, and W1 cannot sit here, so W4 occupies this seat. So as soon as I fix one of them, all of the others are fixed. Similarly, if I fix W4 here, then W1 will have to go here, W2 will have to go here and W3 will have to go here. So I have 2 possibilities for this, and as soon as I fix the woman to sit here, then the others are fixed. So 3 factorial into 2, which is 6 into 2, 12. Alright. So this is how you're supposed to arrange these in a circular arrangement. Find the number of maps F from the set 1, 2, 3 and the possible values are 1, 2, 3, 4, 5 such that f of I is less than equal to f of j. This is a pretty standard problem. We'll look at it, how we can actually do it, but just try it once. So the condition is that f I is less than equal to f of j for every I less than j. That means if 1 is less than 2, then f of 1 will be less than or equal to f of 2. F of 2 cannot be smaller than f of 1. Easy? Yes. Let's see how we actually do this one, okay? Because I don't think we solved it in our theory session. So let's just look at one of the examples here so that you can handle any such problem in your exam. So f of 1, let's say f of 1 is A, f of 2 is B, f of 3 is C. So what's the condition? A is less than equal to B, less than equal to C, right? That is our condition. Now, and the values A, B and C can take are from here, which means if I have fixed B, if I know what B is, then what are the options for C? C can be B, B plus 1 and so on up to 5, right? And if I have fixed A, then B can be just like this. B can be A plus 1 up to 5. So we have to just count the number of possibilities for each of them. So if we have fixed A, then B can be 1 or 2 or 3 up to 5, right? And C can be 1, 2, 3 up to 5. Then again 2, 3 up to 5. So when B is 1, the possibilities for C is 6 minus B. B to 5, that is 6 minus B. So 6 minus 1, 5, 4, 3, like this, 1. So once we have fixed A as 1, then it can go from 1 to 5. If we had fixed A as 2, then we would have 2, and then here we have 4 options, 3, 2 options. So like this we have 1 option. So basically what we are doing is we have how many options for C? 6 minus B. And B can go from A to A or just simply we are doing sigma I goes from 1 to 5 for this, right? 1 to 4 for this, 1 to 3 for this. So basically what we are doing is we are doing sigma I goes from 1 to R, right? And R can go from 1 to 5. This is the sum we are doing because we're taking the sum 5, 4, 3, 2, 1. That will be when R is 5. Then last one will be when A is 5. Then B and C have to be 5, and in that case we only have one option. So when R is 1, then I will go from 1 to 1, and that will be what we are adding. So this is what we are solving, and now it's just simple. So sigma R square plus sigma R, that comes out to be half into 55 plus 15, so 70 by 2, 35. Alright. So this is how you're supposed to actually, if we went totally logically 6 minus A, 6 minus B, then the calculations would have been a little complicated, and I could explain this conversion of sigma as in how we can convert 6 minus A to R, but directly, logically, it just makes sense, right? That this is the sum that we are trying to calculate. So let's just find the sum, and the final sum is 35. Now we have some problems related to coloring, right? So again, there is not anything that you should do separately. If you just understand these problems logically, make the cases one by one, making sure you're not missing any case, then definitely you can do it without learning any new theory. Let's see how. We have a convex hexagon, not necessarily regular, just a convex, something like this. They are colored red. Okay. Each of the diagonals of the hexagon is colored either red or blue. Diagonal means any line segment joining 2 points that are not adjacent vertices, right? So for example, this or this, these can be red or blue, right? So how many of these are there? 5 again. Sorry. How many will be there? Total we can select 6C2 line segments, right? 6C2 can join any two of these 6 points. Now we have already taken 6 sides, so the remaining diagonals will be 6 into 5 by 2 minus 6, 15 minus 6, that is 9. So there will be, 9 line segments like this. I'm not going to draw all 9 of them here because it will be very crowded and you will not be able to understand the figure, but you get which 9 diagonals we're talking about. So just join any two points that are not adjacent and you get one of these 9 diagonals. So these can be either red or blue. Now n is the number of colorings such that every triangle AIAJAK, basically to tell that we have a unique triangle. This is, let's say, A1, A2, A3, A6. Like this we have 6 vertices, and now we are taking any of these triangles. And what do we want? We want that every such triangle will have at least one red side. Now, if our triangle has any one of these sides, then we have a triangle that has at least one red side, right? Because we are including one of these sides. Which cases have we not taken care of? The cases when our AIAJAK triangle has none of the sides, none of these 6 sides as one of its sides. So which will be those triangles? Either if we join this, this and this, or A1, A3, A5, right? So it will either be A2, A4, A6 or A1, A3, A5. All the rest will have adjacent sides, right? Will have at least one of these sides. Adjacent vertices, basically at least one of these sides. So the only 2 triangles now we haven't taken care of is these 2. And with these 2 we have 6 diagonals. So we have to find the number of colorings for these 6. The rest can be anything, right? So the new problem becomes that what will be the total possible number of colorings for these 6 sides or these 9 diagonals, because we have covered those 6 sides. We have colored those 6 sides. We have to color these 9 diagonals, and out of these 6 we have to put the constraint on. The other 3 can be anything, right? So now we have to check what are the possibilities for these 6. All the serious students, I know you're getting disturbed by all the other irrelevant messages in the chat, but it's okay. Just ignore them and focus on the question. And once you have the answer, just write it in the chat. I'll give you a few more seconds while I explain the question again. And if you're not able to solve, it's okay. It's not a trivial question. So we will go through the question, go through the solution together. Now, the question is that we have 6 sides, right? It's a hexagon, it's a convex hexagon, but what is the condition? That it's not necessarily regular. It's a random general hexagon. Now we have colored each side of this hexagon as red, right? Now we have to color the remaining 9 diagonals. How did we get the 9 number? Because in how many ways can we connect 2 of these 6 points? 62. Out of which we will also get A1, A2, A2, A3 and so on, right? So we will subtract 6 and the remaining 9, 15 minus 6, 9, that will be the number of diagonals that we have, and we have to color these. So total ways of coloring these 9 diagonals is 2 raised to power 9, right? Because they can be either red or blue. But now we have a condition that every triangle AIAJAK, you pick any 3 of these vertices and you will have a triangle, and now each of these triangles needs to have at least one red side. So if we are picking 2 adjacent vertices, then we have made sure that they have that triangle has at least one red side, right? The only 2 triangles that we have in which we do not have this condition met is A1, A2, A1, A3, A5 and A2, A4, A6, right? So we have to just check how can we make sure that they have at least one red side. The sum of squares of digits of 9 is 94. What is the n we are getting? 94 is the correct answer, yes. But what is n? Because we need sum of squares of digits of n. So yes, if you have got the square, 94 is the correct answer. The sum of squares of digits should be 94. Okay, chalo, let's see how do we actually do it. So this is actually a problem of inclusion exclusion, right? We have to see we have to have at least one red we have to have at least one red side in each of these triangles, right? So let's define the opposite of this. Let's define a set where A1, A3, A5 have all blue sides. And similarly, B is our set where A2, A4, A6 have all blue sides. What do we need? We need to find number of elements in A union B, and we will subtract that from 2 raised to power 9, which is our total number of colorings, and this will be our final answer. So n of A will be, we color all these 3 blue and the rest can be anything. So 2 raised to power 6, we have fixed the color for A1, A3, A3, A5 and A1, A5. So 2 raised to power 6, that is 64. N of B will be the same, 2 raised to power 6, because now we have fixed the colors for A2, A4, A6, these 3 sides. The remaining can be anything. Of course, we have an overlap here, so we have to subtract N A intersection B and A intersection B. That is, these 3 are blue and these 3 are blue. Now we have fixed the colors for all 6 sides. Now the only option we have left is for the remaining 3 diagonals, because we in total have 9 diagonals. So we have fixed the color for 6. So 2 raised to power 3, that is 8. So N A union B will be 64 plus 64 minus 8, that is 120. Is that it? So our total answer will be 2 raised to power 9, that is 512 minus 120. And we get 392. Is that it? Four, 1, 2, 392. And let's see the sum of squares of this digits. If we got it right, 9 plus 81 plus 4, that is 94. Alright. So this is how we do it. When we need at least one, so it's always better that you go through inclusion-exclusion route, where you check none of them are red and you exclude all of those cases. Okay, so it's a complicated one. I hope you will go through this video, all of these questions again, all of these questions that I have picked for you. You should go through all of these again. Even if you're preparing just for JEE, even then I think these are very good questions. If you are able to solve these questions, if you have been able to understand all of these questions, then you will be able to do any of the hard problems definitely in JEE. Olympiad, yes, you can still get harder problems than this, but this will be a good start for your prep. This will make sure that you can do at least 80% of the combinatorics problems. Alright, so the answer is 94. Now, another coloring thing, I'll get aside so that you can read the entire question. Unconventional dies are to be designed such that the 6 faces are marked with numbers from 1 to 6, with now 1 and 2 are appearing on opposite faces. Okay, so 1 and 2 will appear on opposite faces. Further, each face is colored either red or yellow. So we have two options for each face, either red or yellow, but the condition is that opposite faces always have the same color. So that means the face containing 1 and the face containing 2, both of those faces will have the same color, either red or yellow, but they have to have the same color. Okay, now 2 dice are considered to have the same design if one of them can be rotated to obtain a dice. Right, if you can rotate a dice and get the same configuration, that means they are identical, right? There is no difference, there is no top face and bottom face. So if you get the same configuration after rotating a die, then that is the same die essentially. Find the number of distinct dice that can be designed. So the only condition that we have is 1 and 2 need to be on the opposite sides, and the opposite faces have to have the same color, either red or yellow. Okay, 48 is the right answer. Very good. Let's see how we can actually approach this problem. So let's make a dice. So we have a cube like this, right? Now let's fix 1 and 2. Let's say 1 is on the left face and 2 has to be on the right face. We'll color them later, but let's first fix the numbers. Okay, so 1 and 2 are on the opposite sides. Let's now fix 3 here, right? No matter on which face 3 is out of these 4, we can find a configuration where 1 is on my left, 2 is on my right and 3 is on the top. So let's fix this configuration now. Now it's like a circular arrangement, right? You can rotate this and get the same arrangement. So now we have to arrange the remaining 3 numbers on these 3 faces. So 3 factorial. And now we have numbered the dice. Right, now we have unique configuration for the numbers. Now comes the color part. 1 and 2 need to have the same color. 3 and whatever goes on the bottom face need to have the same color, and these 2 have to have the same color. Basically, we have to color these 3 sets of opposite faces. So 2 options for left and right, 2 options for top and bottom, and 2 options for front and back. And that is your final number of configuration. So first you fix the numbers here and then you color the dice. So this comes out to be 6 into 8, 48. Okay. So this is just like circular arrangement, even though it's a cube, but it's like if you fix 1 here and 2 here, then you can just rotate the dice to get the same arrangement. So it is like a circular arrangement. Okay. The answer is 48. N is a natural number. Consider non-negative integer valued functions, which means f on 1 to an n, right? Satisfying f of I is greater than equal to f of j for I greater than j. And sigma I plus f of I for all I going from 1 to n is 2023. I think they picked the number because the year was 2023. So choose n such that sigma f of I is the least. We have to pick the n such that sigma f of I is the least. Now, how many such functions can exist? So first we have to find the value of n, and once we have n, we have to find f of I. It's a little tricky, so let's just dive into the solution, okay? Meanwhile, if you want to try, you can pause and keep trying and then check the solution. Yes, function is non-decreasing, yeah. So, it's a non-negative integer valued function. So, we can only have integers as the answer of f of I. Now, let's just first find the value of n. So, we have I is equal to 1 to n I plus sigma f of I going from 1 to n. This is 2023. This we know is n plus 1 by 2, which means sigma f of I going from 1 to n is 2023 minus n plus 1 by 2. Now we have to find the n such that this value is the least. This value is least, which means n into n plus 1 by 2 needs to be maximum, but at the same time this is non-negative. The answer cannot be negative, so the sum can also not be negative. So this has to be greater than equal to 0. Right? So now we just find the answer, the maximum n, such that this is less than equal to 2023. And we have done this question before, right? When we are trying to find the maximum n, you just check which n will give you which is the highest n for which this will satisfy, because this is an increasing function though. So you will keep getting a higher and higher answer. As soon as you get a value which is greater than 2023, you will stop there and choose the n before that. So we need the highest possible n for which this inequality holds. You can check, you can solve this. The highest n comes out to be 63. Okay. So this is how we first needed to choose the n such that sigma f of I is least. What is this value? 63 into 64. So 63 into 64 by 2, sigma fi is 2023 minus 63 into 64 by 2. So 63 into 32, and we subtract that. So 2023 minus 2016, and the answer is 7. Not the answer, but sigma f of I. Now we have the problem we actually need to solve. Now we need the function such that sigma f of I is 7. Sigma f of I is 7. And the answers can only be non-negative integer. F of I can only be non-negative integer. It cannot be more than, it cannot be negative. So now sigma f of I is 7. We need to partition this into integers such that the function, as someone said, is non-decreasing. It keeps either it stays the same or increases, right? So that means if we go in the reverse order, then the highest number can either be 7 or 6 or 5 up to 1, right? So the highest number when it's 7, then all the other will be 0. So that means this will give 1 possibility. If it is 6, then we have 1 remaining. So the next one has to be 1. After that, all of them are 0. So this will also give 1 option. Now if it's 5, then we have already taken 5 out of this sum. We have 2 remaining. Either we can do 2 or we can do 1, 1. So 2 options. Now if we have 4, then we have 3 remaining. Either we go 3 or 2, 1 or 1, 1, 1. So 3 possibilities. If we have 3, then we can do 3, 1, 2, 2 or 2, 1, 1 and then finally 1, 1, 1, 1. So like this, it has to be decreasing because we are checking in the reverse order and the remaining are 0. So 1, 2, 3, 4 possibilities. What's the total so far? 2 plus 2, 4 plus 3, 7 plus 4, 11. And we have reached 3 now. Now let's fix 2. Now either the next one can be 2 and the remaining are 1. 3 ones, right? 2 plus 2, 4 and 3 ones. Or it can be 1 and then the remaining are all 1. 4 ones, right? So 2 options for when we have 2. Correct, 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 correct. Are we missing anything? As I mentioned in the first class, we have to check in the reverse order, right? So the highest is 7. You get one option 6, then one option 5. Then either we have the next one is 2 or 1, 1. Then 4. The next one cannot be 4, right? It cannot be 4. So it has to be 3 or 2. And then we have 6, so the remaining is 1. Or we have 1 and then 5 plus 1 because it has to decrease. So we have 3 possibilities here. And now if we have the first one as 3, so the next one can be 3. And in that case, we have 3 plus 3, 6, plus 1, 7, 3 plus 2, 5, plus 2, 7, or 3 plus 2 plus 1 plus 1, or 3 plus 4, 1. Right, these are the only options. 2, 4. We're missing one here. Now, if we have 2 here, so 2 plus 2, 4. Now, what's remaining? 3. We can have another 2 here and then 1. Or we have 2, 2, 1, 1, 1 or 1, 1, 1, 1, 1. How many? 1, 2, 3, 4, 5. Yeah. Right? So, these are the 3 possibilities. And finally, the last possibility when the maximum is 1, so all the remaining are 1 and we get one option for this. So 1 plus 1, 2 plus 2, 4 plus 3, 7 plus 4, 11 plus 3, 14 plus 1, 15. So you have to be smart with these calculations. Of course, there are other methods to solve this, but I think this is the most trivial one. You just have to make sure that you're not missing any of them. If you just consider them case by case, then you will have all the possible arrangements such that it's in decreasing order. Okay, so always follow an order so that you don't miss any case. And now the last question for this session, and then I think you will have done enough practice that you can solve more problems very easily. You have done almost every type of problems in these 2 sessions and as well as the previous 10 theory sessions. So this is the last question. Let's do this one. Consider 5 points in the plane with no 3 of them collinear. It's kind of like our hexagon problem. We have to color the sides such that no 3 of them have the same color. So now let's just look at another coloring problem, because that happens, that shows up in our Olympiad paper very often, right? These coloring things, and you just have to go about it logically. There is no one right solution. So that is why I've added 2-3 problems in this set so that you can actually see how to approach such problems. Now, so we have 5 points such that no 3 of them are collinear, which means no 3 can be on the straight line. We have 5 points. Every pair of points among them is joined by a line. In how many ways can we color these lines? How many arrangements are there? 5, C, 2, right? Which is 10. So 10 will be these sides, and the other, 5 will be these sides, and the other 5 will be the diagonals, which will form like a star. And these are all our 10 line segments joining each of the 2 vertices, each vertex with every other vertex basically. What is the problem now? The problem is how many ways can we color these lines by red or blue? We have to color them again either red or blue such that no 3 of the points form a triangle with lines of the same color. We cannot have the same color. If we pick, let's say, this triangle, any triangle, if you take any triangle, then these 3 cannot be same color. And now you pick any triangle and all the 3 sides cannot be the same color. That has to be true for every triangle here. So how do we go about this? We do it case by case. So case 1, all sides, we have a pentagon, right, which has 5 sides and 5 diagonals. So let's say all sides are same color, either red or blue, but we have same color. Okay, so 1, 2, 3, 4, 5. Now we are trying to form a triangle. We are actually trying to form all the triangles as that no triangle has all the same color as their sides. Basically, if we pick this triangle, if we pick these 2 sides, then the third side cannot be red. So it has to be blue. And that has to be true for every diagonal, because every diagonal here is forming a triangle with 2 adjacent sides, right? You take any diagonal here and it is forming a triangle with 2 adjacent sides. Now we have colored 2 adjacent sides as the same color. Red in this case, it can also be blue, but the third one cannot be that same color. So it has to be the other color. So that is why these, once we fix the color of the 5 sides, the 5 diagonals will have the other color. And now I'll just make sure that any of the other triangles are not having the same color. No, all of them are such that the 3 sides cannot have the same color. So how many possibilities are here? We color all of them the same color. Which color? 2 options, and then we have 1 possible arrangement once we fix the color. So 2 here. Now let's move on to the other case. Case 2. Case 2 is, now we had 4 sides are same color. Now let's say 5 sides are same color. Now let's say 4 sides are same color. So let's say 4 sides have same color. I'm choosing red. It can also be blue. We will count that again. So if I fix, now watch carefully, okay? If we fix these 4 sides, now this diagonal has to be blue because we are considering this triangle, and similarly this triangle also has to be blue. This diagonal also has to be blue. But if that happens, then this triangle is all blue, which is not allowed. So that means we get 0 possible arrangements for this particular case. When we have one side as another color, then this triangle will always be of the same color if we are trying to make sure that these two triangles are not of the same color. So anyway, we cannot have this condition met in this case. Now let's move on to the next case where 3 consecutive sides have same color, or 3 sides have same color. Okay. So now case 3 is 3 sides have same color. Now there are 2 options for that. Either 3 consecutive sides have same color, or 2 consecutive and then 1 opposite, right? If we are choosing 3 sides with same color, it can be red or it can be blue, but these are the only possible arrangements, right? 2 consecutive or 3 consecutive. This has 3 consecutive or 2 consecutive and 1 opposite. Now 2 sides have same color. We will not have a case 4 that 2 sides have same color, because if 2 sides have same color, that means the other 3 have the same color, and we already considered that. If one side has same color, that means the other 4 have same color, so which we have already considered. So this is our last case which has 2 possibilities. Let's look at them one by one. In this case, this top triangle, this has to be blue, right? And now these 2 sides are already blue, so this has to be red. Okay, like that we will start coloring each diagonal. Now this will be blue, and this will be red, because these 2 are already blue, so this will be red. Now this last remaining diagonal, the one yellow one, if I make this blue, then this triangle in the middle will be blue, so it cannot be blue. If I make this red, then this triangle here will be red, which is again not allowed. So that means there is no possible configuration for coloring these such that our condition is met. So 0 again. Okay, so just watch very carefully. If you missed something, then go back to the video and you will see how we were coloring every diagonal and we could not find any color for this diagonal, which means 0 possibility. Now let's come here. Here, how do we color these? We have these 2 as red, so we start with blue here. Now these 2 are blue, so red here. These 2 are blue, so red here. Now these 2 are red, so blue here. These 2 are red, so blue here. And now we can see that every triangle has at least one different color and two same colors, right? So this is a valid arrangement. So and that is the only possible arrangement. As soon as we fixed which two consecutive sides have the same color and which has the different color, then we get exactly one arrangement. We did that one by one and there was not any other option for this, right? So 1 here. But now we have to find how many ways can we have this arrangement. So bache, as soon as we fix the opposite side's color, I picked this side and I know its color, which means I picked the side 5C1 and I picked the color 2C1. Now as soon as I have this, I know that the adjacent sides to that one will be the opposite color and the other two will be the same color. And once I have this arrangement, I saw that there's only one possible arrangement, one possible coloring for the diagonals. So like this, we will have our final arrangement. So basically what did we have to do? We just had to fix the opposite side, which side and which color, and as soon as we did that, we had the entire coloring. So this comes out to be 5 into 2 into 1, 10. So 10 from this case, right? I know it's a bit tricky. You might have to go back and think about this on your own. That will be the best thing to do. All right. Now, so that means case 1 had 2, case 2 had 0, case 3 had 10. So the final answer is 2 plus 10. Answer is 12. All right. So if you are taking something away from this entire course, this entire practice session and the course session, what you need to do is make sure that you're counting all the right cases. You're doing that in some particular order so that you're not missing any case, you're not repeating any case, and that is all what combinatorics is about. I have said this in almost every lecture. All you have to make sure is you're counting every case and be a little smart about it so that you don't have to actually list all the cases in every question, but in some questions you have to list all the cases. But be smart about how you're counting them so that you're not missing any of them, you're not repeating any of them. Chalo, let's end the session here. All the very best. Keep practicing and definitely revise everything we have gone through. Definitely revise every question we have solved, every theory we have done, and keep practicing. Your Olympiad, your any exam that you're targeting will be amazing. It will go great. Okay. Chalo, bye.